Part 2. Some structural components of a theory of experience. Theories. The empirical sciences are systems of theories. The logic of scientific knowledge can therefore be described as a theory of theories. Scientific theories are universal statements. Like all linguistic representations, they are systems of signs or symbols. Thus I do not think it helpful to express the difference between universal theories and singular statements by saying that the latter are concrete whereas theories are merely symbolic formulae or symbolic schemata, for exactly the same may be said of even the most concrete statements. Theories are nets cast to catch what we call the world, to rationalize, to explain, and to master it. We endeavor to make the mesh ever near and near. One causality, explanation, and the deduction of predictions. To give a causal explanation of an event means to deduce a statement which describes it, using as premises of the deduction one or more universal laws, together with certain singular statements, the initial conditions. For example, we can say that we have given a causal explanation of the breaking of a certain piece of thread if we have found that the thread has a tensile strength of pound and that a weight of pounds was put on it. If we analyze this causal explanation, we shall see several constituent parts. On the one hand, there is the hypothesis: whenever a thread is loaded with a weight exceeding that which characterizes the tensile strength of the thread, then it will break, a statement which has the character of a universal law of nature. On the other hand, we have singular statements, in this case too, which apply only to the specific event in question. The weight characteristic for this thread is pound, and the weight put on this thread was pounds. We have thus two different kinds of statement, both of which are necessary ingredients of a complete causal explanation. They are universal statements, i.e. hypotheses of the character of natural laws, and singular statements, which apply to the specific event in question and which I shall call initial conditions. It is from universal statements in conjunction with initial conditions that we deduce the singular statement: this thread will break. We call this statement a specific or singular prediction. The initial conditions describe what is usually called the cause of the event in question. The fact that a load of pounds was put on a thread with a tensile strength of pound was the cause of its breaking. And the prediction describes what is usually called the effect. Both these terms I shall avoid. In physics, the use of the expression causal explanation is restricted as a rule to the special case in which the universal laws have the form of laws of action by contact, or more precisely, of action at a vanishing distance, expressed by differential equations. This restriction will not be assumed here. Furthermore, I shall not make any general assertion as to the universal applicability of this deductive method of the theoretical explanation. Thus I shall not assert any principle of causality, or principle of universal causation. The principle of causality is the assertion that any event whatsoever can be causally explained, that it can be deductively predicted. According to the way in which one interprets the word can in this assertion, it will be either tautological, analytic, or else an assertion about reality, synthetic. For if can means that it is always logically possible to construct a causal explanation, then the assertion is tautological, since for any prediction whatsoever we can always nd universal statements and initial conditions from which the prediction is derivable. Whether these universal statements have been tested and corroborated in other cases is of course quite a different question. If, however, can is meant to signify that the world is governed by strict laws, that it is so constructed that every specific event is an instance of a universal regularity or law, then the assertion is admittedly synthetic. But in this case it is not falsifiable, as will be seen later, in section. I shall, therefore, neither adopt nor reject the principle of causality. I shall be content simply to exclude it, as metaphysical, from the sphere of science. I shall, however, propose a methodological rule which corresponds so closely to the principle of causality that the latter might be regarded as its metaphysical version. It is the simple rule that we are not to abandon the search for universal laws and for a coherent theoretical system, nor ever give up our attempts to explain causally any kind of event we can describe. This rule guides the scientific investigator in his work. The view that the latest developments in physics demand the renunciation of this rule, or that physics has now established that within one eld at least it is pointless to seek any longer for laws, is not accepted here. This matter will be discussed in section 2. Strict and numerical universality. We can distinguish two kinds of universal synthetic statement, the strictly universal and the numerically universal. It is the strictly universal statements which I have had in mind so far when speaking of universal statements of theories or natural laws. The other kind, the numerically universal statements, are in fact equivalent to certain singular statements, or to conjunctions of singular statements, and they will be classed as singular statements here. Compare, for example, the following two statements: A. Of all harmonic oscillators it is true that their energy never falls below a certain amount, viz. HV/, and B. Of all human beings now living on the earth it is true that their height never exceeds a certain amount, say foot. Formal logic, including symbolic logic, which is concerned only with the theory of deduction, treats these two statements alike as universal statements, formal or general implications. I think, however, that it is necessary to emphasize the difference between them. Statement A claims to be true for any place and any time. Statement B refers only to a night class of specific elements within a night individual, or particular, spatio-temporal region. Statements of this latter kind can, in principle, be replaced by a conjunction of singular statements. For given sufficient time, one can enumerate all the elements of the night class concerned. This is why we speak in such cases of numerical universality. By contrast, statement A about the oscillators cannot be replaced by a conjunction of a night number of singular statements about a d-night spatio-temporal region, or rather, it could be so replaced only on the assumption that the world is bounded in time and that there exists only a night number of oscillators in it. But we do not make any such assumption. In particular, we do not make any such assumption in denying the concepts of physics. Rather, we regard a statement of type A as an all statement, i.e. a universal assertion about an unlimited number of individuals. So interpreted, it clearly cannot be replaced by a conjunction of a night number of singular statements. My use of the concept of a strictly universal statement, or all statement, stands opposed to the view that every synthetic universal statement must in principle be translatable into a conjunction of a night number of singular statements. Those who adhere to this view insist that what I call strictly universal statements can never be very ed, and they therefore reject them, referring either to their criterion of meaning, which demands variability, or to some similar consideration. It is clear that on any such view of natural laws which obliterates the distinction between singular and universal statements, the problem of induction would seem to be solved, for obviously, inferences from singular statements to merely numerically universal ones may be perfectly admissible. But it is equally clear that the methodological problem of induction is not acted by this solution. For the verification of a natural law could only be carried out by empirically ascertaining every single event to which the law might apply, and by ending that every such event actually conforms to the law, clearly an impossible task. In any case, the question whether the laws of science are strictly or numerically universal cannot be settled by argument. It is one of those questions which can be settled only by an agreement or a convention. And in view of the methodological situation just referred to, I consider it both useful and fruitful to regard natural laws as synthetic and strictly universal statements, all statements. This is to regard them as non-variable statements which can be put in the form, of all points in space and time, or in all regions of space and time. It is true that, by contrast, statements which relate only to certain night regions of space and time I call specific or singular statements. The distinction between strictly universal statements and merely numerically universal statements, i.e. really a kind of singular statement, will be applied to synthetic statements only. I may, however, mention the possibility of applying this distinction to analytic statements also, for example, to certain mathematical statements. 14 Universal concepts and individual concepts. The distinction between universal and singular statements is closely connected with that between universal and individual concepts or names. It is usual to elucidate this distinction with the help of examples of the following kind: dictator, planet, hoe are universal concepts or universal names. Napoleon, the earth, the Atlantic are singular or individual concepts or names. In these examples, individual concepts or names appear to be characterized either by being proper names, or by having to be deemed by means of proper names, whilst universal concepts or names can be deemed without the use of proper names. I consider the distinction between universal and individual concepts or names to be of fundamental importance. Every application of science is based upon an inference from scientific hypotheses, which are universal, to singular cases, i.e. upon a deduction of singular predictions. But in every singular statement individual concepts or names must occur. The individual names that occur in the singular statements of science often appear in the guise of spatio-temporal coordinates. This is easily understood if we consider that the application of a spatio-temporal system of coordinates always involves reference to individual names. For we have to x its points of origin, and this we can do only by making use of proper names, or their equivalents. The use of the names Greenwich and the year of Christ's birth illustrates what I mean. By this method an arbitrarily large number of individual names may be reduced to a very few. Such vague and general expressions as this thing here, that thing over there, etc., can sometimes be used as individual names, perhaps in conjunction with ostensive gestures of some kind. In short, we can use signs which are not proper names but which to some extent are interchangeable with proper names or with individual coordinates. But universal concepts too can be indicated, if only vaguely, with the help of ostensive gestures. Thus we may point to certain individual things, or events, and then express by a phrase like "and other similar things," or and so on, our intention to regard these individuals only as representatives of some class which should properly be given a universal name. There can be no doubt that we learn the use of universal words, that is their application to individuals, by ostensive gestures and by similar means. The logical basis of applications of this kind is that individual concepts may be concepts not only of elements but also of classes, and that they may thus stand to universal concepts not only in a relation corresponding to that of an element to a class, but also in a relation corresponding to that of a subclass to a class. For example, my dog Lux is not only an element of the class of Viennese dogs, which is an individual concept, but also an element of the universal class of mammals, which is a universal concept. And the Viennese dogs, in their turn, are not only a subclass of the individual class of Austrian dogs, but also a subclass of the universal class of mammals. The use of the word mammals as an example of a universal name might possibly cause misunderstanding. For words like mammal, dog, etc., are in their ordinary use not free from ambiguity. Whether these words are to be regarded as individual class names or as universal class names depends upon our intentions. It depends upon whether we wish to speak of a race of animals living on our planet, an individual concept, or of a kind of physical bodies with properties which can be described in universal terms. Similar ambiguities arise in connection with the use of concepts such as pasteurized, Linnean system, and Latinism, insofar as it is possible to eliminate the proper names to which they allude, or else, to deem them with the help of these proper names. The above examples and explanations should make it clear what will here be meant by universal concepts and individual concepts. If I were asked for definitions, I should probably have to say, as above, an individual concept is a concept in the definition of which proper names, or equivalent signs, are indispensable. If any reference to proper names can be completely eliminated, then the concept is a universal concept. Yet any such definition would be of very little value, since all that it does is to reduce the idea of an individual concept or name to that of a proper name, in the sense of a name of one individual physical thing. I believe that my usage corresponds fairly closely to the customary use of the expressions universal and individual. But whether or not this is so, I certainly consider the distinction here made to be indispensable if we are not to blur the corresponding distinction between universal and singular statements. There is a complete analogy between the problem of universals and the problem of induction. The attempt to identify an individual thing merely by its universal properties and relations, which appear to belong to it alone and to nothing else, is foredoomed to failure. Such a procedure would describe not a single individual thing but the universal class of all those individuals to which these properties and relations belong. Even the use of a universal spatio-temporal system of coordinates would alter nothing. For whether there are any individual things corresponding to a description by means of universal names, and if so how many, must always remain an open question. In the same way, any attempt to deem universal names with the help of individual names is bound to fail. This fact has often been overlooked, and it is widely believed that it is possible to rise by a process called abstraction from individual concepts to universal concepts. This view is a near relation of inductive logic, with its passage from singular statements to universal statements. Logically, these procedures are equally impracticable. It is true that one can obtain classes of individuals in this way, but these classes will still be individual concepts deemed with the help of proper names. Examples of such individual class concepts are Napoleon's generals, and the inhabitants of Paris. Thus we see that my distinction between universal names or concepts and individual names or concepts has nothing to do with the distinction between classes and elements. Both universal names and individual names may occur as names of some classes, and also as the names of elements of some classes. It is therefore not possible to abolish the distinction between individual concepts and universal concepts with arguments like the following of Carnap's. This distinction is not justified, he says, because every concept can be regarded as an individual or universal concept according to the point of view adopted. Carnap tries to support this by the assertion that, almost, all so-called individual concepts are, names of, classes, just like universal concepts. This last assertion is quite correct, as I have shown, but has nothing to do with the distinction in question. Other workers in the field of symbolic logic, at one time called logistics, have similarly confused the distinction between universal names and individual names with the distinction between classes and their elements. It is certainly permissible to use the term universal name as a synonym for name of a class, and individual name as a synonym for name of an element, but there is little to be said for this usage. Problems cannot be solved in this way. On the other hand, this usage may very well prevent one from seeing them. The situation here is quite similar to what we met before when discussing the distinction between universal and singular statements. The instruments of symbolic logic are no more adequate for handling the problem of universals than for handling the problem of induction. 15 Strictly universal and existential statements. It is not enough, of course, to characterize universal statements as statements in which no individual names occur. If the word raven is used as a universal name, then, clearly, the statement all ravens are black is a strictly universal statement. But in many other statements such as many ravens are black or perhaps some ravens are black or there are black ravens, etc., there also occur only universal names, yet we should certainly not describe such statements as universal. Statements in which only universal names and no individual names occur will here be called strict or pure. Most important among them are the strictly universal statements which I have already discussed. In addition to these, I am especially interested in statements of the form there are black ravens, which may be taken to mean the same as there exists at least one black raven. Such statements will be called strictly or purely existential statements, or there is statements. The negation of a strictly universal statement is always equivalent to a strictly existential statement and vice versa. For example, not all ravens are black says the same thing as there exists a raven which is not black, or there are non-black ravens. The theories of natural science, and especially what we call natural laws, have the logical form of strictly universal statements, thus they can be expressed in the form of negations of strictly existential statements or, as we may say, in the form of non-existence statements, or there is not statements. For example, the law of the conservation of energy can be expressed in the form, there is no perpetual motion machine, or the hypothesis of the electrical elementary charge in the form, there is no electrical charge other than a multiple of the electrical elementary charge. In this formulation we see that natural laws might be compared to proscriptions or prohibitions. They do not assert that something exists or is the case, they deny it. They insist on the non-existence of certain things or states of affairs, proscribing or prohibiting, as it were, these things or states of affairs, they rule them out. And it is precisely because they do this that they are falsifiable. If we accept as true one singular statement which, as it were, infringes the prohibition by asserting the existence of a thing, or the occurrence of an event, ruled out by the law, then the law is refuted. An instance would be, in such and such a place, there is an apparatus which is a perpetual motion machine. Strictly existential statements, by contrast, cannot be falsified. No singular statement, that is to say, no basic statement, no statement of an observed event, can contradict the existential statement, there are white ravens. Only a universal statement could do this. On the basis of the criterion of demarcation here adopted, I shall therefore have to treat strictly existential statements as non-empirical or metaphysical. This characterization may perhaps seem dubious at RST sight and not quite in accordance with the practice of empirical science. By way of objection, it might be asserted, with justice, that there are theories even in physics which have the form of strictly existential statements. An example would be a statement, deducible from the periodic system of chemical elements, which asserts the existence of elements of certain atomic numbers. But if the hypothesis that an element of a certain atomic number exists is to be so formulated that it becomes testable, then much more is required than a purely existential statement. For example, the element with the atomic number, hafnium, was not discovered merely on the basis of an isolated purely existential statement. On the contrary, all attempts to end it were in vain until Bohr succeeded in predicting several of its properties by deducing them from his theory. But Bohr's theory and those of its conclusions which were relevant to this element and which helped to bring about its discovery are far from being isolated purely existential statements. They are strictly universal statements. That my decision to regard strictly existential statements as non-empirical because they are not falsifiable is helpful, and also in accordance with ordinary usage, will be seen from its application to probability statements and to the problem of testing them empirically. Cf. sections. Strict or pure statements, whether universal or existential, are not limited as to space and time. They do not refer to an individual, restricted, spatio-temporal region. This is the reason why strictly existential statements are not falsifiable. We cannot search the whole world in order to establish that something does not exist, has never existed, and will never exist. It is for precisely the same reason that strictly universal statements are not variable. Again, we cannot search the whole world in order to make sure that nothing exists which the law forbids. Nevertheless, both kinds of strict statements, strictly existential and strictly universal, are in principle empirically decidable, each, however, in one way only, they are unilaterally decidable. Whenever it is found that something exists here or there, a strictly existential statement may thereby be varied, or a universal one falsified. The asymmetry here described, with its consequence, the one-sided falsifiability of the universal statements of empirical science, may now perhaps seem less dubious than it did before, in section. We now see that no asymmetry of any purely logical relationship is involved. On the contrary, the logical relationships show symmetry. Universal and existential statements are constructed symmetrically. It is only the line drawn by our criterion of demarcation which produces an asymmetry. 16. Theoretical systems. Scientific theories are perpetually changing. This is not due to mere chance but might well be expected, according to our characterization of empirical science. Perhaps this is why, as a rule, only branches of science, and these only temporarily, ever acquire the form of an elaborate and logically well-constructed system of theories. In spite of this, a tentative system can usually be quite well surveyed as a whole, with all its important consequences. This is very necessary, for a severe test of a system presupposes that it is at the time sufficiently definite and null in form to make it impossible for new assumptions to be smuggled in. In other words, the system must be formulated sufficiently clearly and definitely to make every new assumption easily recognizable for what it is, a modification and therefore a revision of the system. This, I believe, is the reason why the form of a rigorous system is aimed at. It is the form of a so-called axiomatized system, the form which Hilbert, for example, was able to give to certain branches of theoretical physics. The attempt is made to collect all the assumptions which are needed, but no more, to form the apex of the system. They are usually called the axioms, or postulates, or primitive propositions. No claim to truth is implied in the term axiom as here used. The axioms are chosen in such a way that all the other statements belonging to the theoretical system can be derived from the axioms by purely logical or mathematical transformations. A theoretical system may be said to be axiomatized if a set of statements, the axioms, has been formulated which satisfies the following four fundamental requirements. A. The system of axioms must be free from contradiction, whether self-contradiction or mutual contradiction. This is equivalent to the demand that not every arbitrarily chosen statement is deducible from it. B. The system must be independent, i.e., it must not contain any axiom deducible from the remaining axioms. In other words, a statement is to be called an axiom only if it is not deducible within the rest of the system. These two conditions concern the axiom system as such. As regards the relation of the axiom system to the bulk of the theory, the axioms should be, c. sufficient for the deduction of all statements belonging to the theory which is to be axiomatized, and d. necessary, for the same purpose, which means that they should contain no superfluous assumptions. In a theory thus axiomatized, it is possible to investigate the mutual dependence of various parts of the system. For example, we may investigate whether a certain part of the theory is derivable from some part of the axioms. Investigations of this kind, of which more will be said in sections and 2, have an important bearing on the problem of falsifiability. They make it clear why the falsification of a logically deduced statement may sometimes not eat the whole system but only some part of it, which may then be regarded as false-ed. This is possible because, although the theories of physics are in general not completely axiomatized, the connections between its various parts may yet be sufficiently clear to enable us to decide which of its subsystems are acted by some particular falsifying observation. 17. Some possibilities of interpreting a system of axioms. The view of classical rationalism that the axioms of certain systems, those of Euclidean geometry, must be regarded as immediately or intuitively certain, or self-evident, will not be discussed here. I will only mention that I do not share this view. I consider two different interpretations of any system of axioms to be admissible. The axioms may be regarded either, I, as conventions, or they may be regarded, 2, as empirical or scientific hypotheses. I, if the axioms are regarded as conventions, then they tie down the use or meaning of the fundamental ideas, or primitive terms, or concepts, which the axioms introduce. They determine what can and what cannot be said about these fundamental ideas. Sometimes the axioms are described as implicit definitions of the ideas which they introduce. This view can perhaps be elucidated by means of an analogy between an axiomatic system and a consistent and soluble system of equations. The admissible values of the unknowns, or variables, which appear in a system of equations are in some way or other determined by it. Even if the system of equations does not suffice for a unique solution, it does not allow every conceivable combination of values to be substituted for the unknowns, variables. Rather, the system of equations characterizes certain combinations of values or value systems as admissible, and others as inadmissible. It distinguishes the class of admissible value systems from the class of inadmissible value systems. In a similar way, systems of concepts can be distinguished as admissible or as inadmissible by means of what might be called a statement equation. A statement equation is obtained from a propositional function or statement function. Cf. Note to section. This is an incomplete statement, in which one or more blanks occur. Two examples of such propositional functions or statement functions are, an isotope of the element X has the atomic weight, or X plus Y equals. Every such statement function is transformed into a statement by the substitution of certain values for the blanks X and Y. The resulting statement will be either true or false, according to the values, or combination of values, substituted. Thus, in the RST example, substitution of the word copper or zinc for X yields a true statement, while other substitutions yield false ones. Now what I call a statement equation is obtained if we decide, with respect to some statement function, to admit only such values for substitution as turn this function into a true statement. By means of this statement equation a finite class of admissible value systems is deemed, namely the class of those which satisfy it. The analogy with a mathematical equation is clear. If our second example is interpreted, not as a statement function, but as a statement equation, then it becomes an equation in the ordinary, mathematical, sense. Since its undefined fundamental ideas or primitive terms can be regarded as blanks, an axiomatic system can, to begin with, be treated as a system of statement functions. But if we decide that only such systems or combinations of values may be substituted as will satisfy it, then it becomes a system of statement equations. As such it implicitly deems a class of admissible systems of concepts. Every system of concepts which satisfies a system of axioms can be called a model of that system of axioms. The interpretation of an axiomatic system as a system of conventions or implicit definitions can also be expressed by saying that it amounts to the decision, only models may be admitted as substitutes. But if a model is substituted then the result will be a system of analytic statements, since it will be true by convention. An axiomatic system interpreted in this way cannot therefore be regarded as a system of empirical or scientific hypotheses, in our sense, since it cannot be refuted by the falsification of its consequences, for these two must be analytic. 2. How then, it may be asked, can an axiomatic system be interpreted as a system of empirical or scientific hypotheses? The usual view is that the primitive terms occurring in the axiomatic system are not to be regarded as implicitly deemed, but as extra-logical constants. For example, such concepts as straight line and point, which occur in every axiom system of geometry, may be interpreted as light ray and intersection of light rays. In this way, it is thought, the statements of the axiom system become statements about empirical objects, that is to say, synthetic statements. At RST site, this view of the matter may appear perfectly satisfactory. It leads, however, to difficulties which are connected with the problem of the empirical basis. For it is by no means clear what would be an empirical way of defining a concept. It is customary to speak of ostensive definitions. This means that a finite empirical meaning is assigned to a concept by correlating it with certain objects belonging to the real world. It is then regarded as a symbol of those objects. But it should have been clear that only individual names or concepts can be xed by ostensibly referring to real objects, say, by pointing to a certain thing and uttering a name, or by attaching to it a label bearing a name, etc. Yet the concepts which are to be used in the axiomatic system should be universal names, which cannot be defined by empirical indications, pointing, etc. They can be defined if at all only explicitly, with the help of other universal names, otherwise they can only be left undefined. That some universal names should remain undefined is therefore quite unavoidable, and herein lies the difficulty. For these undefined concepts can always be used in the non-empirical sense, i.e. as if they were implicitly deemed concepts. Yet this use must inevitably destroy the empirical character of the system. This difficulty, I believe, can only be overcome by means of a methodological decision. I shall, accordingly, adopt a rule not to use undeemed concepts as if they were implicitly deemed. This point will be dealt with below in section 0. Here I may perhaps add that it is usually possible for the primitive concepts of an axiomatic system such as geometry to be correlated with, or interpreted by, the concepts of another system, e.g. physics. This possibility is particularly important when, in the course of the evolution of a science, one system of statements is being explained by means of a new or more general system of hypotheses which permits the deduction not only of statements belonging to the RST system, but also of statements belonging to other systems. In such cases it may be possible to deem the fundamental concepts of the new system with the help of concepts which were originally used in some of the old systems. 18 Levels of universality. The modus tollens. We may distinguish, within a theoretical system, statements belonging to various levels of universality. The statements on the highest level of universality are the axioms, statements on the lower levels can be deduced from them. Higher level empirical statements have always the character of hypotheses relative to the lower level statements deducible from them. They can be falsified by the falsification of these less universal statements. But in any hypothetical deductive system, these less universal statements are themselves still strictly universal statements, in the sense here understood. Thus they too must have the character of hypotheses, a fact which has often been overlooked in the case of lower-level universal statements. Mach, for example, calls Fourier's theory of heat conduction a model theory of physics for the curious reason that this theory is founded not on a hypothesis but on an observable fact. However, the observable fact to which Mach refers is described by him by the statement: the velocity of the leveling out of temperature differences, provided these differences of temperature are small, is proportional to these differences themselves in all statement whose hypothetical character should be sufficiently conspicuous. I shall say even of some singular statements that they are hypothetical, seeing that conclusions may be derived from them, with the help of a theoretical system, such that the falsification of these conclusions may falsify the singular statements in question. The falsifying mode of inference here referred to the way in which the falsification of a conclusion entails the falsification of the system from which it is derived is the modus tollens of classical logic. It may be described as follows. Let P be a conclusion of a system T of statements which may consist of theories and initial conditions. For the sake of simplicity I will not distinguish between them. We may then symbolize the relation of derivability, analytical implication, of P from T by T registered trademark P which may be read, P follows from T. Assume P to be false, which we may write P, to be read not P. Given the relation of deducibility, T registered trademark P, and the assumption P, we can then infer T, read not T, that is, we regard T as falsified. If we denote the conjunction, simultaneous assertion, of two statements by putting a point between the symbols standing for them, we may also write the falsifying inference thus, T registered trademark P, P, registered trademark T, or in words, if P is derivable from T, and if P is false, then T also is false. By means of this mode of inference we falsify the whole system, the theory as well as the initial conditions, which was required for the deduction of the statement P, i.e. of the falsified statement. Thus it cannot be asserted of any one statement of the system that it is, or is not, specifically upset by the falsification. Only if P is independent of some part of the system can we say that this part is not involved in the falsification. With this is connected the following possibility: we may, in some cases, perhaps in consideration of the levels of universality, attribute the falsification to some denied hypothesis, for instance to a newly introduced hypothesis. This may happen if a well-corroborated theory, and one which continues to be further corroborated, has been deductively explained by a new hypothesis of a higher level. The attempt will have to be made to test this new hypothesis by means of some of its consequences which have not yet been tested. If any of these are falsied, then we may well attribute the falsification to the new hypothesis alone. We shall then seek, in its stead, other high-level generalizations, but we shall not feel obliged to regard the old system, of lesser generality, as having been falsied. Cf. also the remarks on quasi-induction in section falsifiability. The question whether there is such a thing as a falsifiable singular statement, or a basic statement, will be examined later. Here I shall assume a positive answer to this question, and I shall examine how far my criterion of demarcation is applicable to theoretical systems if it is applicable at all. A critical discussion of a position usually called conventionalism will raise some problems of method, to be met by taking certain methodological decisions. Next I shall try to characterize the logical properties of those systems of theories which are falsifiable, that is, if our methodological proposals are adopted. 19. Some conventionalist objections. Objections are bound to be raised against my proposal to adopt falsifiability as our criterion for deciding whether or not a theoretical system belongs to empirical science. They will be raised, for example, by those who are influenced by the school of thought known as conventionalism. Some of these objections have already been touched upon in sections, and they will now be considered a little more closely. The source of the conventionalist philosophy would seem to be wonder at the austerely beautiful simplicity of the world as revealed in the laws of physics. Conventionalists seem to feel that this simplicity would be incomprehensible, and indeed miraculous, if we were bound to believe, with the realists, that the laws of nature reveal to us an inner, a structural, simplicity of our world beneath its outer appearance of lavish variety. Kant's idealism sought to explain this simplicity by saying that it is our own intellect which imposes its laws upon nature. Similarly, but even more boldly, the conventionalist treats this simplicity as our own creation. For him, however, it is not the act of the laws of our intellect imposing themselves upon nature, thus making nature simple, for he does not believe that nature is simple. Only the laws of nature are simple, and these, the conventionalist holds, are our own free creations, our inventions, our arbitrary decisions and conventions. For the conventionalist, theoretical natural science is not a picture of nature but merely a logical construction. It is not the properties of the world which determine this construction, on the contrary it is this construction which determines the properties of an artificial world, a world of concepts implicitly deemed by the natural laws which we have chosen. It is only this world of which science speaks. According to this conventionalist point of view, laws of nature are not falsifiable by observation, for they are needed to determine what an observation and, more especially, what a scientific measurement is. It is these laws, laid down, by us, which form the indispensable basis for the regulation of our clocks and the correction of our so-called rigid measuring rods. A clock is called accurate and a measuring rod rigid only if the movements measured with the help of these instruments satisfy the axioms of mechanics which we have decided to adopt. The philosophy of conventionalism deserves great credit for the way it has helped to clarify the relations between theory and experiment. It recognized the importance, so little noticed by inductivists, of the part played by our actions and operations, planned in accordance with conventions and deductive reasoning, in conducting and interpreting our scientific experiments. I regard conventionalism as a system which is self-contained and defensible. Attempts to detect inconsistencies in it are not likely to succeed. Yet in spite of all this I find it quite unacceptable. Underlying it is an idea of science, of its aims and purposes, which is entirely different from mine. Whilst I do not demand any null certainty from science, and consequently do not get it, the conventionalist seeks in science a system of knowledge based upon ultimate grounds, to use a phrase of Dingler's. This goal is attainable, for it is possible to interpret any given scientific system as a system of implicit definitions. And periods when science develops slowly will give little occasion for conflict unless purely academic to arise between scientists inclined towards conventionalism and others who may favor a view like the one I advocate. It will be quite otherwise in a time of crisis. Whenever the classical system of the day is threatened by the results of new experiments which might be interpreted as falsifications according to my point of view, the system will appear unshaken to the conventionalist. He will explain away the inconsistencies which may have arisen, perhaps by blaming our inadequate mastery of the system. Or he will eliminate them by suggesting ad hoc the adoption of certain auxiliary hypotheses, or perhaps of certain corrections to our measuring instruments. In such times of crisis this conflict over the aims of science will become acute. We, and those who share our attitude, will hope to make new discoveries, and we shall hope to be helped in this by a newly erected scientific system. Thus we shall take the greatest interest in the falsifying experiment. We shall hail it as a success, for it has opened up new vistas into a world of new experiences. And we shall hail it even if these new experiences should furnish us with new arguments against our own most recent theories. But the newly rising structure, the boldness of which we admire, is seen by the conventionalist as a monument to the total collapse of science, as Dingler puts it. In the eyes of the conventionalist, one principle only can help us to select a system as the chosen one from among all other possible systems. It is the principle of selecting the simplest system of implicit denitions, which of course means in practice the classical system of the day. For the problem of simplicity see sections, and especially. Thus my conflict with the conventionalists is not one that can be ultimately settled merely by a detached theoretical discussion. And yet it is possible, I think, to extract from the conventionalist mode of thought certain interesting arguments against my criterion of demarcation. For instance, the following. I admit, a conventionalist might say, that the theoretical systems of the natural sciences are not variable, but I assert that they are not falsifiable either. For there is always the possibility of attaining, for any chosen axiomatic system, what is called its correspondence with reality, and this can be done in a number of ways, some of which have been suggested above. Thus we may introduce ad hoc hypotheses. Or we may modify the so-called ostensive denitions, or the explicit denitions which may replace them as shown in section. Or we may adopt a skeptical attitude as to the reliability of the experimenter whose observations, which threaten our system, we may exclude from science on the ground that they are insouciantly supported, unscientific, or not objective, or even on the ground that the experimenter was a liar. This is the sort of attitude which the physicist may sometimes quite rightly adopt towards alleged occult phenomena. In the last resort we can always cast doubt on the acumen of the theoretician, for example if he does not believe, as does Dingler, that the theory of electricity will one day be derived from Newton's theory of gravitation. Thus, according to the conventionalist view, it is not possible to divide systems of theories into falsifiable and non-falsifiable ones, or rather, such a distinction will be ambiguous. As a consequence, our criterion of falsifiability must turn out to be useless as a criterion of demarcation. 20 Methodological rules. These objections of an imaginary conventionalist seem to me incontestable, just like the conventionalist philosophy itself. I admit that my criterion of falsifiability does not lead to an unambiguous classification. Indeed, it is impossible to decide, by analyzing its logical form, whether a system of statements is a conventional system of irrefutable implicit denitions, or whether it is a system which is empirical in my sense, that is, a refutable system. Yet this only shows that my criterion of demarcation cannot be applied immediately to a system of statements, a fact I have already pointed out in sections, and the question whether a given system should as such be regarded as a conventionalist or an empirical one is therefore misconceived. Only with reference to the methods applied to a theoretical system is it at all possible to ask whether we are dealing with a conventionalist or an empirical theory. The only way to avoid conventionalism is by taking a decision, the decision not to apply its methods. We decide that if our system is threatened we will never save it by any kind of conventionalist stratagem. Thus we shall guard against exploiting the ever-open possibility just mentioned of attaining for any chosen system what is called its correspondence with reality. A clear appreciation of what may be gained, and lost, by conventionalist methods was expressed, 100 years before Poincaré, by Black, who wrote, "A nice adaptation of conditions will make almost any hypothesis agree with the phenomena. This will please the imagination but does not advance our knowledge." In order to formulate methodological rules which prevent the adoption of conventionalist stratagems, we should have to acquaint ourselves with the various forms these stratagems may take, so as to meet each with the appropriate anti-conventionalist counter-move. Moreover, we should agree that, whenever we nd that a system has been rescued by a conventionalist stratagem, we shall test it afresh, and reject it, as circumstances may require. The four main conventionalist stratagems have already been listed at the end of the previous section. The list makes no claim to completeness, it must be left to the investigator, especially in the fields of sociology and psychology. The physicist may hardly need the warning, to guard constantly against the temptation to employ new conventionalist stratagems, a temptation to which psychoanalysts, for example, often succumb. As regards auxiliary hypotheses, we propose to lay down the rule that only those are acceptable whose introduction does not diminish the degree of falsifiability or testability of the system in question, but, on the contrary, increases it. How degrees of falsifiability are to be estimated will be explained in sections 2-0. If the degree of falsifiability is increased, then introducing the hypothesis has actually strengthened the theory. The system now rules out more than it did previously, it prohibits more. We can also put it like this. The introduction of an auxiliary hypothesis should always be regarded as an attempt to construct a new system, and this new system should then always be judged on the issue of whether it would, if adopted, constitute a real advance in our knowledge of the world. An example of an auxiliary hypothesis which is eminently acceptable in this sense is Pauli's exclusion principle, cf. section. An example of an unsatisfactory auxiliary iliary hypothesis would be the contraction hypothesis of Fitzgerald and Lawrence, which had no falsifiable consequences but merely served to restore the agreement between theory and experiment, mainly the endings of Michelson and Morley. An advance was here achieved only by the theory of relativity, which predicted new consequences, new physical eaks, and thereby opened up new possibilities for testing, and for falsifying, the theory. Our methodological rule may be quali-ed by the remark that we need not reject, as conventionalistic, every auxiliary hypothesis that fails to satisfy these standards. In particular, there are singular statements which do not really belong to the theoretical system at all. They are sometimes called auxiliary hypotheses, and although they are introduced to assist the theory, they are quite harmless. An example would be the assumption that a certain observation or measurement which cannot be repeated may have been due to error. Cf. note to section, and sections end. In section I mentioned explicit definitions whereby the concepts of an axiom system are given a meaning in terms of a system of lower level universality. Changes in these definitions are permissible if useful, but they must be regarded as modifications of the system, which thereafter has to be re-examined as if it were new. As regards undefined universal names, two possibilities must be distinguished. There are some undefined concepts which only appear in statements of the high est level of universality, and whose use is established by the fact that we know in what logical relation other concepts stand to them. They can be eliminated in the course of deduction. An example is energy. There are other undefined concepts which occur in statements of lower levels of universality also, and whose meaning is established by usage, e.g. movement, mass point, position. In connection with these, we shall forbid surreptitious alterations of usage, and otherwise proceed in conformity with our methodological decisions, as before. As to the two remaining points, which concern the competence of the experimenter or theoretician, we shall adopt similar rules. Intersubjectively testable experiments are either to be accepted, or to be rejected in the light of counter-experiments. The bare appeal to logical derivations to be discovered in the future can be disregarded. 21. Logical investigation of falsifiability. Only in the case of systems which would be falsifiable if treated in accordance with our rules of empirical method is there any need to guard against conventionalist stratagems. Let us assume that we have successfully banned these stratagems by our rules. We may now ask for a logical characterization of such falsifiable systems. We shall attempt to characterize the falsifiability of a theory by the logical relations holding between the theory and the class of basic statements. The character of the singular statements which I call basic statements will be discussed more fully in the next chapter, and also the question whether they, in their turn, are falsifiable. Here we shall assume that falsifiable basic statements exist. It should be borne in mind that when I speak of basic statements, I am not referring to a system of accepted statements. The system of basic statements, as I use the term, is to include, rather, all self-consistent singular statements of a certain logical form, all conceivable singular statements of fact, as it were. Thus the system of all basic statements will contain many statements which are mutually incompatible. As a RST attempt, one might perhaps try calling a theory empirical whenever singular statements can be deduced from it. This attempt fails, however, because in order to deduce singular statements from a theory, we always need other singular statements, the initial conditions that tell us what to substitute for the variables in the theory. As a second attempt, one might try calling a theory empirical if singular statements are derivable with the help of other singular statements serving as initial conditions. But this will not do either, for even a non-empirical theory, for example a tautological one, would allow us to derive some singular statements from other singular statements. According to the rules of logic, we can for example say, from the conjunction of twice 2 is 4 and here is a black raven, there follows, among other things, here is a raven. It would not even be enough to demand that from the theory together with some initial conditions we should be able to deduce more than we could deduce from those initial conditions alone. This demand would indeed exclude tautological theories, but it would not exclude synthetic metaphysical statements. For example, from every occurrence has a cause. And a catastrophe is occurring here, we can deduce this catastrophe has a cause. In this way we are led to the demand that the theory should allow us to deduce, roughly speaking, more empirical singular statements than we can deduce from the initial conditions alone. This means that we must base our definition upon a particular class of singular statements, and this is the purpose for which we need the basic statements. Seeing that it would not be very easy to say in detail how a complicated theoretical system helps in the deduction of singular or basic statements, I propose the following definition. A theory is to be called empirical or falsifiable if it divides the class of all possible basic statements unambiguously into the following two non-empty subclasses. First, the class of all those basic statements with which it is inconsistent, or which it rules out, or prohibits. We call this the class of the potential falsifiers of the theory, and secondly, the class of those basic statements which it does not contradict, or which it permits. We can put this more brief by saying, a theory is falsifiable if the class of its potential falsifiers is not empty. It may be added that a theory makes assertions only about its potential falsifiers. It asserts their falsity. About the permitted basic statements it says nothing. In particular, it does not say that they are true. 22. Falsifiability and falsification. We must clearly distinguish between falsifiability and falsification. We have introduced falsifiability solely as a criterion for the empirical character of a system of statements. As to falsification, special rules must be introduced which will determine under what conditions a system is to be regarded as falsified. We say that a theory is falsified only if we have accepted basic statements which contradict it, cf. section, rule. This condition is necessary, but not sufficient, for we have seen that non-reproducible single occurrences are of no significance to science. Thus a few stray basic statements contradicting a theory will hardly induce us to reject it as falsified. We shall take it as falsified only if we discover a reproducible ict which refutes the theory. In other words, we only accept the falsification if a low-level empirical hypothesis which describes such an ict is proposed and corroborated. This kind of hypothesis may be called a falsifying hypothesis. The requirement that the falsifying hypothesis must be empirical, and so falsifiable, only means that it must stand in a certain logical relationship to possible basic statements, thus this requirement only concerns the logical form of the hypothesis. The writer that the hypothesis should be corroborated refers to tests which it ought to have passed, tests which confront it with accepted basic statements. Thus the basic statements play two different roles. On the one hand, we have used the system of all logically possible basic statements in order to obtain with its help the logical characterization for which we were looking, that of the form of empirical statements. On the other hand, the accepted basic statements are the basis for the corroboration of hypotheses. If accepted basic statements contradict a theory, then we take them as providing sufficient grounds for its falsification only if they corroborate a falsifying hypothesis at the same time. 23 Occurrences and events. The requirement of falsifiability, which was a little vague to start with, has now been split into two parts. The RST, the methodological postulate, cf. section 0, can hardly be made quite precise. The second, the logical criterion, is quite denied as soon as it is clear which statements are to be called basic, cf. section. This logical criterion has so far been presented, in a somewhat formal manner, as a logical relation between statements, the theory, and the basic statements. Perhaps it will make matters clearer and more intuitive if I now express my criterion in a more realistic language. Although it is equivalent to the formal mode of speech, it may be a little nearer to ordinary usage. In this realistic mode of speech we can say that a singular statement, a basic statement, describes an occurrence. Instead of speaking of basic statements which are ruled out or prohibited by a theory, we can then say that the theory rules out certain possible occurrences, and that it will be falsified if these possible occurrences do in fact occur. The use of this vague expression occurrence is perhaps open to criticism. It has sometimes been said that expressions such as occurrence or event should be banished altogether from epistemological discussion, and that we should not speak of occurrences or non-occurrences, or of the happening of events, but instead of the truth or falsity of statements. I prefer, however, to retain the expression occurrence. It is easy enough to deem its use so that it is unobjectionable. For we may use it in such a way that whenever we speak of an occurrence, we could speak instead of some of the singular statements which correspond to it. When denying occurrence, we may remember the fact that it would be quite natural to say that two singular statements which are logically equivalent, i.e. mutually deducible, describe the same occurrence. This suggests the following definition. Let pk be a singular statement. The subscript k refers to the individual names or coordinates which occur in pk. Then we call the class of all statements which are equivalent to pk the occurrence pk. Thus we shall say that it is an occurrence, for example, that it is now thundering here. And we may regard this occurrence as the class of the statements it is now thundering here, it is thundering in the th district of Vienna on the 0th of June at p.m., and of all other statements equivalent to these. The realistic formulation the statement pk represents the occurrence pk can then be regarded as meaning the same as the somewhat trivial statement the statement pk is an element of the class pk of all statements which are equivalent to it. Similarly, we regard the statement the occurrence pk has occurred, or is occurring, as meaning the same as pk and all statements equivalent to it are true. The purpose of these rules of translation is not to assert that whoever uses, in the realistic mode of speech, the word occurrence is thinking of a class of statements. Their purpose is merely to give an interpretation of the realistic mode of speech which makes intelligible what is meant by saying, for example, that an occurrence pk contradicts a theory. This statement will now simply mean that every statement equivalent to pk contradicts the theory t, and is thus a potential falsifier of it. Another term, event, will now be introduced, to denote what may be typical or universal about an occurrence, or what, in an occurrence, can be described with the help of universal names. Thus we do not understand by an event a complex, or perhaps a protracted, occurrence, whatever ordinary usage may suggest. We deem, let pk, pl, be elements of a class of occurrences which differ only in respect of the individuals, the spatio-temporal positions or regions, involved, then we call this class the event, P. In accordance with this definition, we shall say, for example, of the statement a glass of water has just been upset here that the class of statements which are equivalent to it is an element of the event, upsetting of a glass of water. Speaking of the singular statement pk, which represents an occurrence pk, one may say, in the realistic mode of speech, that this statement asserts the occurrence of the event, p, at the spatio-temporal position k. And we take this to mean the same as the class pk, of the singular statements equivalent to pk, is an element of the event, p. We will now apply this terminology to our problem. We can say of a theory, provided it is falsifiable, that it rules out, or prohibits, not merely one occurrence, but always at least one event. Thus the class of the prohibited basic statements, i.e. of the potential falsifiers of the theory, will always contain, if it is not empty, an unlimited number of basic statements, for a theory does not refer to individuals as such. We may call the singular basic statements which belong to one event homotypic, so as to point to the analogy between equivalent statements describing one occurrence, and homotypic statements describing one, typical, event. We can then say that every non-empty class of potential falsifiers of a theory contains at least one non-empty class of homotypic basic statements. Let us now imagine that the class of all possible basic statements is represented by a circular area. The area of the circle can be regarded as representing something like the totality of all possible worlds of experience, or of all possible empirical worlds. Let us imagine, further, that each event is represented by one of the radii, or more precisely, by a very narrow area or a very narrow sector along one of the radii, and that any two occurrences involving the same coordinates, or individuals, are located at the same distance from the center, and thus on the same concentric circle. Then we can illustrate the postulate of falsifiability by the requirement that for every empirical theory there must be at least one radius, or very narrow sector, in our diagram which the theory forbids. This illustration may prove helpful in the discussion of our various problems, such as that of the metaphysical character of purely existential statements, referred to in section. Clearly, to each of these statements there will belong one event, one radius, such that the various basic statements belonging to this event will each verify the purely existential statement. Nevertheless, the class of its potential falsifiers is empty, so from the existential statement nothing follows about the possible worlds of experience. It excludes or forbids none of the radii. The fact that, conversely, from every basic statement a purely existential statement follows, cannot be used as an argument in support of the latter's empirical character. For every tautology also follows from every basic statement, since it follows from any statement whatsoever. At this point I may perhaps say a word about self-contradictory statements. Whilst tautologies, purely existential statements and other non-falsifiable statements assert, as it were, too little about the class of possible basic statements, self-contradictory statements assert too much. From a self-contradictory statement, any statement whatsoever can be validly deduced. Consequently, the class of its potential falsifiers is identical with that of all possible basic statements. It is falsified by any statement whatsoever. One could perhaps say that this fact illustrates an advantage of our method, i.e. of our way of considering possible falsifiers rather than possible verifiers. For if one could verify a statement by the verification of its logical consequences, or merely make it probable in this way, then one would expect that, by the acceptance of any basic statement whatsoever, any self-contradictory statements would become confirmed, or verid, or at least probable. 24. Falsifiability and consistency. The requirement of consistency plays a special role among the various requirements which a theoretical system, or an axiomatic system, must satisfy. It can be regarded as the RST of the requirements to be satisfied by every theoretical system, be it empirical or non-empirical. In order to show the fundamental importance of this requirement, it is not enough to mention the obvious fact that a self-contradictory system must be rejected because it is false. We frequently work with statements which, although actually false, nevertheless yield results which are adequate for certain purposes. An example is Nernst's approximation for the equilibrium equation of gases. But the importance of the requirement of consistency will be appreciated if one realizes that a self-contradictory system is uninformative. It is so because any conclusion we please can be derived from it. Thus no statement is singled out, either as incompatible or as derivable, since all are derivable. A consistent system, on the other hand, divides the set of all possible statements into two, those which it contradicts and those with which it is compatible. Among the latter are the conclusions which can be derived from it. This is why consistency is the most general requirement for a system, whether empirical or non-empirical, if it is to be of any use at all. Besides being consistent, an empirical system should satisfy a further condition: it must be falsifiable. The two conditions are to a large extent analogous. Statements which do not satisfy the condition of consistency fail to differentiate between any two statements within the totality of all possible statements. Statements which do not satisfy the condition of falsifiability fail to differentiate between any two statements within the totality of all possible empirical basic statements. The problem of the empirical basis. We have now reduced the question of the falsifiability of theories to that of the falsifiability of those singular statements which I have called basic statements. But what kind of singular statements are these basic statements? How can they be falsified? To the practical research worker, these questions may be of little concern. But the obscurities and misunderstandings which surround the problem make it advisable to discuss it here in some detail. 25 Perceptual experiences as empirical basis, psychologism. The doctrine that the empirical sciences are reducible to sense perceptions, and thus to our experiences, is one which many accept as obvious beyond all question. However, this doctrine stands or falls with inductive logic, and is here rejected along with it. I do not wish to deny that there is a grain of truth in the view that mathematics and logic are based on thinking, and the factual sciences on sense perceptions. But what is true in this view has little bearing on the epistemological problem. And indeed, there is hardly a problem in epistemology which has swerved more severely from the confusion of psychology with logic than this problem of the basis of statements of experience. The problem of the basis of experience has troubled few thinkers so deeply as Fry's. He taught that, if the statements of science are not to be accepted dogmatically, we must be able to justify them. If we demand justification by reasoned argument, in the logical sense, then we are committed to the view that statements can be justified only by statements. The demand that all statements are to be logically justified, described by Fries as a predilection for proofs, is therefore bound to lead to an innate regress. Now, if we wish to avoid the danger of dogmatism as well as an innate regress, then it seems as if we could only have recourse to psychologism, i.e. the doctrine that statements can be justified not only by statements but also by perceptual experience. Faced with this trilemma, dogmatism versus innate regress versus psychologism, Fries, and with him almost all epistemologists who wished to account for our empirical knowledge, opted for psychologism. In sense experience, he taught, we have immediate knowledge. By this immediate knowledge, we may justify our immediate knowledge expressed in the symbolism of some language. And this mediate knowledge includes, of course, the statements of science. Usually the problem is not explored as far as this. In the epistemologies of sensationalism and positivism, it is taken for granted that empirical scientific statements speak of our experiences. For how could we ever reach any knowledge of facts if not through sense perception? Merely by taking thought a man cannot add an iota to his knowledge of the world of facts. Thus perceptual experience must be the sole source of knowledge of all the empirical sciences. All we know about the world of facts must therefore be expressible in the form of statements about our experiences. Whether this table is red or blue can be found out only by consulting our sense experience. By the immediate feeling of conviction which it conveys, we can distinguish the true statement, the one whose terms agree with experience, from the false statement, whose terms do not agree with it. Science is merely an attempt to classify and describe this perceptual knowledge, these immediate experiences whose truth we cannot doubt. It is the systematic presentation of our immediate convictions. This doctrine founders in my opinion on the problems of induction and of universals. For we can utter no scientific statement that does not go far beyond what can be known with certainty on the basis of immediate experience. This fact may be referred to as the transcendence inherent in any description. Every description uses universal names, or symbols, or ideas. Every statement has the character of a theory, of a hypothesis. The statement, "Here is a glass of water," cannot be varied by any observational experience. The reason is that the universals which appear in it cannot be correlated with any specific sense experience. An immediate experience is only once immediately given, it is unique. By the word glass, for example, we denote physical bodies which exhibit a certain law-like behavior, and the same holds for the word water. Universals cannot be reduced to classes of experiences, they cannot be constituted. 26. Concerning the so-called protocol sentences. The view which I call psychologism, discussed in the previous section, still underlies, it seems to me, a modern theory of the empirical basis, even though its advocates do not speak of experiences or perceptions but, instead, of sentences which represent experiences. These are called protocol sentences by Neurath and by Carnap. A similar theory had been held even earlier by Reininger. His starting point was the question, wherein lies the correspondence or agreement between a statement and the fact or state of affairs which it describes. He came to the conclusion that statements can be compared only with statements. According to his view, the correspondence of a statement with a fact is nothing else than a logical correspondence between statements belonging to different levels of universality. It is the correspondence of higher-level statements with statements which are of similar content, and ultimately with statements recording experiences. These are sometimes called elementary statements by Reininger. Carnap starts with a somewhat different question. His thesis is that all philosophical investigations speak of the forms of speech. The logic of science has to investigate the forms of scientific language. It does not speak of physical objects but of words, not of facts, but of sentences. With this, the correct, the formal mode of speech, Carnap contrasts the ordinary or, as he calls it, the material mode of speech. If confusion is to be avoided, then the material mode of speech should only be used where it is possible to translate it into the correct formal mode of speech. Now this view with which I can agree leads Carnap, like Reininger, to assert that we must not say, in the logic of science, that sentences are tested by comparing them with states of affairs or with experiences. We may only say that they can be tested by comparing them with other sentences. Yet Carnap is nevertheless really retaining the fundamental ideas of the psychologistic approach to the problem. All that he is doing is to translate them into the formal mode of speech. He says that the sentences of science are tested with the help of proto-col sentences, but since these are explained as statements or sentences which are not in need of confirmation but serve as a basis for all the other sentences of science, this amounts to saying in the ordinary material mode of speech that the protocol sentences refer to the given, to the sense data. They describe, as Carnap himself puts it, the contents of immediate experience, or the phenomena, and thus the simplest knowable facts. Which shows clearly enough that the theory of protocol sentences is nothing but psychologism translated into the formal mode of speech. Much the same can be said of Neurath's view. He demands that in protocol sentences such words as perceive, see, etc., should occur together with the full name of the author of the protocol sentence. Protocol sentences, as the term indicates, should be records or protocols of immediate observations, or perceptions. Like Reininger zero Neurath holds that perceptual statements recording experiences, i.e. protocol sentences, are not irrevocable, but that they can sometimes be rejected. He opposes Carnap's view, since revised by the latter, that protocol sentences are ultimate, and not in need of confirmation. But whilst Reininger describes a method of testing his elementary statements, in cases of doubt, by means of other statements, it is the method of deducing and testing conclusions. Neurath gives no such method. He only remarks that we can either delete a protocol sentence which contradicts a system, or else accept it, and modify the system in such a way that, with the sentence added, it remains consistent. Neurath's view that protocol sentences are not inviolable represents, in my opinion, a notable advance. But apart from the replacement of perceptions by perception statements, merely a translation into the formal mode of speech, the doctrine that protocol sentences may be revised is his only advance upon the theory, due to Fries, of the immediacy of perceptual knowledge. It is a step in the right direction, but it leads nowhere if it is not followed up by another step. We need a set of rules to limit the arbitrariness of deleting, or else accepting, a protocol sentence. Neurath fails to give any such rules and thus unwittingly throws empiricism overboard. For without such rules, empirical statements are no longer distinguished from any other sort of statements. Every system becomes defensible if one is allowed, as every body is, in Neurath's view, simply to delete a protocol sentence if it is inconvenient. In this way one could not only rescue any system, in the manner of conventionalism, but given a good supply of protocol sentences, one could even confirm it, by the testimony of witnesses who have tested, or protocolled, what they have seen and heard. Neurath avoids one form of dogmatism, yet he paves the way for any arbitrary system to set itself up as empirical science. Thus it is not quite easy to see what part the protocol sentences are supposed to play in Neurath's scheme. In Carnap's earlier view, the system of protocol sentences was the touchstone by which every assertion of an empirical science had to be judged. This is why they had to be irrefutable. For they alone could overthrow sentences other than protocol sentences, of course. But if they are deprived of this function, and if they themselves can be overthrown by theories, what are they for? Since Neurath does not try to solve the problem of demarcation, it seems that his idea of protocol sentences is merely a relic, a surviving memorial of the traditional view that empirical science starts from perception. 27. The objectivity of the empirical basis. I propose to look at science in a way which is slightly different from that favored by the various psychologistic schools. I wish to distinguish sharply between objective science on the one hand, and our knowledge on the other. I readily admit that only observation can give us knowledge concerning facts, and that we can, as Hahn says, become aware of facts only by observation. But this awareness, this knowledge of ours, does not justify or establish the truth of any statement. I do not believe, therefore, that the question which epistemology must ask is, on what does our knowledge rest, or more exactly, how can I, having had the experience justify my description of it, and defend it against doubt? This will not do, even if we change the term experience into protocol sentence. In my view, what epistemology has to ask is, rather, how do we test scientific statements by their deductive consequences? And what kind of consequences can we select for this purpose if they in their turn are to be intersubjectively testable? By now, this kind of objective and non-psychological approach is pretty generally accepted where logical or tautological statements are concerned. Yet not so long ago it was held that logic was a science dealing with mental processes and their laws, the laws of our thought. On this view there was no other justification to be found for logic than the alleged fact that we just could not think in any other way. A logical inference seemed to be justified because it was experienced as a necessity of thought, as a feeling of being compelled to think along certain lines. In the eld of logic, this kind of psychologism is now perhaps a thing of the past. Nobody would dream of justifying the validity of a logical inference, or of defending it against doubts, by writing beside it in the margin the following protocol sentence. Protocol, In checking this chain of inferences today, I experienced an acute feeling of conviction. The position is very different when we come to empirical statements of science. Here everybody believes that these are grounded on experiences such as perceptions, or in the formal mode of speech, on protocol sentences. Most people would see that any attempt to base logical statements on protocol sentences is a case of psychologism. But curiously enough, when it comes to empirical statements, the same kind of thing goes today by the name of physicalism. Yet whether statements of logic are in question or statements of empirical science, I think the answer is the same: our knowledge, which may be described vaguely as a system of dispositions, and which may be of concern to psychology, may be in both cases linked with feelings of belief or of conviction, in the one case, perhaps, with the feeling of being compelled to think in a certain way, in the other with that of perceptual assurance. But all this interests only the psychologist. It does not even touch upon problems like those of the logical connections between scientific statements, which alone interest the epistemologist. There is a widespread belief that the statement "I see that this table here is white," possesses some profound advantage over the statement "this table here is white," from the point of view of epistemology. But from the point of view of evaluating its possible objective tests, the RST statement, "in speaking about me," does not appear more secure than the second statement, which speaks about the table here. There is only one way to make sure of the validity of a chain of logical reasoning. This is to put it in the form in which it is most easily testable. We break it up into many small steps, each easy to check by anybody who has learned the mathematical or logical technique of transforming sentences. If after this anybody still raises doubts, then we can only beg him to point out an error in the steps of the proof, or to think the matter over again. In the case of the empirical sciences, the situation is much the same. Any empirical scientific statement can be presented, by describing experimental arrangements, etc., in such a way that anyone who has learned the relevant technique can test it. If, as a result, he rejects the statement, then it will not satisfy us if he tells us all about his feelings of doubt or about his feelings of conviction as to his perceptions. What he must do is to formulate an assertion which contradicts our own, and give us his instructions for testing it. If he fails to do this, we can only ask him to take another and perhaps a more careful look at our experiment, and think again. An assertion which, owing to its logical form, is not testable can at best operate, within science, as stimulus. It can suggest a problem. In the field of logic and mathematics, this may be exemplified by Fermat's problem, and in the field of natural history, say, by reports about sea serpents. In such cases, science does not say that the reports are unfounded, that Fermat was in error, or that all the records of observed sea serpents are lies. Instead, it suspends judgment. Science can be viewed from various standpoints, not only from that of epistemology. For example, we can look at it as a biological or as a sociological phenomenon. As such, it might be described as a tool, or an instrument, comparable perhaps to some of our industrial machinery. Science may be regarded as a means of production, as the last word in roundabout production. Even from this point of view, science is no more closely connected with our experience than other instruments or means of production. And even if we look at it as gratifying our intellectual needs, its connection with our experiences does not differ in principle from that of any other objective structure. Admittedly, it is not incorrect to say that science is an instrument whose purpose is to predict from immediate or given experiences later experiences, and even as far as possible to control them. But I do not think that this talk about experiences contributes to clarity. It has hardly more point than, say, the not incorrect characterization of an oil derrick by the assertion that its purpose is to give us certain experiences, not oil, but rather the sight and smell of oil, not money, but rather the feeling of having money. 28 Basic Statements. It has already been indicated what role the basic statements play within the epistemological theory I advocate. We need them in order to decide whether a theory is to be called falsifiable, i.e. empirical. Cf. Section And we also need them for the corroboration of falsifying hypotheses, and thus for the falsification of theories. Cf. section. Basic statements must therefore satisfy the following conditions. A. From a universal statement without initial conditions, no basic statement can be deduced. On the other hand, B. A universal statement and a basic statement can contradict each other. Condition, B, can only be satisfied if it is possible to derive the negation of a basic statement from the theory which it contradicts. From this end condition, A, it follows that a basic statement must have a logical form such that its negation cannot be a basic statement in its turn. We have already encountered statements whose logical form is different from that of their negations. These were universal statements and existential statements. They are negations of one another, and they differ in their logical form. Singular statements can be constructed in an analogous way. The statement, "There is a raven in the space-time region K," may be said to be different in its logical form and not only in its linguistic form from the statement, "There is no raven in the space-time region K." A statement of the form, "There is a so and so in the region K," or "such and such an event is occurring in the region K," cf. section, may be called a singular existential statement or a singular "there is" statement. And the statement which results from negating it, i.e. "There is no so and so in the region K," or "no event of such and such a kind is occurring in the region K," may be called a singular non-existence statement, or a singular "there is not" statement. We may now lay down the following rule concerning basic statements. Basic statements have the form of singular existential statements. This rule means that basic statements will satisfy condition, A, since a singular existential statement can never be deduced from a strictly universal statement, i.e. from a strict non-existence statement. They will also satisfy condition, B, as can be seen from the fact that from every singular existential statement a purely existential statement can be derived simply by omitting any reference to any individual space-time region, and as we have seen, a purely existential statement may indeed contradict a theory. It should be noticed that the conjunction of two basic statements, P and R, which do not contradict each other, is in turn a basic statement. Sometimes we may even obtain a basic statement by joining one basic statement to another statement which is not basic. For example, we may form the conjunction of the basic statement, R, "There is a pointer at the place K," with the singular non-existence statement P, "There is no pointer in motion at the place K." For clearly, the conjunction RP, Rn non-P, of the two statements is equivalent to the singular existential statement, "There is a pointer at rest at the place K." This has the consequence that, if we are given a theory T and the initial conditions R, from which we deduce the prediction P, then the statement RP will be a falsifier of the theory, and so a basic statement. On the other hand, the conditional statement R registered trademark P, i.e. if R then P, is no more basic than the negation P, since it is equivalent to the negation of a basic statement, viz. To the negation of RP. These are the formal requirements for basic statements. They are satisfied by all singular existential statements. In addition to these, a basic statement must also satisfy a material requirement, a requirement concerning the event which, as the basic statement tells us, is occurring at the place K. This event must be an observable event, that is to say, basic statements must be testable, intersubjectively, by observation. Since they are singular statements, this requirement can of course only refer to observers who are suitably placed in space and time, a point which I shall not elaborate. No doubt it will now seem as though in demanding observability, I have, after all, allowed psychologism to slip back quietly into my theory. But this is not so. Admittedly, it is possible to interpret the concept of an observable event in a psychologistic sense. But I am using it in such a sense that it might just as well be replaced by an event involving position and movement of macroscopic physical bodies. Or we might lay it down, more precisely, that every basic statement must either be itself a statement about relative positions of physical bodies, or that it must be equivalent to some basic statement of this mechanistic or materialistic kind. That this stipulation is practicable is connected with the fact that a theory which is intersubjectively testable will also be intersensually testable. This is to say that tests involving the perception of one of our senses can, in principle, be replaced by tests involving other senses. Thus the charge that, in appealing to observability, I have stealthily readmitted psychologism would have no more force than the charge that I have admitted mechanism or materialism. This shows that my theory is really quite neutral and that neither of these labels should be pinned to it. I say all this only so as to save the term observable, as I use it, from the stigma of psychologism. Observations and perceptions may be psychological, but observability is not. I have no intention of denning the term observable or observable event, though I am quite ready to elucidate it by means of either psychologistic or mechanistic examples. I think that it should be introduced as an undine term which becomes sufficiently precise in use, as a primitive concept whose use the epistemologist has to learn, much as he has to learn the use of the term symbol, or as the physicist has to learn the use of the term mass point. Basic statements are therefore in the material mode of speech statements asserting that an observable event is occurring in a certain individual region of space and time. The various terms used in this definition, with the exception of the primitive term observable, have been explained more precisely in section. Observable is undined, but can also be explained fairly precisely, as we have seen here. 29. The relativity of basic statements. Resolution of Frey's trilemma. Every test of a theory, whether resulting in its corroboration or falsification, must stop at some basic statement or other which we decide to accept. If we do not come to any decision, and do not accept some basic statement or other, then the test will have led nowhere. But considered from a logical point of view, the situation is never such that it compels us to stop at this particular basic statement rather than at that, or else give up the test altogether. For any basic statement can again in its turn be subjected to tests, using as a touchstone any of the basic statements which can be deduced from it with the help of some theory, either the one under test, or another. This procedure has no natural end. Thus if the test is to lead us anywhere, nothing remains but to stop at some point or other and say that we are satisfied, for the time being. It is fairly easy to see that we arrive in this way at a procedure according to which we stop only at a kind of statement that is especially easy to test. For it means that we are stopping at statements about whose acceptance or rejection the various investigators are likely to reach agreement. And if they do not agree, they will simply continue with the tests, or else start them all over again. If this too leads to no result, then we might say that the statements in question were not intersubjectively testable, or that we were not, after all, dealing with observable events. If someday it should no longer be possible for scientific observers to reach agreement about basic statements, this would amount to a failure of language as a means of universal communication. It would amount to a new Babel of tongues. Scientific discovery would be reduced to absurdity. In this new Babel, the soaring edifice of science would soon lie in ruins. Just as a logical proof has reached a satisfactory shape when the occult work is over, and everything can be easily checked, so, after science has done its work of deduction or explanation, we stop at basic statements which are easily testable. Statements about personal experiences, i.e. protocol sentences, are clearly not of this kind. Thus they will not be very suitable to serve as statements at which we stop. We do of course make use of records or protocols, such as certificates of tests issued by a department of scientific and industrial research. These, if the need arises, can be re-examined. Thus it may become necessary, for example, to test the reaction times of the experts who carry out the tests, i.e. to determine their personal equations. But in general, and especially in critical cases, we do stop at easily testable statements, and not, as Carnap recommends, at perception or protocol sentences, i.e. we do not stop just at these because the intersubjective testing of statements about perceptions is relatively complicated and occult. What is our position now in regard to Frey's trilemma, the choice between dogmatism, innate regress, and psychologism? Cf. section. The basic statements at which we stop, which we decide to accept as satisfactory, and as scientifically tested, have admittedly the character of dogmas, but only in so far as we may desist from justifying them by further arguments, or by further tests. But this kind of dogmatism is innocuous since, should the need arise, these statements can easily be tested further. I admit that this too makes the chain of deduction in principle innate. But this kind of innate regress is also innocuous since in our theory there is no question of trying to prove any statements by means of it. And nally, as to psychologism, I admit, again, that the decision to accept a basic statement, and to be satisfied with it, is causally connected with our experiences, especially with our perceptual experiences. But we do not attempt to justify basic statements by these experiences. Experiences can motivate a decision, and hence an acceptance or a rejection of a statement, but a basic statement cannot be justified by them no more than by thumping the table. 30. Theory and experiment. Basic statements are accepted as the result of a decision or agreement, and to that extent they are conventions. The decisions are reached in accordance with a procedure governed by rules. Of special importance among these is a rule which tells us that we should not accept stray basic statements, i.e. logically disconnected ones, but that we should accept basic statements in the course of testing theories, of raising searching questions about these theories, to be answered by the acceptance of basic statements. Thus the real situation is quite different from the one visualized by the naive empiricist, or the believer in inductive logic. He thinks that we begin by collecting and arranging our experiences, and so ascend the ladder of science. Or, to use the more formal mode of speech, that if we wish to build up a science, we have RST to collect protocol sentences. But if I am ordered, record what you are now experiencing, I shall hardly know how to obey this ambiguous order. Am I to report that I am writing, that I hear a bell ringing, a newsboy shouting, a loudspeaker droning, or am I to report, perhaps, that these noises irritate me? And even if the order could be obeyed, however rich a collection of statements might be assembled in this way, it could never add up to a science. A science needs points of view, and theoretical problems. Agreement upon the acceptance or rejection of basic statements is reached, as a rule, on the occasion of applying a theory. The agreement, in fact, is part of an application which puts the theory to the test. Coming to an agreement upon basic statements is, like other kinds of applications, to perform a purposeful action, guided by various theoretical considerations. We are now, I think, in a position to solve such problems as, for instance, Whitehead's problem of how it is that the tactile breakfast should always be served along with the visual breakfast, and the tactile times with the visible and the audibly rustling times. The inductive logician who believes that all science starts from stray elementary perceptions must be puzzled by such regular coincidences, they must seem to him entirely accidental. He is prevented from explaining regularity by theories, because he is committed to the view that theories are nothing but statements of regular coincidences. But according to the position reached here, the connections between our various experiences are explicable, and deducible, in terms of theories which we are engaged in testing. Our theories do not lead us to expect that along with the visible moon we shall be served a tactile moon, nor do we expect to be bothered by an auditory nightmare. One question, certainly, does remain, a question which obviously cannot be answered by any falsifiable theory and which is therefore metaphysical. How is it that we are so often lucky in the theories we construct? How is it that there are natural laws? All these considerations are important for the epistemological theory of experiment. The theoretician puts certain finite questions to the experimenter, and the latter, by his experiments, tries to elicit a decisive answer to these questions, and to no others. All other questions he tries hard to exclude. Here the relative independence of subsystems of a theory may be important. Thus he makes his test with respect to this one question as sensitive as possible, but as insensitive as possible with respect to all other associated questions. Part of this work consists in screening all possible sources of error. but it is a mistake to suppose that the experimenter proceeds in this way in order to lighten the task of the theoretician, or perhaps in order to furnish the theoretician with a basis for inductive generalizations. On the contrary, the theoretician must long before have done his work, or at least what is the most important part of his work, he must have formulated his question as sharply as possible. Thus it is he who shows the experimenter the way. But even the experimenter is not in the main engaged in making exact observations. His work, too, is largely of a theoretical kind. Theory dominates the experimental work from its initial planning up to the finishing touches in the laboratory. This is well illustrated by cases in which the theoretician succeeded in predicting an observable effect which was later experimentally produced. Perhaps the most beautiful instance is de Broglie's prediction of the wave character of matter, RST confirmed experimentally by Davison and Germer. It is illustrated perhaps even better by cases in which experiments had a conspicuous influence upon the progress of theory. What compels the theorist to search for a better theory, in these cases, is almost always the experimental falsification of a theory, so far accepted and corroborated. It is, again, the outcome of tests guided by theory. Famous examples are the Michelson-Morley experiment which led to the theory of relativity, and the falsification, by Lumiere and Pringsheim, of the radiation formula of Rayleigh and Jeans, and of that of Wien, which led to the quantum theory. Accidental discoveries occur too, of course, but they are comparatively rare. Mach rightly speaks in such cases of a correction of scientific opinions by accidental circumstances, thus acknowledging the significance of theories in spite of himself. It may now be possible for us to answer the question, how and why do we accept one theory in preference to others? The preference is certainly not due to anything like a experiential justification of the statements composing the theory. It is not due to a logical reduction of the theory to experience. We choose the theory which best holds its own in competition with other theories, the one which, by natural selection, proves itself the test to survive. This will be the one which not only has hitherto stood up to the severest tests, but the one which is also testable in the most rigorous way. A theory is a tool which we test by applying it, and which we judge as to its fitness by the results of its applications. From a logical point of view, the testing of a theory depends upon basic statements whose acceptance or rejection, in its turn, depends upon our decisions. Thus it is decisions which settle the fate of theories. To this extent my answer to the question, how do we select a theory, resembles that given by the conventionalist, and like him I say that this choice is in part determined by considerations of utility. But in spite of this, there is a vast difference between my views and his. For I hold that what characterizes the empirical method is just this, that the convention or decision does not immediately determine our acceptance of universal statements but that, on the contrary, it enters into our acceptance of the singular statements, that is, the basic statements. For the conventionalist, the acceptance of universal statements is governed by his principle of simplicity. He selects that system which is the simplest. I, by contrast, propose that the RST thing to be taken into account should be the severity of tests. There is a close connection between what I call simplicity and the severity of tests, yet my idea of simplicity differs widely from that of the conventionalist, see section. And I hold that what ultimately decides the fate of a theory is the result of a test, i.e. an agreement about basic statements. With the conventionalist I hold that the choice of any particular theory is an act, a practical matter. But for me the choice is decisively influenced by the application of the theory and the acceptance of the basic statements in connection with this application, whereas for the conventionalist, aesthetic motives are decisive. Thus I differ from the conventionalist in holding that the statements decided by agreement are not universal but singular. And I differ from the positivist in holding that basic statements are not judgeable by our immediate experiences, but are, from the logical point of view, accepted by an act, by a free decision. From the psychological point of view this may perhaps be a purposeful and well-adapted reaction. This important distinction, between a justification and a decision reached in accordance with a procedure governed by rules might be clarified, perhaps, with the help of an analogy, the old procedure of trial by jury. The verdict of the jury, vir dictum equals spoken truly, like that of the experimenter, is an answer to a question of fact, quid facti, which must be put to the jury in the sharpest, the most denied form. But what question is asked, and how it is put, will depend very largely on the legal situation, i.e. on the prevailing system of criminal law, corresponding to a system of theories. By its decision, the jury accepts, by agreement, a statement about a factual occurrence, a basic statement, as it were. The significance of this decision lies in the fact that from it, together with the universal statements of the system of criminal law, certain consequences can be deduced. In other words, the decision forms the basis for the application of the system, the verdict plays the part of a true statement of fact. But it is clear that the statement need not be true merely because the jury has accepted it. This fact is acknowledged in the rule allowing a verdict to be quashed or revised. The verdict is reached in accordance with a procedure which is governed by rules. These rules are based on certain fundamental principles which are chiefly, if not solely, designed to result in the discovery of objective truth. They sometimes leave room not only for subjective convictions but even for subjective bias. Yet even if we disregard these special aspects of the older procedure and imagine a procedure based solely on the aim of promoting the discovery of objective truth, it would still be the case that the verdict of the jury never justifies, or gives grounds for, the truth of what it asserts. Neither can the subjective convictions of the jurors be held to justify the decision reached, although there is, of course, a close causal connection between them and the decision reached, a connection which might be stated by psychological laws. Thus these convictions may be called the motives of the decision. The fact that the convictions are not justifications is connected with the fact that different rules may regulate the jury's procedure, for example, simple or qualied major ity. This shows that the relationship between the convictions of the jurors and their verdict may vary greatly. In contrast to the verdict of the jury, the judgment of the judge is reasoned, it needs, and contains, a justification. The judge tries to justify it by, or deduce it logically from, other statements, the statements of the legal system, combined with the verdict that plays the role of initial conditions. This is why the judgment may be challenged on logical grounds. The jury's decision, on the other hand, can only be challenged by questioning whether it has been reached in accordance with the accepted rules of procedure, i.e. formally, but not as to its content. A justification of the content of a decision is significantly called a motivated report, rather than a logically justified report. The analogy between this procedure and that by which we decide basic statements is clear. It throws light, for example, upon their relative ity, and the way in which they depend upon questions raised by the theory. In the case of the trial by jury, it would be clearly impossible to apply the theory unless there is a verdict arrived at by decision, yet the verdict has to be found in a procedure that conforms to, and thus applies, part of the general legal code. The case is analogous to that of basic statements. Their acceptance is part of the application of a theoretical system, and it is only this application which makes any further applications of the theoretical system possible. The empirical basis of objective science has thus nothing absolute about it. Science does not rest upon solid bedrock. The bold structure of its theories rises, as it were, above a swamp. It is like a building erected on piles. The piles are driven down from above into the swamp, but not down to any natural or given base, and if we stop driving the piles deeper, it is not because we have reached RM ground. We simply stop when we are satisfied that the piles are RM enough to carry the structure, at least for the time being. Addendum 1. My term basis has ironical overtones, it is a basis that is not RM. 2. I assume a realist and objectivist point of view, I try to replace perception as basis by critical testing. Our observational experiences are never beyond being tested, and they are impregnated with theories. Basic statements are test statements, they are, like all language, impregnated with theories. Even a phenomenal language permitting statements like now here read would be impregnated with theories about time, space, and color. Degrees of testability. Theories may be more, or less, severely testable, that is to say, more, or less, easily falsifiable. The degree of their testability is of significance for the selection of theories. In this chapter, I shall compare the various degrees of testability or falsifiability of theories through comparing the classes of their potential falsifiers. This investigation is quite independent of the question whether or not it is possible to distinguish in an absolute sense between falsifiable and non-falsifiable theories. Indeed, one might say of the present chapter that it relativizes the requirement of falsifiability by showing falsifiability to be a matter of degree. 31. A program and an illustration. A theory is falsifiable, as we saw in section, if there exists at least one non-empty class of homotypic basic statements which are forbidden by it, that is, if the class of its potential falsifiers is not empty. If, as in section, we represent the class of all possible basic statements by a circular area, and the possible events by the radii of the circle, then we can say, at least one radius or perhaps better, one narrow sector whose width may represent the fact that the event is to be observable must be incompatible with the theory and ruled out by it. One might then represent the potential falsifiers of various theories by sectors of various widths. And according to the greater and lesser width of the sectors ruled out by them, theories might then be said to have more, or fewer, potential falsifiers. The question whether this more or fewer could be made at all precise will be left open for the moment. It might then be said, further, that if the class of potential falsifiers of one theory is larger than that of another, there will be more opportunities for the RST theory to be refuted by experience. Thus, compared with the second theory, the RST theory may be said to be falsifiable in a higher degree. This also means that the RST theory says more about the world of experience than the second theory, for it rules out a larger class of basic statements. Although the class of permitted statements will thereby become smaller, this does not eat our argument, for we have seen that the theory does not assert anything about this class. Thus it can be said that the amount of empirical information conveyed by a theory, or its empirical content, increases with its degree of falsifiability. Let us now imagine that we are given a theory, and that the sector representing the basic statements which it forbids becomes wider and wider. Ultimately, the basic statements not forbidden by the theory will be represented by a narrow remaining sector. If the theory is to be consistent, then some such sector must remain. A theory like this would obviously be very easy to falsify, since it allows the empirical world only a narrow range of possibilities, for it rules out almost all conceivable, i.e. logically possible, events. It asserts so much about the world of experience, its empirical content is so great, that there is, as it were, little chance for it to escape falsification. Now theoretical science aims, precisely, at obtaining theories which are easily falsifiable in this sense. It aims at restricting the range of permitted events to a minimum, and, if this can be done at all, to such a degree that any further restriction would lead to an actual empirical falsification of the theory. If we could be successful in obtaining a theory such as this, then this theory would describe our particular world as precisely as a theory can, for it would single out the world of our experience from the class of all logically possible worlds of experience with the greatest precision attainable by theoretical science. All the events or classes of occurrences which we actually encounter and observe, and only these, would be characterized as permitted. 32. How are classes of potential falsifiers to be compared? The classes of potential falsifiers are innate classes. The intuitive more and fewer which can be applied without special safeguards to innate classes cannot similarly be applied to innate classes. We cannot easily get round this difficulty, not even if, instead of the forbidden basic statements or occurrences, we consider, for the purpose of comparison, classes of forbidden events, in order to ascertain which of them contains more forbidden events. For the number of events forbidden by an empirical theory is also innate, as may be seen from the fact that the conjunction of a forbidden event with any other event, whether forbidden or not, is again a forbidden event. I shall consider three ways of giving a precise meaning, even in the case of innate classes, to the intuitive more or fewer, in order to end out whether any of them may be used for the purpose of comparing classes of forbidden events. 1. The concept of the cardinality, or power, of a class. This concept cannot help us to solve our problem, since it can easily be shown that the classes of potential falsiers have the same cardinal number for all theories. 2. The concept of dimension. The vague intuitive idea that a cube in some way contains more points than, say, a straight line can be clearly formulated in logically unexceptionable terms by the set theoretical concept of dimension. This distinguishes classes or sets of points according to the wealth of the neighborhood relations between their elements. Sets of higher dimension have more abundant neighborhood relations. The concept of dimension, which allows us to compare classes of higher and lower dimension, will be used here to tackle the problem of comparing degrees of testability. This is possible because basic statements, combined by conjunction with other basic statements, again yield basic statements which, however, are more highly composite than their components, and this degree of composition of basic statements may be linked with the concept of dimension. However, it is not the compositions of the forbidden events but that of the permitted ones which will have to be used. The reason is that the events forbidden by a theory can be of any degree of composition. On the other hand, some of the permitted statements are permitted merely because of their form or, more precisely, because their degree of composition is too low to enable them to contradict the theory in question, and this fact can be used for comparing dimensions. 3. The subclass relation. Let all elements of a class alpha be also elements of a class beta, so that alpha is a subclass of beta, in symbols, alpha I beta. Then either all elements of beta are in their turn also elements of alpha, in which case the two classes are said to have the same extension, or to be identical, or there are elements of beta which do not belong to alpha. In the latter case the elements of beta which do not belong to alpha form the diarence class or the complement of alpha with respect to beta, and alpha is a proper subclass of beta. The subclass relation corresponds very well to the intuitive more and fewer, but it suffers from the disadvantage that this relation can only be used to compare the two classes if one includes the other. If therefore two classes of potential falsiers intersect, without one being included in the other, or if they have no common elements, then the degree of falsiability of the corresponding theories cannot be compared with the help of the subclass relation. They are non-comparable with respect to this relation. 33 degrees of falsifiability compared by means of the subclass relation. The following definitions are introduced provisionally, to be improved later in the course of our discussion of the dimensions of theories. 1. A statement X is said to be falsiable in a higher degree or better testable than a statement Y, or in symbols, FSB, X, FSB, Y, if and only if the class of potential falsiers of X includes the class of the potential falsiers of Y as a proper subclass. 2. If the classes of potential falsiers of the two statements X and Y are identical, then they have the same degree of falsiability, i.e. FSB, X, equals FSB, Y. 3. If neither of the classes of potential falsiers of the two statements includes the other as a proper subclass, then the two statements have non-comparable degrees of falsiability, FSB, X, FSB, Y. If, applies, there will always be a non-empty complement class. In the case of universal statements, this complement class must be innate. It is not possible, therefore, for the two, strictly universal, theories to differ in that one of them forbids a finite number of single occurrences permitted by the other. The classes of potential falsiers of all tautological and metaphysical statements are empty. In accordance with, they are, therefore, identical. For empty classes are subclasses of all classes, and hence also of empty classes, so that all empty classes are identical, which may be expressed by saying that there exists only one empty class. If we denote an empirical statement by E, and a tautology or a metaphysical statement, e.g. a purely existential statement, by T or M respectively, then we may ascribe to tautological and metaphysical statements a zero degree of falsiability, and we can write FSB T equals FSB M equals 0, and FSB E 0. A self-contradictory statement, which we may denote by C, may be said to have the class of all logically possible basic statements as its class of potential falsiers. This means that any statements whatsoever is comparable with a self-contradictory statement as to its degree of falsiability. We have FSB, C, FSB, E, 0. If we arbitrarily put FSB, C, equals, i.e. arbitrarily assign the number to the degree of falsiability of a self-contradictory statement, then we may even deem an empirical statement E by the condition FSB, E, 0. In accordance with this formula, FSB, E, always falls within the interval between 0 and, excluding these limits, i.e. within the open interval bounded by these numbers. By excluding contradiction and tautology, as well as metaphysical statements, the formula expresses at the same time both the requirement of consistency and that of falsiability. 34. The structure of the subclass relation. Logical probability. We have done the comparison of the degree of falsiability of two statements with the help of the subclass relation. It therefore shares all the structural properties of the latter. The question of comparability can be elucidated with the help of a diagram, G, in which certain subclass relations are depicted on the left, and the corresponding testability relations on the right. The Arabic numerals on the right correspond to the Roman numerals on the left in such a way that a given Roman numeral denotes the class of the potential falsiers of that statement, which is denoted by the corresponding Arabic numeral. The arrows in the diagram showing the degrees of testability run from the better testable or better falsiable statements to those which are not so well testable. They therefore correspond fairly precisely to derivability arrows, see section. It will be seen from the diagram that various sequences of subclasses can be distinguished and traced, for example the sequence I24 or I3V, and that these could be made more dense by introducing new intermediate classes. All these sequences begin in this particular case with and end with the empty class, since the latter is included in every class. The empty class cannot be depicted in our diagram on the left, just because it is a subclass of every class and would therefore have to appear, so to speak, everywhere. If we choose to identify class with the class of all possible basic statements, then becomes the contradiction, C, and 0, corresponding to the empty class, may then denote the tautology, T. It is possible to pass from to the empty class, or from, C, to, T, by various paths. Some of these, as can be seen from the right-hand diagram, may cross one another. We may therefore say that the structure of the relation is that of a lattice of sequences ordered by the arrow, or the subclass relation. There are nodal points, e.g. statements and, in which the lattice is partially connected. The relation is totally connected only in the universal class and in the empty class, corresponding to the contradiction C and tautology T. Is it possible to arrange the degrees of falsiability of various statements on one scale, i.e. to correlate, with the various statements, number pairs which order them according to their falsiability? Clearly, we cannot possibly order all statements in this way, for if we did, we should be arbitrarily making the non-comparable statements comparable. There is, however, nothing to prevent us from picking out one of the sequences from the lattice, and indicating the order of its statements by numbers. In so doing we should have to proceed in such a way that a statement which lies nearer to the contradiction C is always given a higher number than one which lies nearer to the tautology T. Since we have already assigned the numbers 0 and to tautology and contradiction respectively, we should have to assign proper fractions to the empirical statements of the selected sequence. I do not really intend, however, to single out one of the sequences. Also, the assignment of numbers to the statements of the sequence would be entirely arbitrary. Nevertheless, the fact that it is possible to assign such fractions is of great interest, especially because of the light it throws upon the connection between degree of falsiability and the idea of probability. Whenever we can compare the degrees of falsiability of two statements, we can say that the one which is the less falsiable is also the more probable, by virtue of its logical form. This probability I call logical probability. It must not be confused with that numerical probability which is employed in the theory of games of chance, and in statistics. The logical probability of a statement is complementary to its degree of falsiability. It increases with decreasing degree of falsiability. The logical probability corresponds to the degree 0 of falsiability, and vice versa. The better testable statement, i.e. the one with the higher degree of falsiability, is the one which is logically less probable, and the statement which is less well testable is the one which is logically more probable. As will be shown in section, numerical probability can be linked with logical probability, and thus with degree of falsiability. It is possible to interpret numerical probability as applying to a subsequence, picked out from the logical probability relation, for which a system of measurement can be deemed, on the basis of frequency estimates. These observations on the comparison of degrees of falsiability do not hold only for universal statements, or for systems of theories, they can be extended so as to apply to singular statements. Thus they hold, for example, for theories in conjunction with initial conditions. In this case the class of potential falsiers must not be mistaken for a class of events for a class of homotypic basic statements since it is a class of occurrences. This remark has some bearing on the connection between logical and numerical probability which will be analyzed in section 35 Empirical content, entailment, and degrees of falsifiability. It was said in section that what I call the empirical content of a statement increases with its degree of falsiability. The more a statement forbids, the more it says about the world of experience. Cf. section. What I call empirical content is closely related to, but not identical with, the concept content as deemed, for instance, by Carnap. For the latter I will use the term logical content, to distinguish it from that of empirical content. I deem the empirical content of a statement P as the class of its potential falsiers, cf. section. The logical content is deemed, with the help of the concept of derivability, as the class of all non-tautological statements which are derivable from the statement in question. It may be called its consequence class. So the logical content of P is at least equal to, i.e. greater than or equal to, that of a statement Q, if Q is derivable from P, or, in symbols, if P registered trademark Q. If the derivability is mutual, in symbols, PQ, then P and Q are said to be of equal content. If Q is derivable from P, but not P from Q, then the consequence class of Q must be a proper subset of the consequence class of P, and P then possesses the larger consequence class, and thereby the greater logical content, or logical force. It is a consequence of my definition of empirical content that the comparison of the logical and of the empirical contents of two statements P and Q leads to the same result if the statements compared contain no metaphysical elements. We shall therefore require the following: a. Two statements of equal logical content must also have equal empirical content. b. A statement P whose logical content is greater than that of a statement Q must also have greater empirical content, or at least equal empirical content, and nally, c. If the empirical content of a statement P is greater than that of a statement Q, then the logical content must be greater or else non-comparable. The qualification in b, or at least equal empirical content had to be added because P might be, for example, a conjunction of Q with some purely existential statement, or with some other kind of metaphysical statement to which we must ascribe a certain logical content, for in this case the empirical content of P will not be greater than that of Q. Corresponding considerations make it necessary to add to C the qualification or else non-comparable. In comparing degrees of testability or of empirical content we shall therefore as a rule, i.e. in the case of purely empirical statements, arrive at the same results as in comparing logical content, or derivability relations. Thus it will be possible to base the comparison of degrees of falsiability to a large extent upon derivability relations. Both relations show the form of lattices which are totally connected in the self-contradiction and in the tautology, cf. section. This may be expressed by saying that a self-contradiction entails every statement and that a tautology is entailed by every statement. Moreover, empirical statements, as we have seen, can be characterized as those whose degree of falsiability falls into the open interval which is bounded by the degrees of falsiability of self-contradictions on the one side, and of tautologies on the other. Similarly, synthetic statements in general, including those which are non-empirical, are placed, by the entailment relation, in the open interval between self-contradiction and tautology. To the positivist thesis that all non-empirical, metaphysical, statements are meaningless, there would thus correspond the thesis that my distinction between empirical and synthetic statements, or between empirical and logical content, is superfluous, for all synthetic statements would have to be empirical, all that are genuine, that is, and not mere pseudo-statements. But this way of using words, though feasible, seems to me more likely to confuse the issue than to clarify it. Thus I regard the comparison of the empirical content of two statements as equivalent to the comparison of their degrees of falsiability. This makes our methodological rule that those theories should be given preference which can be most severely tested, cf. the anti-conventionalist rules in section 0, equivalent to a rule favoring theories with the highest possible empirical content. 36 levels of universality and degrees of precision. There are other methodological demands which may be reduced to the demand for the highest possible empirical content. Two of these are outstanding: the demand for the highest attainable level, or degree, of universality, and the demand for the highest attainable degree of precision. With this in mind, we may examine the following conceivable natural laws. P. All heavenly bodies which move in closed orbits move in circles, or more brie, all orbits of heavenly bodies are circles. Q. All orbits of planets are circles. R. All orbits of heavenly bodies are ellipses. S. All orbits of planets are ellipses. The deducibility relations holding between these four statements are shown by the arrows in our diagram. From P all the others follow, from Q follows S, which also follows from R, so that S follows from all the others. Moving from P to Q, the degree of universality decreases, and Q says less than P because the orbits of planets form a proper subclass of the orbits of heavenly bodies. Consequently, P is more easily falsied than Q. If Q is falsied, so is P, but not vice versa. Moving from P to R, the degree of precision, of the predicate, decreases. Circles are a proper subclass of ellipses, and if R is falsied, so is P, but not vice versa. Corresponding remarks apply to the other moves. Moving from P to S, the degree of both universality and precision decreases, from Q to S precision decreases, and from R to S, universality. To a higher degree of universality or precision corresponds a greater, logical or empirical content, and thus a higher degree of testability. Both universal and singular statements can be written in the form of a universal conditional statement, or a general implication as it is often called. If we put our four laws in this form, then we can perhaps see more easily and accurately how the degrees of universality and the degrees of precision of two statements may be compared. A universal conditional statement, cf. note to section, may be written in the form, x, phi x registered trademark fx, or in words, all values of x which satisfy the statement function phi x also satisfy the statement function fx. The statement S from our diagram yields the following example: x is an orbit of a planet registered trademark x is an ellipse, which means, whatever x may be, if x is an orbit of a planet then x is an ellipse. Let P and Q be two statements written in this normal form, then we can say that P is of greater universality than Q if the antecedent statement function of P, which may be denoted by phi px, is tautologically implied by, or logically deducible from, but not equivalent to, the corresponding statement function of Q, which may be denoted by phi qx, or in other words, if x, phi qx registered trademark phi px, is tautological, or logically true. Similarly, we shall say that P has greater precision than Q if X, FPX registered trademark FQX, is tautological, that is if the predicate, or the consequent statement function, of P is narrower than that of Q, which means that the predicate of P entails that of Q. This definition may be extended to statement functions with more than one variable. Elementary logical transformations lead from it to the derivability relations which we have asserted, and which may be expressed by the following rule: if of two statements both their universality and their precision are comparable, then the less universal or less precise is derivable from the more universal or more precise, unless, of course, the one is more universal and the other more precise, as in the case of Q and R in my diagram. We could now say that our methodological decision, sometimes metaphysically interpreted as the principle of causality, is to leave nothing unexplained, i.e. always to try to deduce statements from others of higher universality. This decision is derived from the demand for the highest attainable degree of universality and precision, and it can be reduced to the demand, or rule, that preference should be given to those theories which can be most severely tested. 37 Logical ranges. Notes on the theory of measurement. If a statement P is more easy to falsify than a statement Q, because it is of a higher level of universality or precision, then the class of the basic statements permitted by P is a proper subclass of the class of the basic statements permitted by Q. The subclass relationship holding between classes of permitted statements is the opposite of that holding between classes of forbidden statements. Potential falsiers, the two relationships may be said to be inverse, or perhaps complementary. The class of basic statements permitted by a statement may be called its range. The range which a statement allows to reality is, as it were, the amount of free play, or the degree of freedom, which it allows to reality. Range and empirical content, cf. section, are converse, or complementary, concepts. Accordingly, the ranges of two statements are related to each other in the same way as are their logical probabilities, cf. sections and. I have introduced the concept of range because it helps us to handle certain questions connected with degree of precision in measurement. Assume that the consequences of two theories differ so little in all fields of application that the very small differences between the calculated observable events cannot be detected, owing to the fact that the degree of precision attainable in our measurements is not sufficiently high. It will then be impossible to decide by experiment between the two theories, without improving our technique of measurement. This shows that the prevailing technique of measurement determines a certain range or region within which discrepancies between the observations are permitted by the theory. Thus the rule that theories should have the highest attainable degree of testability, and thus allow only the narrowest range, entails the demand that the degree of precision in measurement should be raised as much as possible. It is often said that all measurement consists in the determination of coincidences of points. But any such determination can only be correct within limits. There are no coincidences of points in a strict sense. Two physical points, a mark, say, on the measuring rod, and another on a body to be measured, can at best be brought into close proximity. They cannot coincide, that is, coalesce into one point. However trite this remark might be in another context, it is important for the question of precision in measurement. For it reminds us that measurement should be described in the following terms. We nd that the point of the body to be measured lies between two gradations or marks on the measuring rod, or, say, that the pointer of our measuring apparatus lies between two gradations on the scale. We can then either regard these gradations or marks as our two optimal limits of error, or proceed to estimate the position of, say, the pointer within the interval of the gradations, and so obtain a more accurate result. One may describe this latter case by saying that we take the pointer to lie between two imaginary gradation marks. Thus an interval, a range, always remains. It is the custom of physicists to estimate this interval for every measurement. Thus, following Millikan, they give, for example, the elementary charge of the electron, measured in electrostatic units, as E equals 0, 0, adding that the range of imprecision is plus or minus 0.00.00. But this raises a problem. What can be the purpose of replacing, as it were, one mark on a scale by two, to wit, the two bounds of the interval, when for each of these two bounds there must again arise the same question: what are the limits of accuracy for the bounds of the interval? Giving the bounds of the interval is clearly useless unless these two bounds in turn can be exceeded with a degree of precision greatly exceeding what we can hope to attain for the original measurement, exceed, that is, within their own intervals of imprecision, which should thus be smaller, by several orders of magnitude, than the interval they determine for the value of the original measurement. In other words, the bounds of the interval are not sharp bounds but are really very small intervals, the bounds of which are in their turn still much smaller intervals, and so on. In this way we arrive at the idea of what may be called the unsharp bounds or condensation bounds of the interval. These considerations do not presuppose the mathematical theory of errors, nor the theory of probability. It is rather the other way round. By analyzing the idea of a measuring interval they furnish a background without which the statistical theory of errors makes very little sense. If we measure a magnitude many times, we obtain values which are distributed with diarrhent densities over an interval, the interval of precision depending upon the prevailing measuring technique. Only if we know what we are seeking, namely the condensation bounds of this interval, can we apply to these values the theory of errors, and determine the bounds of the interval. Now all this sheds some light, I think, on the superiority of methods that employ measurements over purely qualitative methods. It is true that even in the case of qualitative estimates, such as an estimate of the pitch of a musical sound, it may sometimes be possible to give an interval of accuracy for the estimates, but in the absence of measurements, any such interval can be only very vague, since in such cases the concept of condensation bounds cannot be applied. This concept is applicable only where we can speak of orders of magnitude, and therefore only where methods of measurement are deemed. I shall make further use of the concept of condensation bounds of intervals of precision in connection with the theory of probability. 38 degrees of testability compared by reference to dimensions. Till now we have discussed the comparison of theories with respect to their degrees of testability only in so far as they can be compared with the help of the subclass relation. In some cases this method is quite successful in guiding our choice between theories. Thus we may now say that Pauli's exclusion principle, mentioned by way of example in section 0, indeed turns out to be highly satisfactory as an auxiliary hypothesis. For it greatly increases the degree of precision and, with it, the degree of testability, of the older quantum theory, like the corresponding statement of the new quantum theory, which asserts that anti-symmetrical states are realized by electrons, and symmetrical ones by uncharged, and by certain multiply charged, particles. For many purposes, however, comparison by means of the subclass relation does not suit. Thus Frank, for example, has pointed out that statements of a high level of universality such as the principle of the conservation of energy in Planck's formulation are apt to become tautological, and to lose their empirical content, unless the initial conditions can be determined by few measurements, i.e. by means of a small number of magnitudes characteristic of the state of the system. The question of the number of parameters which have to be ascertained, and to be substituted in the formulae, cannot be elucidated with the help of the subclass relation, in spite of the fact that it is evidently closely connected with the problem of testability and falsiability, and their degrees. The fewer the magnitudes which are needed for determining the initial conditions, the less composite will be the basic statements which sus for the falsification of the theory, for a falsifying basic statement consists of the conjunction of the initial conditions with the negation of the derived prediction, cf. section. Thus it may be possible to compare theories as to their degree of testability by ascertaining the minimum degree of composition which a basic statement must have if it is to be able to contradict the theory, provided always that we can find a way to compare basic statements in order to ascertain whether they are more, or less, composite, i.e. compounds of a greater, or a smaller, number of basic statements of a simpler kind. All basic statements, whatever their content, whose degree of composition does not reach the requisite minimum, would be permitted by the theory simply because of their low degree of composition. But any such program is faced with difficulties. For generally it is not easy to tell, merely by inspecting it, whether a statement is composite, i.e. equivalent to a conjunction of simpler statements. In all statements there occur universal names, and by analyzing these one can often break down the statement into conjunctive components. For example, the statement "there is a glass of water at the place K" might perhaps be analyzed, and broken down into the two statements "there is a glass containing a liquid at the place K" and "there is water at the place K." There is no hope of ending any natural end to the dissection of statements by this method, especially since we can always introduce new universals deemed for the purpose of making a further dissection possible. With a view to rendering comparable the degrees of composition of all basic statements, it might be suggested that we should choose a certain class of statements as the elementary or atomic ones, from which all other statements could then be obtained by conjunction and other logical operations. If successful, we should have deemed in this way an absolute zero of composition, and the composition of any statement could then be expressed, as it were, in absolute degrees of composition. But for the reason given above, such a procedure would have to be regarded as highly unsuitable, for it would impose serious restrictions upon the free use of scientific language. Yet it is still possible to compare the degrees of composition of basic statements, and thereby also those of other statements. This can be done by selecting arbitrarily a class of relatively atomic statements, which we take as a basis for comparison. Such a class of relatively atomic statements can be deemed by means of a generating schema or matrix. For example, there is a measuring apparatus for at the place, the pointer of which lies between the gradation marks and. We can then deem as relatively atomic, and thus as equicomposite, the class of all statements obtained from this kind of matrix, or statement function, by the substitution of finite values. The class of these statements, together with all the conjunctions which can be formed from them, may be called a eld. A conjunction of n-diarent relatively atomic statements of a eld may be called an n-tuple of the eld, and we can say that the degree of its composition is equal to the number n. If there exists, for a theory T, a eld of singular, but not necessarily basic, statements such that, for some number d, the theory T cannot be falsified by any d-tuple of the eld, although it can be falsified by certain d plus tuples, then we call d the characteristic number of the theory with respect to that eld. All statements of the eld whose degree of composition is less than d, or equal to d, are then compatible with the theory, and permitted by it, irrespective of their content. Now it is possible to base the comparison of the degree of testability of theories upon this characteristic number d. But in order to avoid inconsistencies which might arise through the use of diarent elds, it is necessary to use a somewhat narrower concept than that of a eld, namely that of a eld of application. If a theory T is given, we say that a eld is a eld of application of the theory T if there exists a characteristic number d of the theory T with respect to this eld, and if, in addition, it satisfies certain further conditions, which are explained in Appendix I. The characteristic number d of a theory T, with respect to a eld of application, I call the dimension of T with respect to this eld of application. The expression dimension suggests itself because we can think of all possible n-tuples of the eld as spatially arranged, in a congruation space of infinite dimensions. If, for example, d equals, then those statements which are admissible because their composition is too low form a three-dimensional subspace of this congruation. Transition from d equals to d equals corresponds to the transition from a solid to a surface. The smaller the dimension d, the more severely restricted is the class of those permitted statements which, regardless of their content, cannot contradict the theory owing to their low degree of composition, and the higher will be the degree of falsifiability of the theory. The concept of the eld of application has not been restricted to basic statements, but singular statements of all kinds have been allowed to be statements belonging to a eld of application. But by comparing their dimensions with the help of the eld, we can estimate the degree of composition of the basic statements. We assume that to highly composite singular statements there correspond highly composite basic statements. It thus can be assumed that to a theory of higher dimension, there corresponds a class of basic statements of higher dimension, such that all statements of this class are permitted by the theory, irrespective of what they assert. This answers the question of how the two methods of comparing degrees of testability are related, the one by means of the dimension of a theory, and the other by means of the subclass relation. There will be cases in which neither, or only one, of the two methods is application-able. In such cases there is of course no room for conflict between the two methods. But if in a particular case both methods are applicable, then it may conceivably happen that two theories of equal dimensions may yet have different degrees of falsifiability if assessed by the method based upon the subclass relation. In such cases, the verdict of the latter method should be accepted, since it would prove to be the more sensitive method. In all other cases in which both methods are applicable, they must lead to the same result, for it can be shown, with the help of a simple theorem of the theory of dimension, that the dimension of a class must be greater than, or equal to, that of its subclasses. 39. The dimension of a set of curves. Sometimes we can identify what I have called the ELD of application of a theory quite simply with the ELD of its graphic representation, i.e. the area of a graph paper on which we represent the theory by graphs. Each point of this ELD of graphic representation can be taken to correspond to one relatively atomic statement. The dimension of the theory with respect to this ELD, deemed in appendix, is then identical with the dimension of the set of curves corresponding to the theory. I shall discuss these relations with the help of the two statements Q and S of section. Our comparison of dimensions applies to statements with different predicates. The hypothesis Q that all planetary orbits are circles is three-dimensional. For its falsification at least four singular statements of the ELD are necessary, corresponding to 4 points of its graphic representation. The hypothesis S, that all planetary orbits are ellipses, is VE-dimensional, since for its falsification at least 6 singular statements are necessary, corresponding to 6 points of the graph. We saw in section that Q is more easily falsifiable than S, since all circles are ellipses. It was possible to base the comparison on the subclass relation. But the use of dimensions enables us to compare theories which previously we were unable to compare. For example, we can now compare a circle hypothesis with a parabola hypothesis, which is four-dimensional. Each of the words circle, ellipse, parabola denotes a class or set of curves, and each of these sets has the dimension d if d points are necessary and sufficient to single out, or characterize, one particular curve of the set. In algebraic representation, the dimension of the set of curves depends upon the number of parameters whose values we may freely choose. We can therefore say that the number of freely determinable parameters of a set of curves by which a theory is represented is characteristic for the degree of falsifiability, or testability, of that theory. In connection with the statements Q and S in my example, I should like to make some methodological comments on Kepler's discovery of his laws. I do not wish to suggest that the belief in perfection, the heuristic principle that guided Kepler to his discovery, was inspired, consciously or unconsciously, by methodological considerations regarding degrees of falsifiability. But I do believe that Kepler owed his success in part to the fact that the circle hypothesis with which he started was relatively easy to falsify. Had Kepler started with a hypothesis which, owing to its logical form, was not so easily testable as the circle hypothesis, he might well have got no result at all, considering the difficulties of calculations whose very basis was in the air, adrift in the skies, as it were, and moving in a way unknown. The unequivocal negative result which Kepler reached by the falsification of his circle hypothesis was in fact his RST real success. His method had been vindicated sufficiently for him to proceed further, especially since even this RST attempt had already yielded certain approximations. No doubt, Kepler's laws might have been found in another way. But I think it was no mere accident that this was the way which led to success. It corresponds to the method of elimination which is applicable only if the theory is sufficiently easy to falsify, sufficiently precise to be capable of clashing with observational experience. 40. Two ways of reducing the number of dimensions of a set of curves. Quite different sets of curves may have the same dimension. The set of all circles, for example, is three-dimensional, but the set of all circles passing through a given point is a two-dimensional set, like the set of straight lines. If we demand that the circles should all pass through two given points, then we get a one-dimensional set, and so on. Each additional demand that all curves of a set should pass through one more given point reduces the dimensions of the set by one. The number of dimensions can also be reduced by methods other than that of increasing the number of given points. For example, the set of ellipses with given ratio of the axes is four-dimensional, as is that of parabolas, and so is the set of ellipses with given numerical eccentricity. The transition from the ellipse to the circle, of course, is equivalent to specifying an eccentricity, the eccentricity 0, or a particular ratio of the axes, unity. As we are interested in assessing degrees of falsifiability of theories, we will now ask whether the various methods of reducing the number of dimensions are equivalent for our purposes, or whether we should examine more closely their relative merits. Now, the stipulation that a curve should pass through a certain singular point, or small region, will often be linked up with, or correspond to, the acceptance of a certain singular statement, i.e. of an initial condition. On the other hand, the transition from, say, an ellipse hypothesis to a circle hypothesis, will obviously correspond to a reduction of the dimension of the theory itself. But how are these two methods of reducing the dimensions to be kept apart? We may give the name material reduction to that method of reducing dimensions which does not operate with stipulations as to the form or shape of the curve, that is, to reductions through specifying one or more points, for example, or by some equivalent specification. The other method, in which the form or shape of the curve becomes more narrowly specified as, for example, when we pass from ellipse to circle, or from circle to straight line, etc., I will call the method of formal reduction of the number of dimensions. It is not very easy, however, to get this distinction sharp. This may be seen as follows. Reducing the dimensions of a theory means, in algebraic terms, replacing a parameter by a constant. Now, it is not quite clear how we can distinguish between different methods of replacing a parameter by a constant. The formal reduction, by passing from the general equation of an ellipse to the equation of a circle, can be described as equating one parameter to 0, and a second parameter to 1. But if another parameter, the absolute term, is equated to 0, then this would mean a material reduction, namely the specification of a point of the ellipse. I think, however, that it is possible to make the distinction clear, if we see its connection with the problem of universal names. For material reduction introduces an individual name, formal reduction a universal name, into the definition of the relevant set of curves. Let us imagine that we are given a certain individual plane, perhaps by ostensive definition. The set of all ellipses in this plane can be defined by means of the general equation of the ellipse, the set of circles, by the general equation of the circle. These definitions are independent of where, in the plane, we draw the Cartesian co-ordinates to which they relate. Consequently, they are independent of the choice of the origin, and the orientation, of the co-ordinates. A specific system of co-ordinates can be determined only by individual names, say, by ostensively specifying its origin and orientation. Since the definition of the set of ellipses, or circles, is the same for all Cartesian co-ordinates, it is independent of the specification of these individual names. It is invariant with respect to all co-ordinate transformations of the Euclidean group, displacements and similarity transformations. If, on the other hand, one wishes to define a set of ellipses, or circles, which have a specific, an individual point of the plane in common, then we must operate with an equation which is not invariant with respect to the transformations of the Euclidean group, but relates to a singular, i.e. an individually or ostensibly specified, co-ordinate system. Thus it is connected with individual names. The transformations can be arranged in a hierarchy. A definition which is invariant with respect to a more general group of transformations is also invariant with respect to more special ones. For each definition of a set of curves, there is one the most general transformation group which is characteristic of it. Now we can say, the definition D of a set of curves is called equally general to, or more general than, a definition D of a set of curves if it is invariant with respect to the same transformation group as is D, or a more general one. A reduction of the dimension of a set of curves may now be called formal if the reduction does not diminish the generality of the definition, otherwise it may be called material. If we compare the degree of falsiability of two theories by considering their dimensions, we shall clearly have to take into account their generality, i.e. their invariance with respect to co-ordinate transformations, along with their dimensions. The procedure will, of course, have to be diarrant according to whether the theory, like Kepler's theory, in fact makes geometrical statements about the world or whether it is geometrical only in that it may be represented by a graph such as, for example, the graph which represents the dependence of pressure upon temperature. It would be inappropriate to require of this latter kind of theory, or of the corresponding set of curves, that its definition should be invariant with respect to, say, rotations of the co-ordinate system, for in these cases, the diarrant co-ordinates may represent entirely diarrant things, the one pressure and the other temperature. This concludes my exposition of the methods whereby degrees of falsiability are to be compared. I believe that these methods can help us to elucidate epistemological questions, such as the problem of simplicity, which will be our next concern. But there are other problems which are placed in a new light by our examination of degrees of falsiability, as we shall see, especially the problem of the so-called probability of hypotheses or of corroboration. Addendum. One of the more important ideas of this book is that of the empirical, or informative, content of a theory. Not for nothing do we call the laws of nature laws, the more they prohibit, the more they say. CP pages above, and pp. F. 2 points were stressed by me in the preceding chapter, the content or the testability, or the simplicity, CCH 7, of a theory may have degrees, which may thus be said to relativize the idea of falsiability, whose logical basis remains the modus tollens. The aim of science, the growth of knowledge, can be identified with the growth of the content of our theories. See my paper The Aim of Science, in ratio I, pages and, revised, in Contemporary Philosophy, ed. R. Klibinsky, pages, now also chapter of my book Objective Knowledge, An Evolutionary Approach, which is forthcoming at the Clarendon Press. More recently I have developed these ideas further, see especially CH0 of my Conjectures and Refutations, and later editions, with the new addenda. Two of the new points are, a further relativization of the idea of content or testability with respect to the problem, or set of problems, under discussion. Already I relativized these ideas with respect to a eld of application, see my old Appendix I. The introduction of the idea of the truth content of a theory and of its approximation or nearness to truth, verisimilitude. Simplicity. There seems to be little agreement as to the importance of the so-called problem of simplicity. Wales said, not long ago, that the problem of simplicity is of central importance for the epistemology of the natural sciences. Yet it seems that interest in the problem has lately declined, perhaps because, especially after Wales' penetrating analysis, there seemed to be so little chance of solving it. Until quite recently the idea of simplicity has been used uncritically, as though it were quite obvious what simplicity is, and why it should be valuable. Not a few philosophers of science have given the concept of simplicity a place of crucial importance in their theories, without even noticing the difficulties to which it gives rise. For example, the followers of Mach, Kirchhoff, and Avenarius have tried to replace the idea of a causal explanation by that of the simplest description. Without the adjective simplest or a similar word, this doctrine would say nothing. As it is supposed to explain why we prefer a description of the world with the help of theories to one with the help of singular statements, it seems to presuppose that theories are simpler than singular statements. Yet few have ever attempted to explain why they should be simpler, or what is meant, more precisely, by simplicity. If, moreover, we assume that theories are to be used for the sake of simplicity, then, clearly, we should use the simplest theories. This is how Poincaré, for whom the choice of theories is a matter of convention, comes to formulate his principle for the selection of theories. He chooses the simplest of the possible conventions. But which are the simplest? 41. Elimination of the aesthetic and the pragmatic concepts of simplicity. The word simplicity is used in very many different senses. Schrödinger's theory, for instance, is of great simplicity in a methodological sense, but in another sense it might well be called complex. We can say of a problem that its solution is not simple but difficult, or of a presentation or an exposition that it is not simple but intricate. To begin with, I shall exclude from our discussion the application of the term simplicity to anything like a presentation or an exposition. It is sometimes said of two expositions of one and the same mathematical proof that the one is simpler or more elegant than the other. This is a distinction which has little interest from the point of view of the theory of knowledge. It does not fall within the province of logic, but merely indicates a preference of an aesthetic or pragmatic character. The situation is similar when people say that one task may be carried out by simpler means than another, meaning that it can be done more easily or that, in order to do it, less training or less knowledge is needed. In all such cases the word simple can be easily eliminated, its use is extralogical. 42. The methodological problem of simplicity. What, if anything, remains after we have eliminated the aesthetic and the pragmatic ideas of simplicity? Is there a concept of simplicity which is of importance for the logician? Is it possible to distinguish theories that are logically not equivalent according to their degrees of simplicity? The answer to this question may well seem doubtful, seeing how little successful have been most attempts to deem this concept. Schlick, for one, gives a negative answer. He says, simplicity is a concept indicative of preferences which are partly practical, partly aesthetic in character. And it is notable that he gives this answer when writing of the concept which interests us here, and which I shall call the epistemological concept of simplicity, for he continues, even if we are unable to explain what is really meant by simplicity here, we must yet recognize the fact that any scientist who has succeeded in representing a series of observations by means of a very simple formula, e.g. by a linear, quadratic, or exponential function, is immediately convinced that he has discovered a law. Schlick discusses the possibility of denying the concept of law-like regularity, and especially the distinction between law and chance, with the help of the concept of simplicity. He narrowly dismisses it with the remark that simplicity is obviously a wholly relative and vague concept, no strict definition of causality can be obtained with its help, nor can law and chance be precisely distinguished. From this passage it becomes clear what the concept of simplicity is actually expected to achieve. It is to provide a measure of the degree of law-likeness or regularity of events. A similar view is voiced by Fagel when he speaks of the idea of denying the degree of regularity or of law-likeness with the help of the concept of simplicity. The epistemological idea of simplicity plays a special part in theories of inductive logic, for example in connection with the problem of the simplest curve. Believers in inductive logic assume that we arrive at natural laws by generalization from particular observations. If we think of the various results in a series of observations as points plotted in a coordinate system, then the graphic representation of the law will be a curve passing through all these points. But through a finite number of points we can always draw an unlimited number of curves of the most diverse form. Since therefore the law is not uniquely determined by the observations, inductive logic is confronted with the problem of deciding which curve, among all these possible curves, is to be chosen. The usual answer is, choose the simplest curve. Wittgenstein, for example, says, the process of induction consists in assuming the simplest law that can be made to harmonize with our experience. In choosing the simplest law, it is usually tacitly assumed that a linear function, say, is simpler than a quadratic one, a circle simpler than an ellipse, etc. But no reasons are given either for choosing this particular hierarchy of simplicities in preference to any other, or for believing that simple laws have advantages over the less simple apart from aesthetic and practical ones. Schlick and Feigl mention an unpublished paper of Natkin who, according to Schlick's account, proposes to call one curve simpler than another if its average curvature is smaller, or, according to Feigl's account, if it deviates less from a straight line. The two accounts are not equivalent. This definition seems to agree pretty well with our intuitions, but it somehow misses the crucial point. It would, for example, make certain parts, the asymptotic parts, of a hyperbola much simpler than a circle, etc. And really, I do not think that the question can be settled by such artifices, as Schlick calls them. Moreover, it would remain a mystery why we should give preference to simplicity if deemed in this particular way. Weyl discusses and rejects a very interesting attempt to base simplicity on probability. Assume, for example, that 20 co-ordinated pairs of values, x, y, of the same function, y equals f, x, lie, within the expected accuracy, on a straight line, when plotted on square graph paper. We shall then conjecture that we are faced here with a rigorous natural law, and that y depends linearly upon x. And we shall conjecture this because of the simplicity of the straight line, or because it would be so extremely improbable that just these 20 pairs of arbitrarily chosen observations should lie very nearly on a straight line, had the law in question been a diarrhent one. If now we use the straight line for interpolation and extrapolation, we obtain predictions which go beyond what the observations tell us. However, this analysis is open to criticism. It will always be possible to deem all kinds of mathematical functions which will be satisfied by the 20 observations, and some of these functions will deviate considerably from the straight line. And for every single one of these we may claim that it would be extremely improbable that the 20 observations should lie just on this curve, unless it represented the true law. It is thus essential, after all, that the function, or rather the class of functions, should be aired to us, a priori, by mathematics because of its mathematical simplicity. It should be noted that this class of functions must not depend upon as many parameters as the number of observations to be satisfied. Weyl remarked that the class of functions should be aired to us a priori, by mathematics, because of its mathematical simplicity, and his reference to the number of parameters agree with my view, to be developed in section. But Weyl does not say what mathematical simplicity is, and above all, he does not say what logical or epistemological advantages the simpler law is supposed to possess, compared with one that is more complex. The various passages so far quoted are very important, because of their bearing upon our present aim, the analysis of the epistemological concept of simplicity. For this concept is not yet precisely determined. It is therefore possible to reject any attempt, such as mine, to make this concept precise by saying that the concept of simplicity in which epistemologists are interested is really quite a diarrhent one. To such objections I could answer that I do not attach the slightest importance to the word simplicity. The term was not introduced by me, and I am aware of its disadvantages. All I do assert is that the concept of simplicity which I am going to clarify helps to answer those very questions which, as my quotations show, have so often been raised by philosophers of science in connection with their problem of simplicity. 43. Simplicity and degree of falsifiability. The epistemological questions which arise in connection with the concept of simplicity can all be answered if we equate this concept with degree of falsifiability. This assertion is likely to meet with opposition, and so I shall try, to make it intuitively more acceptable. I have already shown that theories of a lower dimension are more easily falsifiable than those of a higher dimension. A law having the form of a function of the RST degree, for instance, is more easily falsifiable than one expressible by means of a function of the second degree. But the latter still belongs to the best falsifiable ones among the laws whose mathematical form is that of an algebraic function. This agrees well with Schlick's remark concerning simplicity. We should certainly be inclined to regard a function of the RST degree as simpler than one of the second degree, though the latter also doubtless represents a perfectly good law. The degree of universality and of precision of a theory increases with its degree of falsiability, as we have seen. Thus we may perhaps identify the degree of strictness of a theory, the degree, as it were, to which a theory imposes the rigor of law upon nature, with its degree of falsiability, which shows that the latter does just what Schlick and Fagel expected the concept of simplicity to do. I may add that the distinction which Schlick hoped to make between law and chance can also be clarified with the help of the idea of degrees of falsiability. Probability statements about sequences having chance-like characteristics turn out to be of inite dimension, cf. section, not simple but complex, cf. section and latter part of, and falsiable only under special safeguards, section. The comparison of degrees of testability has been discussed at length in sections 2.0. Some of the examples and other details given there can be easily transferred to the problem of simplicity. This holds especially for the degree of universality of a theory. A more universal statement can take the place of many less universal ones, and for that reason has often been called simpler. The concept of the dimension of a theory may be said to give precision to Weyl's idea of using the number of parameters to determine the concept of simplicity. And by means of our distinction between a formal and a material reduction of the dimension of a theory, cf. section 0, certain possible objections to Weyl's theory can be met. One of these is the objection that the set of ellipses whose axes stand in a given ratio, and whose numerical eccentricity is given, has exactly as many parameters as the set of circles, although it is obviously less simple. Above all, our theory explains why simplicity is so highly desirable. To understand this, there is no need for us to assume a principle of economy of thought or anything of the kind. Simple statements, if no leges are object, are to be prized more highly than less simple ones because they tell us more, because their empirical content is greater, and because they are better testable. 44. Geometrical shape and functional form. Our view of the concept of simplicity enables us to resolve a number of contradictions which up to now have made it doubtful whether this concept was of any use. Few would regard the geometrical shape of, say, a logarithmic curve as particularly simple, but a law which can be represented by a logarithmic function is usually regarded as a simple one. Similarly, a sine function is commonly said to be simple, even though the geometrical shape of the sine curve is perhaps not so very simple. Difficulties like this can be cleared up if we remember the connection between the number of parameters and the degree of falsiability, and if we distinguish between the formal and the material reduction of dimensions. We must also remember the role of invariance with respect to transformations of the coordinate systems. If we speak of the geometrical form or shape of a curve, then what we demand is invariance with respect to all transformations belonging to the group of displacements, and we may demand invariance with respect to similarity transformations, for we do not think of a geometrical GUR or shape as being tied to a d-nite position. Consequently, if we think of the shape of a one-parametric logarithmic curve, y equals log x, as lying anywhere in a plane, then it would have VE parameters, if we allow for similarity transformations. It would thus be by no means a particularly simple curve. If, on the other hand, a theory or law is represented by a logarithmic curve, then coordinate transformations of the kind described are irrelevant. In such cases, there is no point in either rotations or parallel displacements or similarity transformations. For a logarithmic curve as a rule is a graphic representation in which the coordinates cannot be interchanged. For example, the x-axis might represent atmospheric pressure, and the y-axis height above sea level. For this reason, similarity transformations are equally without any significance here. Analogous considerations hold for sine oscillations along a particular axis, for example, the time axis, and for many other cases. 45. The simplicity of Euclidean geometry. One of the issues which played a major role in most of the discussions of the theory of relativity was the simplicity of Euclidean geometry. Nobody ever doubted that Euclidean geometry as such was simpler than any non-Euclidean geometry with given constant curvature, not to mention non-Euclidean geometries with curvatures varying from place to place. At RST site the kind of simplicity here involved seems to have little to do with degrees of falsiability. But if the statements at issue are formulated as empirical hypotheses, then we nd that the two concepts, simplicity and falsiability, coincide in this case also. Let us consider what experiments may help us to test the hypothesis. In our world, we have to employ a certain metrical geometry with such and such a radius of curvature. A test will be possible only if we identify certain geometrical entities with certain physical objects, for instance straight lines with light rays, or points with the intersection of threads. If such an identification, a correlating denition, or perhaps an ostensive denition, cf section, is adopted, then it can be shown that the hypothesis of the validity of an Euclidean light ray geometry is falsiable to a higher degree than any of the competing hypotheses which assert the validity of some non-Euclidean geometry. For if we measure the sum of the angles of a light ray triangle, then any significant deviation from 0 degrees will falsify the Euclidean hypothesis. The hypothesis of a Bolyai-Lobachevsky geometry with given curvature, on the other hand, would be compatible with any particular measurement not exceeding 0 degrees. Moreover, to falsify this hypothesis it would be necessary to measure not only the sum of the angles, but also the absolute size of the triangle, and this means that in addition to angles, a further unit of measurement, such as a unit of area, would have to be deemed. Thus we see that more measurements are needed for a falsification, that the hypothesis is compatible with greater variations in the results of measurements, and that it is therefore more difficult to falsify, it is falsifiable to a lesser degree. To put it in another way, Euclidean geometry is the only metric geometry with a finite curvature in which similarity transformations are possible. In consequence, Euclidean geometrical groups can be invariant with respect to more transformations, that is, they can be of lower dimension, they can be simpler. 46. Conventionalism and the concept of simplicity. What the conventionalist calls simplicity does not correspond to what I call simplicity. It is the central idea of the conventionalist, and also his starting point, that no theory is unambiguously determined by experience, a point with which I agree. He believes that he must therefore choose the simplest theory. But since the conventionalist does not treat his theories as falsifiable systems but rather as conventional stipulations, he obviously means by simplicity something different from degree of falsifiability. The conventionalist concept of simplicity turns out to be indeed partly aesthetic and partly practical. Thus the following comment by Schlick, cf section, applies to the conventionalist concept of simplicity, but not to mine. It is certain that one can only deem the concept of simplicity by a convention which must always be arbitrary. It is curious that conventionalists themselves have overlooked the conventional character of their own fundamental concept, that of simplicity. That they must have overlooked it is clear, for otherwise they would have noticed that their appeal to simplicity could never save them from arbitrariness, once they had chosen the way of arbitrary convention. From my point of view, a system must be described as complex in the highest degree if, in accordance with conventionalist practice, one holds fast to it as a system established forever which one is determined to rescue, whenever it is in danger, by the introduction of auxiliary hypotheses. For the degree of falsifiability of a system thus protected is equal to 0. Thus we are led back, by our concept of simplicity, to the methodological rules of section 0, and especially also to that rule or principle which restrains us from indulgence in ad hoc hypotheses and auxiliary hypotheses, to the principle of parsimony in the use of hypotheses. Addendum. In this chapter I have tried to show how far degrees of simplicity can be identified with degrees of testability. Nothing depends on the word simplicity, I never quarrel about words, and I did not seek to reveal the essence of simplicity. What I attempted was merely this. Some great scientists and philosophers have made assertions about simplicity and its value for science. I suggested that some of these assertions can be better understood if we assume that when speaking about simplicity they sometimes had testability in mind. This elucidates even some of Poincaré's examples, though it clashes with his views. Today I should stress two further points. we can compare the IES with respect to testability only if at least some of the problems they are supposed to solve coincide. Ad hoc hypotheses cannot be compared in this way. Probability. In this chapter I shall only deal with the probability of events and the problems it raises. They arise in connection with the theory of games of chance, and with the probabilistic laws of physics. I shall leave the problems of what may be called the probability of hypotheses, such questions as whether a frequently tested hypothesis is more probable than one which has been little tested, to be discussed in sections 2 under the title of corroboration. Ideas involving the theory of probability play a decisive part in modern physics. Yet we still lack a satisfactory, consistent definition of probability, or, what amounts to much the same, we still lack a satisfactory axiomatic system for the calculus of probability. The relations between probability and experience are also still in need of clarification. In investigating this problem we shall discover what will at RST seem an almost insuperable objection to my methodological views. For although probability statements play such a vitally important role in empirical science, they turn out to be in principle impervious to strict falsification. Yet this very stumbling block will become a touchstone upon which to test my theory, in order to end out what it is worth. Thus we are confronted with two tasks. The RST is to provide new foundations for the calculus of probability. This I shall try to do by developing the theory of probability as a frequency theory, along the lines followed by Richard von Mises, but without the use of what he calls the axiom of convergence, or limit axiom, and with a somewhat weakened axiom of randomness. The second task is to elucidate the relations between probability and experience. This means solving what I call the problem of decidability of probability statements. My hope is that these investigations will help to relieve the present unsatisfactory situation in which physicists make much use of probabilities without being able to say, consistently, what they mean by probability. 47. The problem of interpreting probability statements. I shall begin by distinguishing two kinds of probability statements, those which state a probability in terms of numbers, which I will call numerical probability statements, and those which do not. Thus the statement, the probability of throwing 11 with 2 true dice is / would be an example of a numerical probability statement. Non-numerical probability statements can be of various kinds. It is very probable that we shall obtain a homogeneous mixture. By mixing water and alcohol, illustrates one kind of statement which, suitably interpreted, might perhaps be transformed into a numerical probability statement. For example, the probability of obtaining is very near to . A very different kind of non-numerical probability statement would be, for instance, the discovery of a physical fact which contradicts the quantum theory is highly improbable, a statement which, I believe, cannot be transformed into a numerical probability statement, or put on a par with 1, without distorting its meaning. I shall deal RST with numerical probability statements. Non-numerical ones, which I think less important, will be considered afterwards. In connection with every numerical probability statement, the question arises, how are we to interpret a statement of this kind and, in particular, the numerical assertion it makes? 48. Subjective and objective interpretations. The classical, Laplacian, theory of probability deems the numerical value of a probability as the quotient obtained by dividing the number of favorable cases by the number of equally possible cases. We might disregard the logical objections which have been raised against this definition, such as that equally possible is only another expression for equally probable. But even then we could hardly accept this definition as providing an unambiguously applicable interpretation. For there are latent in it several different interpretations which I will classify as subjective and objective. A subjective interpretation of probability theory is suggested by the frequent use of expressions with a psychological avur, like mathematical expectation or, say, normal law of error, etc. In its original form it is psychologistic. It treats the degree of probability as a measure of the feelings of certainty or uncertainty, of belief or doubt, which may be. Cf. for example von Mises, Wahrscheinlichkeit, Statistik und Wahrheit, pp. Dot, ND edition, pp. Dot, English translation by J. Neyman, D. Schall, and E. Rubinowitz, Probability, Statistics, and Truth, pp. Although the classical definition is often called Laplacian, also in this book, it is at least as old as de Moivre's doctrine of chances. For an early objection against the phrase equally possible, C.C. Speier's, Collected Papers, RST published, p. para. Aroused in us by certain assertions or conjectures. In connection with some non-numerical statements, the word probable may be quite satisfactorily translated in this way, but an interpretation along these lines does not seem to me very satisfactory for numerical probability statements. A newer variant of the subjective interpretation, however, deserves more serious consideration here. This interprets probability statements not psychologically but logically, as assertions about what may be called the logical proximity of statements. Statements, as we all know, can stand in various logical relations to one another, like derivability, incompatibility, or mutual independence, and the logico-subjective theory, of which Keynes is the principal exponent, treats the probability relation as a special kind of logical relationship between two statements. The two extreme cases of this probability relation are derivability and contradiction. A statement Q gives, it is said, to another statement P the probability if P follows from Q. In case P and Q contradict each other, the probability given by Q to P is 0. Between these extremes lie other probability relations which, roughly speaking, may be interpreted in the following way: the numerical probability of a statement P, given Q, is the greater the less its content goes beyond what is already contained in that statement Q upon which the probability of P depends, and which gives to P a probability. The kinship between this and the psychologistic theory may be seen from the fact that Keynes deems probability as the degree of rational belief. By this he means the amount of trust it is proper to accord to a statement P in the light of the information or knowledge which we get from that statement Q which gives probability to P. A third interpretation, the objective interpretation, treats every numerical probability statement as a statement about the relative frequency with which an event of a certain kind occurs within a sequence of occurrences. According to this interpretation, the statement "the probability of the next throw with this die being a VE equals / is not really an assertion about the next throw, rather, it is an assertion about a whole class of throws of which the next throw is merely an element. The statement in question says no more than that the relative frequency of VES, within this class of throws, equals /. According to this view, numerical probability statements are only admissible if we can give a frequency interpretation of them. Those probability statements for which a frequency interpretation cannot be given, and especially the non-numerical probability statements, are usually shunned by the frequency theorists. In the following pages I shall attempt to construct anew the theory of probability as a moded frequency theory. Thus I declare my faith in an objective interpretation, chiefly because I believe that only an objective theory can explain the application of the probability calculus within empirical science. Admittedly, the subjective theory is able to give a consistent solution to the problem of how to decide probability statements, and it is, in general, faced by fewer logical difficulties than is the objective theory. But its solution is that probability statements are non-empirical, that they are tautologies. And this solution turns out to be utterly unacceptable when we remember the use which physics makes of the theory of probability. I reject that variant of the subjective theory which holds that objective frequency statements should be derived from subjective assumptions, perhaps using Bernoulli's theorem as a bridge. I regard this program for logical reasons as unrealizable. 49. The fundamental problem of the theory of chance. The most important application of the theory of probability is to what we may call chance-like or random events, or occurrences. These seem to be characterized by a peculiar kind of incalculability which makes one disposed to believe after many unsuccessful attempts that all known rational methods of prediction must fail in their case. We have, as it were, the feeling that not a scientist but only a prophet could predict them. And yet, it is just this incalculability that makes us conclude that the calculus of probability can be applied to these events. This somewhat paradoxical conclusion from incalculability to calculability, i.e. to the applicability of a certain calculus, ceases, it is true, to be paradoxical if we accept the subjective theory. But this way of avoiding the paradox is extremely unsatisfactory. For it entails the view that the probability calculus is not a method of calculating predictions, in contradistinction to all the other methods of empirical science. It is, according to the subjective theory, merely a method for carrying out logical transformations of what we already know, or rather what we do not know, for it is just when we lack knowledge that we carry out these transformations. This conception dissolves the paradox indeed, but it does not explain how a statement of ignorance, interpreted as a frequency statement, can be empirically tested and corroborated. Yet this is precisely our problem. How can we explain the fact that from incalculability, that is, from ignorance, we may draw conclusions which we can interpret as statements about empirical frequencies, and which we then brilliantly corroborated in practice? Even the frequency theory has not up to now been able to give a satisfactory solution of this problem, the fundamental problem of the theory of chance, as I shall call it. It will be shown in section that this problem is connected with the axiom of convergence, which is an integral part of the theory in its present form. But it is possible to end a satisfactory solution within the framework of the frequency theory, after this axiom has been eliminated. It will be found by analyzing the assumptions which allow us to argue from the irregular succession of single occurrences to the regularity or stability of their frequencies. 50. The frequency theory of von Mises. A frequency theory which provides a foundation for all the principal theorems of the calculus of probability was proposed by Richard von Mises. His fundamental ideas are as follows. The calculus of probability is a theory of certain chance-like or random sequences of events or occurrences, i.e. of repetitive events such as a series of throws with a die. These sequences are deemed as chance-like or random by means of two axiomatic conditions, the axiom of convergence, or the limit axiom, and the axiom of randomness. If a sequence of events satisfies both of these conditions, it is called by von Mises a collective. A collective is, roughly speaking, a sequence of events or occurrences which is capable in principle of being continued indefinitely, for example a sequence of throws made with a supposedly indestructible die. Each of these events has a certain character or property, for example, the throw may show a VE and so have the property VE. If we take all those throws having the property VE which have appeared up to a certain element of the sequence, and divide their number by the total number of throws up to that element, i.e. its ordinal number in the sequence, then we obtain the relative frequency of VES up to that element. If we determine the relative frequency of VES up to every element of the sequence, then we obtain in this way a new sequence, the sequence of the relative frequencies of VES. This sequence of frequencies is distinct from the original sequence of events to which it corresponds, and which may be called the event sequence or the property sequence. As a simple example of a collective, I choose what we may call an alternative. By this term we denote a sequence of events supposed to have two properties only, such as a sequence of tosses of a coin. The one property, heads, will be denoted by, and the other, tails, by 0. A sequence of events, or sequence of properties, may then be represented as follows. A 0 0 0 0 0 0 0. Corresponding to this alternative, or, more precisely, correlated with the property of this alternative, is the following sequence of relative frequencies, or frequency sequence. A cent, A 0. Now the axiom of convergence, or limit axiom, postulates that, as the event sequence becomes longer and longer, the frequency sequence shall tend towards a finite limit. This axiom is used by von Mises because we have to make sure of one XED frequency value with which we can work, even though the actual frequencies have fluctuating values. In any collective there are at least two properties, and if we are given the limits of the frequencies corresponding to all the properties of a collective, then we are given what is called its distribution. The axiom of randomness, or, as it is sometimes called, the principle of the excluded gambling system, is designed to give mathematical expression to the chance-like character of the sequence. Clearly, a gambler would be able to improve his chances by the use of a gambling system. If sequences of penny tosses showed regularities such as, say, a fairly regular appearance of tails after every run of 3 heads. Now the axiom of randomness postulates of all collectives that there does not exist a gambling system that can be successfully applied to them. It postulates that, whatever gambling system we may choose for selecting supposedly favorable tosses, we shall end that, if gambling is continued long enough, the relative frequencies in the sequence of tosses supposed to be favorable will approach the same limit as those in the sequence of all tosses. Thus a sequence for which there exists a gambling system by means of which the gambler can improve his chances is not a collective in the sense of von Mises. Probability, for von Mises, is thus another term for limit of relative frequency in a collective. The idea of probability is therefore application able only to sequences of events, a restriction likely to be quite unacceptable from a point of view such as Keynes's. To critics objecting to the narrowness of his interpretation, von Mises replied by stressing the difference between the scientific use of probability, for example in physics, and the popular uses of it. He pointed out that it would be a mistake to demand that a properly defined scientific term has to correspond in all respects to inexact, pre-scientific usage. The task of the calculus of probability consists, according to von Mises, simply and solely in this, to infer certain derived collectives with derived distributions from certain given initial collectives with certain given initial distributions, in short, to calculate probabilities which are not given from probabilities which are given. The distinctive features of his theory are summarized by von Mises in 4 points. The concept of the collective precedes that of probability, the latter is deemed as the limit of the relative frequencies, an axiom of randomness is formulated, and the task of the calculus of probability is deemed. 51. Plan for a new theory of probability. The 2 axioms or postulates formulated by von Mises in order to deem the concept of a collective have met with strong criticism. Criticism which is not, I think, without some justification. In particular, objections have been raised against combining the axiom of convergence with the axiom of randomness on the ground that it is inadmissible to apply the mathematical concept of a limit, or of convergence, to a sequence which by definition, that is, because of the axiom of randomness, must not be subject to any mathematical rule or law. For the mathematical limit is nothing but a characteristic property of the mathematical rule or law by which the sequence is determined. It is merely a property of this rule or law if, for any chosen fraction arbitrarily close to 0, there is an element in the sequence such that all elements following it deviate by less than that fraction from some finite value which is then called their limit. To meet such objections it has been proposed to refrain from combining the axiom of convergence with that of randomness, and to postulate only convergence, i.e. the existence of a limit. As to the axiom of randomness, the proposal was either to abandon it altogether, Kampf, or to replace it by a weaker requirement, Reichenbach. These suggestions presuppose that it is the axiom of randomness which is the cause of the trouble. In contrast to these views, I am inclined to blame the axiom of convergence no less than the axiom of randomness. Thus I think that there are 2 tasks to be performed, the improvement of the axiom of randomness mainly a mathematical problem, and the complete elimination of the axiom of convergence a matter of particular concern for the epistemologist. Cf. section. In what follows I propose to deal RST with the mathematical, and afterwards with the epistemological question. The RST of these 2 tasks, the reconstruction of the mathematical theory, has as its main aim the derivation of Bernoulli's theorem, the RST law of great numbers, from a moded axiom of randomness. Moded, namely, so as to demand no more than is needed to achieve this aim. Or to be more precise, my aim is the derivation of the binomial formula, sometimes called Newton's formula, in what I call its 3rd form. For from this formula, Bernoulli's theorem and the other limit theorems of probability theory can be obtained in the usual way. My plan is to work out RST of frequency theory for night classes, and to develop the theory, within this frame, as far as possible, that is, up to the derivation of the RST binomial formula. This frequency theory for night classes turns out to be a quite elementary part of the theory of classes. It will be developed merely in order to obtain a basis for discussing the axiom of randomness. Next I shall proceed to innate sequences, i.e. to sequences of events which can be continued indefinitely, by the old method of introducing an axiom of convergence, since we need something like it for our discussion of the axiom of randomness. And after deriving and examining Bernoulli's theorem, I shall consider how the axiom of convergence might be eliminated, and what sort of axiomatic system we should be left with as the result. In the course of the mathematical derivation I shall use three diarent frequency symbols. F superscript 2 is to symbolize relative frequency in night classes, F cent is to symbolize the limit of the relative frequencies of an innate frequency sequence, and nally F is to symbolize objective probability, i.e. relative frequency in an irregular or random or chance-like sequence. 52 Relative frequency within a finite class. Let us consider a class alpha of a night number of occurrences, for example the class of throws made yesterday with this particular die. This class alpha, which is assumed to be non-empty, serves, as it were, as a frame of reference, and will be called a night reference class. The number of elements belonging to alpha, i.e. its cardinal number, is denoted by n, alpha, to be read the number of alpha. Now let there be another class, beta, which may be night or not. We will call beta our property class. It may be, for example, the class of all throws which show a VE, or, as we shall say, which have the property VE. The class of those elements which belong to both alpha and beta, for example the class of throws made yesterday with this particular die and having the property VE, is called the product class of alpha and beta, and is denoted by alpha.beta, to be read alpha and beta. Since alpha.beta is a subclass of alpha, it can at most contain a night number of elements, it may be empty. The number of elements in alpha.beta is denoted by n, alpha.beta. Whilst we symbolize night numbers of elements by n, the relative frequencies are symbolized by f superscript 2. For example, the relative frequency of the property beta within the night reference class alpha is written alpha f superscript 2, beta, which may be read the alpha frequency of beta. We can now definition alpha f superscript 2, beta, equals n, alpha dot beta, n, alpha. In terms of our example this would mean, the relative frequency of VES among yesterday's throws with this die is, by definition, equal to the quotient obtained by dividing the number of VES, thrown yesterday with this die, by the total number of yesterday's throws with this die. From this rather trivial definition, the theorems of the calculus of frequency in night classes can very easily be derived, more especially, the general multiplication theorem, the theorem of addition, and the theorems of division, i.e. Bayes' rules. Cf. Appendix 2. Of the theorems of this calculus of frequency, and of the calculus of probability in general, it is characteristic that cardinal numbers, n numbers, never appear in them, but only relative frequencies, i.e. ratios, or f numbers. The n numbers only occur in the proofs of a few fundamental theorems which are directly deduced from the definition, but they do not occur in the theorems themselves. How this is to be understood will be shown here with the help of one very simple example. Further examples will be found in Appendix 2. Let us denote the class of all elements which do not belong to beta by beta, read, the complement of beta or simply, non-beta. Then we may write f superscript 2, beta, plus f superscript 2, equals alpha alpha beta. While this theorem only contains f numbers, its proof makes use of n numbers. For the theorem follows from the definition, with the help of a simple theorem from the calculus of classes which asserts that beta n, alpha dot beta, plus n, alpha equals n, alpha. 53 Selection, independence, insensitiveness, Irrelevance. Among the operations which can be performed with relative frequencies in night classes, the operation of selection is of special importance for what follows. Let a night reference class alpha be given, for example the class of buttons in a box, and two property classes, beta, say, the red buttons, and gamma, say, the large buttons. We may now take the product class alpha.beta as a new reference class, and raise the question of the value of alpha.beta f superscript 2, gamma, i.e. of the frequency of gamma within the new reference class. The new reference class alpha.beta may be called the result of selecting beta elements from alpha, or the selection from alpha according to the property beta, for we may think of it as being obtained by selecting from alpha all those elements, buttons, which have the property beta, red. Now it is just possible that gamma may occur in the new reference class, alpha.beta, with the same relative frequency as in the original reference class alpha, i.e. it may be true that alpha.beta f superscript 2, gamma, equals alpha f superscript 2, gamma. In this case we say, following Hoster, that the properties beta and gamma are mutually independent, within the reference class alpha. The relation of independence is a three-termed relation and is symmetrical in the properties beta and gamma. If two properties beta and gamma are, mutually, independent within a reference class alpha, we can also say that the property gamma is, within alpha, insensitive to the selection of beta elements, or perhaps that the reference class alpha is, with respect to this property gamma, insensitive to a selection according to the property beta. The mutual independence, or insensitiveness, of beta and gamma within alpha could also from the point of view of the subjective theory be interpreted as follows: if we are informed that a particular element of the class alpha has the property beta, then this information is irrelevant if beta and gamma are mutually independent within alpha, irrelevant namely, to the question whether this element also has the property gamma, or not. If, on the other hand, we know that gamma occurs more often, or less often, in the subclass alpha.beta, which has been selected from alpha according to beta, then the information that an element has the property beta is relevant to the question whether this element also has the property gamma or not. 54 Finite sequences. Ordinal selection and neighborhood selection. Let us suppose that the elements of a night reference class alpha are numbered, for instance that a number is written on each button in the box, and that they are arranged in a sequence, in accordance with these ordinal numbers. In such a sequence we can distinguish two kinds of selection which have special importance, namely selection according to the ordinal number of an element, or BRI, ordinal selection, and selection according to its neighborhood. Ordinal selection consists in making a selection, from the sequence alpha, in accordance with a property beta which depends upon the ordinal number of the element, whose selection is to be decided on. For example, beta may be the property even, so that we select from alpha all those elements whose ordinal number is even. The elements thus selected form a selected subsequence. Should a property gamma be independent of an ordinal selection according to beta, then we can also say that the ordinal selection is independent with respect to gamma, or we can say that the sequence alpha is, with respect to gamma, insensitive to a selection of beta elements. Neighborhood selection is made possible by the fact that, in ordering the elements in a numbered sequence, certain neighborhood relations are created. This allows us, for example, to select all those members whose immediate predecessor has the property gamma, or, say, those whose RST and second predecessors, or whose second successor, have the property gamma, and so on. Thus if we have a sequence of events, say tosses of a coin, we have to distinguish two kinds of properties, its primary properties such as heads or tails, which belong to each element independently of its position in the sequence, and its secondary properties such as even or successor of tails, etc., which an element acquires by virtue of its position in the sequence. A sequence with two primary properties has been called alternative. As von Mises has shown, it is possible to develop, if we are careful, the essentials of the theory of probability as a theory of alternatives, without sacrificing generality. Denoting the two primary properties of an alternative by the Gers and zero, every alternative can be represented as a sequence of ones and zeros. Now the structure of an alternative can be regular, or it can be more or less irregular. In what follows we will study this regularity or irregularity of certain Knight alternatives more closely. 55 and freedom in finite sequences. Let us take a Knight alternative alpha, for example one consisting of 1,000 ones and zeros regularly arranged as follows. Alpha, 0 0 0 0 0 0 0 0. In this alternative we have equal distribution, i.e. the relative frequencies of the ones and the zeros are equal. If we denote the relative frequency of the property by f superscript 2, and that of 0 by f superscript 2, 0, we can write f superscript 2 equals f superscript 2, 0, equals alpha alpha. We now select from alpha all terms with the neighborhood property of immediately succeeding a 1, within the sequence alpha. If we denote this property by beta, we may call the selected subsequence alpha dot beta. It will have the structure alpha dot beta, 0 0 0 0 0. This sequence is again an alternative with equal distribution. Moreover, neither the relative frequency of the ones nor that of the zeros has changed, i.e. we have alpha dot beta f superscript 2 equals alpha f superscript 2, alpha dot beta f superscript 2, 0, equals alpha f superscript 2, 0. In the terminology introduced in section, we can say that the primary properties of the alternative alpha are insensitive to selection according to the property beta, or, more brie, that alpha is insensitive to selection according to beta. Since every element of alpha has either the property beta, that of being the successor of a 1, or that of being the successor of a 0, we can denote the latter property by. If we now select the members having beta, the property beta, we obtain the alternative beta alpha 0 0 0 0 0. This sequence shows a very slight deviation from equal distribution insofar as it begins and ends with 0, since alpha itself ends with 0, 0 on account of its equal distribution. If alpha contains 0 0 0 elements, then beta alpha will contain 0 0 zeros, and only ones. Such deviations from equal distribution, or from other distributions, arise only on account of the RST or last elements. They can be made as small as we please by making the sequence sufficiently long. For this reason they will be neglected in what follows, especially since our investigations are to be extended to innate sequences, where these deviations vanish. Accord beta. Ingly, we shall say that the alternative alpha has equal distribution, and beta, that the alternative alpha is insensitive to the selection of elements having the property. As a consequence, alpha, or rather the relative frequency of the primary properties of alpha, is insensitive to both a selection according to beta and according to, and we may therefore say that alpha is insensitive to every selection according to the property of the immediate predecessor. Clearly, this insensitivity is due to certain aspects of the structure of the alternative alpha, aspects which may distinguish it from other alterna beta tivs. For example, the alternatives alpha dot beta and alpha are not insensitive to selection according to the property of a predecessor. We can now investigate the alternative alpha in order to see whether it is insensitive to other selections, especially to selection according to the property of a pair of predecessors. We can, for example, select from alpha all those elements which are successors of a pair. And we see at once that alpha is not insensitive to the selection of the successor of any of the four possible pairs, 0, 0, 0, 0. In none of these cases have the resulting subsequences equal distribution. On the contrary, they all consist of uninterrupted blocks, or iterations, i.e. of nothing but ones, or of nothing but zeros. The fact that alpha is insensitive to selection according to single predecessors, but not insensitive to selection according to pairs of predecessors, might be expressed, from the point of view of the subjective theory, as follows. Information about the property of one predecessor of any element in alpha is irrelevant to the question of the property of this element. On the other hand, information about the properties of its pair of predecessors is of the highest relevance, for given the law according to which alpha is constructed, it enables us to predict the property of the element in question. The information about the properties of its pair of predecessors furnishes us, so to speak, with the initial conditions needed for deducing the prediction. The law according to which alpha is constructed requires a pair of properties as initial conditions, thus it is two-dimensional with respect to these properties. The specie-cation of one property is irrelevant only in being composite in an insouciant degree to serve as an initial condition. Cf. section. Remembering how closely the idea of causality of cause and effect is related to the deduction of predictions, I shall now make use of the following terms. The assertion previously made about the alternative alpha is insensitive to selection according to a single predecessor, I shall now express by saying, alpha is free from any after effect of single predecessors or brie, alpha is free. And instead of saying as before, that alpha is, or is not, insensitive to selection according to pairs of predecessors, I shall now say, alpha is, not, free from the after effects of pairs of predecessors, or brie, alpha is, not, free. Using the free alternative alpha as our prototype, we can now easily construct other sequences, again with equal distribution, which are not only free from the after effects of one predecessor, i.e. free, like alpha, but which are, in addition, free from the after effects of a pair of predecessors, i.e. free, and after this, we can go on to sequences which are free, etc. In this way we are led to a general idea which is fundamental for what follows. It is the idea of freedom from the after effects of all the predecessors up to some number n, or, as we shall say, of n freedom. More precisely, we shall call a sequence n free if, and only if, the relative frequencies of its primary properties are n insensitive, i.e. insensitive to selection according to single predecessors and according to pairs of predecessors and according to triplets of predecessors and according to n tuples of predecessors. An alternative alpha which is free can be constructed by repeating the generating period a 0 0 any number of times. Similarly, we obtain a free alternative with equal distribution if we take b 0 0 0 0 as its generating period. A free alternative is obtained from the generating period c 0 0 0 0 0 0 0 0. And a free alternative is obtained from the generating period d 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. It will be seen that the intuitive impression of being faced with an irregular sequence becomes stronger with the growth of the number n of its n freedom. As Dr. Kayski has pointed out to me, it is possible to simplify this definition. It is enough to demand insensitivity to selection of any predecessor n tuple, for a given n. Insensitivity to selection of n, tuples, etc., can then be proved easily. The generating period of an n-free alternative with equal distribution must contain at least n and elements. The periods given as examples can, of course, begin at diarrhent places. C, for example, can begin with its fourth element, so that we obtain, in place of c cent 0 0 0 0 0 0 0 0. There are other transformations which leave the n freedom of a sequence unchanged. A method of constructing generating periods of n-free sequences for every number n will be described elsewhere. If to the generating period of an n-free alternative we add the rstn elements of the next period, then we obtain a sequence of the length n plus n. This has, among others, the following property: every arrangement of n and zeros and ones, i.e. every possible n plus tuple, occurs in it at least once. 56 sequences of segments. The first form of the binomial formula. Given a Knight sequence alpha, we call a subsequence of alpha consisting of n consecutive elements a segment of alpha of length n, or, more brie, an n segment of alpha. If, in addition to the sequence alpha, we are given some d-night number n, then we can arrange the n segments of alpha in a sequence, the sequence of n segments of alpha. Given a sequence alpha, we may construct a new sequence, of n segments of alpha, in such a way that we begin with the segment of the rst n elements of alpha. Next comes the segment of the elements to n and of alpha. In general, we take as the xth element of the new sequence the segment consisting of the elements x to x and n, of alpha. The new sequence so obtained may be called the sequence of the overlapping n segments of alpha. This name indicates that any two consecutive elements, i.e. segments, of the new sequence overlap in such a way that they have n elements of the original sequence alpha in common. Now we can obtain, by selection, other n sequences from a sequence of overlapping segments, especially sequences of adjoining n segments. A sequence of adjoining n segments contains only such n segments as immediately follow each other in alpha without overlapping. It may begin, for example, with the n segments of the elements numbered to n, of the original sequence alpha, followed by that of the elements n and to n, and to n, and so on. In general, a sequence of adjoining segments will begin with the kth element of alpha and its segments will contain the elements of alpha numbered k to n and k to n and k, n and k to n and k, and so on. In what follows, sequences of overlapping n segments of alpha will be denoted by alpha, n, and sequences of adjoining n segments by alpha n. Let us now consider the sequences of overlapping segments alpha, n, a little more closely. Every element of such a sequence is an n segment of alpha. As a primary property of an element of alpha, n, we might consider, for instance, the ordered n tuple of zeros and ones of which the segment consists. Or we could, more simply, regard the number of its ones as the primary property of the element, disregarding the order of the ones and zeros. If we denote the number of ones by m, then, clearly, we have mn. Now from every sequence alpha, n, we again get an alternative if we select a particular m, mn, ascribing the property m to each element of the sequence alpha, n, which has exactly m ones, and therefore n, m zeros, and the property m, non-m, to all other elements of alpha, n. Every element of alpha, n, must then have one or the other of these two properties. Let us now imagine again that we are given a night alternative alpha with the primary properties n 0. Assume that the frequency of the ones, alpha f superscript 2, is equal to p, and that the frequency of the zeros, alpha f superscript 2, 0, is equal to q. We do not assume that the distribution is equal, i.e. that p equals q. n. Now let this alternative alpha be at least n, free, n being an arbitrarily chosen natural number. We can then ask the following question: what is the frequency with which the property m occurs in the sequence alpha n? Or in other words, what will be the value of alpha f superscript 2, m? Without assuming anything beyond the fact that alpha is at least n, free, we can settle this question by elementary arithmetic. The answer is contained in the following formula, the proof of which will be found in Appendix 3. n. Alpha f superscript 2, m, equals ncmpmqn, m. The right-hand side of the binomial formula was given in another connection by Newton. It is therefore sometimes called Newton's formula. I shall call it the RST form of the binomial formula. With the derivation of this formula, I now leave the frequency theory as far as it deals with night reference classes. The formula will provide us with a foundation for our discussion of the axiom of randomness. 57 Infinite sequences. Hypothetical estimates of frequency. It is quite easy to extend the results obtained for n-free night sequences to inite n-free sequences which are deemed by a generating period, cf section. An innate sequence of elements playing the role of the reference class to which our relative frequencies are related may be called a reference sequence. It more or less corresponds to a collective in von Mises's sense. The concept of n-freedom presupposes that of relative frequency, for what its definition requires to be insensitive to selection according to certain predecessors is the relative frequency with which a property occurs. In our theorems dealing with innate sequences I shall employ, but only provisionally, up to section, the idea of a limit of relative frequencies, denoted by f cent, to take the place of relative frequency in innate classes, f superscript 2. The use of this concept gives rise to no problem so long as we can ourselves to reference sequences which are constructed according to some mathematical rule. We can always determine for such sequences whether the corresponding sequence of relative frequencies is convergent or not. The idea of a limit of relative frequencies leads to trouble only in the case of sequences for which no mathematical rule is given, but only an empirical rule, linking, for example the sequence with tosses of a coin, for in these cases the concept of limit is not deemed, cf section. An example of a mathematical rule for constructing a sequence is the following: the nth element of the sequence alpha shall be 0 if, and only if, n is divisible by 4. This means the innate alternative alpha, 0, 0. With the limits of the relative frequencies, alpha f cent, equals slash, and alpha f cent, 0, equals slash. Sequences which are deemed in this way by means of a mathematical rule I shall call, for brevity, mathematical sequences. By contrast, a rule for constructing an empirical sequence would be, for instance, the nth element of the sequence alpha shall be 0 if, and only if, the nth toss of the coin C shows tails. But empirical rules need not always deem sequences of a random character. For example, I should describe the following rule as empirical: the nth element of the sequence shall be if, and only if, the nth second, counting from some 0 instant, and ds the pendulum p to the left of this mark. The example shows that it may sometimes be possible to replace an empirical rule by a mathematical one, for example on the basis of certain hypotheses and measurements relating to some pendulum. In this way, we may nd a mathematical sequence approximating to our empirical sequence with a degree of precision which may or may not satisfy us, according to our purposes. Of particular interest in our present context is the possibility, which our example could be used to establish, of obtaining a mathematical sequence whose various frequencies approximate to those of a certain empirical sequence. In dividing sequences into mathematical and empirical ones I am making use of a distinction that may be called intentional rather than extensional. For if we are given a sequence extensionally, i.e. by listing its elements singly, one after the other so that we can only know a night piece of it, a night segment, however long, then it is impossible to determine, from the properties of the segment, whether the sequence of which it is a part is a mathematical or an empirical sequence. Only when a rule of construction is given, that is, an intentional rule, can we decide whether a sequence is mathematical or empirical. Since we wish to tackle our innate sequences with the help of the concept of a limit, of relative frequencies, we must restrict our investigation to mathematical sequences, and indeed to those for which the corresponding sequence of relative frequencies is convergent. This restriction amounts to introducing an axiom of convergence. The problems connected with this axiom will not be dealt with until sections 2, since it turns out to be convenient to discuss them along with the law of great numbers. Thus we shall be concerned only with mathematical sequences. Yet we shall be concerned only with those mathematical sequences of which we expect, or conjecture, that they approximate, as regards frequencies, to empirical sequences of a chance-like or random character, for these are our main interest. But to expect, or to conjecture, of a mathematical sequence that it will, as regards frequencies, approximate to an empirical one is nothing else than to frame a hypothesis about the frequencies of the empirical sequence. The fact that our estimates of the frequencies in empirical random sequences are hypotheses is without any influence on the way we may calculate these frequencies. Clearly, In connection with night classes, it does not matter in the least how we obtain the frequencies from which we start our calculations. These frequencies may be obtained by actual counting, or from a mathematical rule, or from a hypothesis of some kind or other. Or we may simply invent them. In calculating frequencies we accept some frequencies as given, and derive other frequencies from them. The same is true of estimates of frequencies in innate sequences. Thus the question as to the sources of our frequency estimates is not a problem of the calculus of probability, which, however, does not mean that it will be excluded from our discussion of the problems of probability theory. In the case of innate empirical sequences we can distinguish two main sources of our hypothetical estimates of frequencies, that is to say, two ways in which they may suggest themselves to us. One is an estimate based upon an equal chance hypothesis, or equiprobability hypothesis, the other is an estimate based upon an extrapolation of statistical endings. By an equal chance hypothesis I mean a hypothesis asserting that the probabilities of the various primary properties are equal. It is a hypothesis asserting equal distribution. Equal chance hypotheses are usually based upon considerations of symmetry. A highly typical example is the conjecture of equal frequencies in dicing, based upon the symmetry and geometrical equivalence of the six faces of the cube. For frequency hypotheses based on statistical extrapolation, estimates of rates of mortality provide a good example. Here statistical data about mortality are empirically ascertained, and upon the hypothesis that past trends will continue to be very nearly stable, or that they will not change much at least during the period immediately ahead, an extrapolation to unknown cases is made from known cases, i.e. from occurrences which have been empirically classified and counted. People with inductivist leanings may tend to overlook the hypothetical character of these estimates. They may confuse a hypothetical estimate, i.e. a frequency prediction based on statistical extrapolation, with one of its empirical sources, the classifying and actual counting of past occurrences and sequences of occurrences. The claim is often made that we derive estimates of probabilities, that is, predictions of frequencies, from past occurrences which have been classified and counted, such as mortality statistics. But from a logical point of view there is no justification for this claim. We have made no logical derivation at all. What we may have done is to advance a non-variable hypothesis which nothing can ever justify logically, the conjecture that frequencies will remain constant, and so permit of extrapolation. Even equal chance hypotheses are held to be empirically derivable or empirically explicable by some believers in inductive logic who suppose them to be based upon statistical experience, that is, upon empirically observed frequencies. For my own part I believe, however, that in making this kind of hypothetical estimate of frequency we are often guided solely by our reactions about the significance of symmetry, and by similar considerations. I do not see any reason why such conjectures should be inspired only by the accumulation of a large mass of inductive observations. However, I do not attach much importance to these questions about the origins or sources of our estimates. Cf. section. It is more important, in my opinion, to be quite clear about the fact that every predictive estimate of frequencies, including one which we may get from statistical extrapolation and certainly all those that refer to innate empirical sequences, will always be pure conjecture, since it will always go far beyond anything which we are entitled to arm on the basis of observations. My distinction between equal chance hypotheses and statistical extrapolations corresponds fairly well to the classical distinction between a priori and a posteriori probabilities. But since these terms are used in so many different senses, and since they are, moreover, heavily tainted with philosophical associations, they are better avoided. In the following examination of the axiom of randomness, I shall attempt to nd mathematical sequences which approximate to random empirical sequences, which means that I shall be examining frequency hypotheses. 58. An examination of the axiom of randomness. The concept of an ordinal selection, i.e. of a selection according to position, and the concept of a neighborhood selection, have both been introduced and explained in section. With the help of these concepts I will now examine von Mises's axiom of randomness, the principle of the excluded gambling system, in the hope of ending a weaker requirement which is nevertheless able to take its place. In von Mises's theory this axiom is part of his definition of the concept of a collective. He demands that the limits of frequencies in a collective shall be insensitive to any kind of systematic selection whatsoever. As he points out, a gambling system can always be regarded as a systematic selection. Most of the criticism which has been leveled against this axiom concentrates on a relatively unimportant and superficial aspect of its formulation. It is connected with the fact that, among the possible selections, there will be the selection, say, of those throws which come up VE, and within this selection, obviously, the frequency of the VES will be quite different from what it is in the original sequence. This is why von Mises in his formulation of the axiom of randomness speaks of what he calls selections or choices which are independent of the result of the throw in question, and are thus deemed without making use of the property of the element to be selected. But the many attacks leveled against this formulation can all be answered merely by pointing out that we can formulate von Mises's axiom of randomness without using the questionable expressions at all. For we may put it, for example, as follows: the limits of the frequencies in a collective shall be insensitive both to ordinal and to neighborhood selection, and also to all combinations of these two methods of selection that can be used as gambling systems. With this formulation the above-mentioned difficulties disappear. Others however remain. Thus it might be impossible to prove that the concept of a collective, deemed by means of so strong an axiom of randomness, is not self-contradictory, or in other words, that the class of collectives is not empty. The necessity for proving this has been stressed by Kant. At least it seems to be impossible to construct an example of a collective and in that way to show that collectives exist. This is because an example of an innate sequence which is to satisfy certain conditions can only be given by a mathematical rule. But for a collective in von Mises's sense there can be, by definition, no such rule, since any rule could be used as a gambling system or as a system of selection. This criticism seems indeed unanswerable if all possible gambling systems are ruled out. Against the idea of excluding all gambling systems, another objection may be raised, however, that it really demands too much. If we are going to axiomatize a system of statements, in this case the theorems of the calculus of probability, particularly the special theorem of multiplication or Bernoulli's theorem, then the axioms chosen should not only be sufficient for the derivation of the theorems of the system, but also, if we can make them so, necessary. Yet the exclusion of all systems of selection can be shown to be unnecessary for the deduction of Bernoulli's theorem and its corollaries. It is quite sufficient to demand the exclusion of a special class of neighborhood selection. It suffices to demand that the sequence should be insensitive to selections according to arbitrarily chosen n tuples of predecessors, that is to say, that it should be n free from after x for every n, or more brie, that it should be absolutely free. I therefore propose to replace von Mises's principle of the excluded gambling system by the less exacting requirement of absolute free DOM, in the sense of n freedom for every n, and accordingly to deem chance-like mathematical sequences as those which fulfill this requirement. The chief advantage of this is that it does not exclude all gambling systems, so that it is possible to give mathematical rules for constructing sequences which are absolutely free in our sense, and hence to construct examples. Cf. section A of Appendix 4. Thus Kamp's objection, discussed above, is met. For we can now prove that the concept of chance-like mathematical sequences is not empty, and is therefore consistent. It may seem odd, perhaps, that we should try to trace the highly irregular features of chance sequences by means of mathematical sequences which must conform to the strictest rules. Von Mises's axiom of randomness may seem at RST to be more satisfying to our intuitions. It seems quite satisfying to learn that a chance sequence must be completely irregular, so that every conjectured regularity will be found to fail, in some later part of the sequence, if only we keep on trying hard to falsify the conjecture by continuing the sequence long enough. But this intuitive argument benefits my proposal also. For if chance sequences are irregular, then, a fortiori, they will not be regular sequences of one particular type. And our requirement of absolute freedom does no more than exclude one particular type of regular sequence, though an important one. That it is an important type may be seen from the fact that by our requirement we implicitly exclude the following three types of gambling systems, cf. the next section. First, we exclude normal or pure neighborhood selections, i.e. those in which we select according to some constant characteristic of the neighborhood. Secondly, we exclude normal ordinal selection, which picks out elements whose distance apart is constant, such as the elements numbered k, n and k, and so on. And nally, we exclude many combinations of these two types of selection, for example the selection of every nth element, provided its neighborhood has certain specied constant characteristics. A characteristic property of all these selections is that they do not refer to an absolute RST element of the sequence. They may thus yield the same selected subsequence if the numbering of the original sequence begins with another, appropriate, element. Thus the gambling systems which are excluded by my requirement are those which could be used without knowing the RST element of the sequence. The systems excluded are invariant with respect to certain, linear, transformations. They are the simple gambling systems, cf. section. Only gambling systems which refer to the absolute distances of the elements from an absolute, initial, element are not excluded by my requirement. The requirement of n freedom for every n of absolute freedom also seems to agree quite well with what most of us, consciously or unconsciously, believe to be true of chance sequences. For example, that the result of the next throw of a die does not depend upon the results of preceding throws. The practice of shaking the die before the throw is intended to ensure this independence. 59. Chance-like sequences. Objective probability. In view of what has been said, I now propose the following definition. An event sequence or property sequence, especially an alternative, is said to be chance-like or random if and only if the limits of the frequencies of its primary properties are absolutely free, i.e. insensitive to every selection based upon the properties of any n-tuple of predecessors. A frequency limit corresponding to a sequence which is random is called the objective probability of the property in question. Within the sequence concerned, it is symbolized by f. This may also be put as follows. Let the sequence alpha be a chance-like or random-like sequence with the primary property beta. In this case, the following holds. Alpha f, beta, equals alpha f cent, beta. We shall have to show now that our definition suits for the derivation of the main theorems of the mathematical theory of probability, especially Bernoulli's theorem. Subsequently in section the definition here given will be moded so as to make it independent of the concept of a limit of frequencies. 60. Bernoulli's problem. The RST binomial formula which was mentioned in section, viz. n alpha f superscript 2, m, equals ncmpmqn, m, holds for night sequences of overlapping segments. It is derivable on the assumption that the night sequence alpha is at least n, free. Upon the same assumption, we immediately obtain an exactly corresponding formula for innite sequences, that is to say, if alpha is innite and at least n free, then n alpha f cent, m, equals ncmpmqn, m. Since chance-like sequences are absolutely free, i.e. n free for every n, formula, the second binomial formula, must also apply to them, and it must apply to them, indeed, for whatever value of n we may choose. In what follows, we shall be concerned only with chance-like sequences, or random sequences, as defined in the foregoing section. We are going to show that, for chance-like sequences, a third binomial formula, must hold in addition to formula. It is the formula n alpha f, m, equals ncmpmqn, m. Formula, differs from formula, in two ways. First, it is asserted for sequences of adjoining segments alpha n instead of for sequences of overlapping segments alpha, n. Secondly, it does not contain the symbol f cent but the symbol f. This means that it asserts, by implication, that the sequences of adjoining segments are in their turn chance-like, or random, for f, i.e. objective probability, is deemed only for chance-like sequences. N. The question, answered by, of the objective probability of the property M in a sequence of adjoining segments, i.e. the question of the value of alpha f, M, I call, following von Mises, Bernoulli's problem. For its solution, and hence for the derivation of the third, the corresponding question for sequences of overlapping segments, i.e. the problem of alpha, n, f cent, m, answered by, can be called the quasi-Bernoulli problem, cf. Note to section as well as section. Binomial formula, it is sufficient to assume that alpha is chance-like or random. Our task is equivalent to that of showing that the special theorem of multiplication holds for the sequence of adjoining segments of a random sequence alpha dot. The proof of formula may be carried out in two steps. First, we show that formula holds not only for sequences of overlapping segments alpha, n, but also for sequences of adjoining sequences alpha n. Secondly, we show that the latter are absolutely free. The order of these steps cannot be reversed, because a sequence of overlapping segments alpha, n, is definitely not absolutely free. In fact, a sequence of this kind provides a typical example of what may be called sequences with asterisks. N. First step. Sequences of adjoining segments alpha n are subsequences of alpha, n. They can be obtained from these by normal ordinal selection. Thus, if we can show that the limits of the frequencies in overlapping sequences alpha f cent, m, are insensitive to normal ordinal selection, we have taken our RST step, and even gone a little farther, for we shall have proved the formula n alpha f cent, m, equals alpha f cent, m. I shall RST sketch this proof in the case of n equals, i.e. I shall show that alpha f cent, m, equals alpha f cent, m, a, is true. It will then be easy to generalize this formula for every n. From the sequence of overlapping segments alpha, we can select two. Reichenbach, Axiomatik der Wahrscheinlichkeitsrechnung, Mathematische Zeitschrift. P0, implicitly contests this when he writes, normal sequences are also free from asterisks, whilst the converse does not necessarily hold. But Reichenbach's normal sequences are those for which, holds. My proof is made possible by the fact that I have departed from previous procedure, by denying the concept freedom from asterisks not directly, but with the help of n freedom from asterisks, thus making it accessible to the procedure of mathematical induction. Only a sketch of the proof is here given. Readers not interested in the proof may turn to the last paragraph of the present section. Von Smiluchowski based his theory of the Brownian movement on after-eq sequences, i.e. on sequences of overlapping segments. And only two distinct sequences alpha of adjoining segments, one, which will be denoted by a, contains the RST, third, FTH, segments of alpha, that is, the pairs of alpha consisting of the numbers. The other, denoted by b, contains the second, fourth, sixth, segments of alpha, that is, the pairs of elements of alpha consisting of the numbers, etc. Now assume that formula, a, does not hold for one of the two sequences, a, or, b, so that the segment, i.e. the pair, 0, 0 occurs too often in, say, the sequence, a, then in sequence b, a complementary deviation must occur, that is, the segment 0, 0 will occur not often enough, too often, or not often enough, as compared with the binomial formula. But this contradicts the assumed absolute freedom of alpha. For if the pair 0, 0 occurs in a, more often than in b, then in sufficiently long segments of alpha the pair 0, 0 must appear more often at certain characteristic distances apart than at other distances. The more frequent distances would be those which would obtain if the 0,0 pairs belong to one of the two alpha sequences. The less frequent distances would be those which would obtain if they belong to both alpha sequences. But this would contradict the assumed absolute freedom of alpha, for according to the second binomial formula, the absolute freedom of alpha entails that the frequency with which a particular sequence of the length n occurs in any alpha, n, sequence depends only on the number of ones and zeros occurring in it, and not on their arrangement in the sequence. This proves, a, and since this proof can easily be generalized for any n, the validity of, follows, which completes the RST step of the proof. Second step. The fact that the alpha n sequences are absolutely free can be shown by a very similar argument. Again, we RST consider alpha sequences only, and with respect to these it will only be shown, to start with, that they are free. Assume that one of the two alpha sequences, e.g. the sequence, A, is not free. Then in A, after at least one of the segments consisting of two elements, a particular alpha pair, say after the segment 0,0, another segment, say, must follow more often than would be the case if A were absolutely free. This means that the segment would appear with greater frequency in the subsequence selected from A, according to the predecessor segment 0,0 than the binomial formula would lead us to expect. This assumption, however, contradicts the absolute freedom of the sequence alpha. For if the segment follows in A, the segment 0,0 too frequently, then, by way of compensation, the converse must take place in B, for otherwise the quadruple 0,0 would, in a sufficiently long segment of alpha, occur too often at certain characteristic distances apart, namely at the distances which would obtain if the double pairs in question belong to one and the same alpha sequence. Moreover, at other characteristic distances the quadruple would occur not often enough at those distances, namely, which would obtain if they belong to both alpha sequences. Thus we are confronted with precisely the same situation as before, and we can show, by analogous considerations, that the assumption of a preferential occurrence at characteristic distances is incompatible with the assumed absolute freedom of alpha. This proof can again be generalized, so that we may say of alpha sequences that they are not only free but n-free for every n, and hence that they are chance-like, or random. This completes our sketch of the two steps. Thus we are now entitled to replace, in, f sent by f, and this means that we may accept the claim that the third binomial formula solves Bernoulli's problem. Incidentally, we have shown that sequences alpha, n, of overlapping segments are insensitive to normal ordinal selection whenever alpha is absolutely free. The same is also true for sequences alpha n of adjoining segments, because every normal ordinal selection from alpha n can be regarded as a normal ordinal selection from alpha n, and it must therefore apply to the sequence alpha itself, since alpha is identical with both alpha and alpha. We have thus shown, among other things, that from absolute freedom, which means insensitiveness to a special type of neighborhood selection, insensitiveness to normal ordinal selection follows. A further consequence, as can easily be seen, is insensitiveness to any pure neighborhood selection, that is, selection according to a constant characterization of its neighborhood, a characterization that does not vary with the ordinal number of the element. And it follows, nally, that absolute freedom will entail insensitivity to all combinations of these two types of selection. 61. The law of great numbers, Bernoulli's theorem. Bernoulli's theorem, or the RST, law of great numbers, can be derived from the third binomial formula by purely arithmetical reasoning, under the assumption that we can take n to the limit, n registered trademark yen. It can therefore be asserted only of inite sequences alpha, for it is only in these that the n segments of alpha n sequences can increase in length indefinitely. And it can be asserted only of such sequences alpha as are absolutely free, for it is only under the assumption of n freedom for every n that we can take n to the limit, n registered trademark yen. N. Bernoulli's theorem provides the solution of a problem which is closely akin to the problem which, Following von Mises, I have called Bernoulli's problem, viz. The problem of the value of alpha f, m. As indicated in section, an n segment may be said to have the property m when it contains precisely m ones. The relative frequency of ones within this night segment is then, of course, m/n. We may now deem an n segment of alpha has the property p if and only if the relative frequency of its ones deviates by less than delta from the value alpha f equals p, i.e. the probability of ones in the sequence alpha. Here, delta is any small fraction, chosen as near to zero as we like, but different from zero. We can express this condition by saying, an n segment has the m property p if and only if n p delta, otherwise, the segment has the property p. Now Bernoulli's theorem answers the question of the value of the frequency, or probability, of segments of this kind of n segments possessing the property p within the alpha n sequences. It thus answers the question of the value of alpha f, p, n. Intuitively one might guess that if the value delta, with delta 0, is xed, and if n increases, then the frequency of these segments with the property p, and therefore the value of alpha f, p, will also increase, and that its increase will be monotonic. Bernoulli's proof, which can be found in any textbook on the calculus of probability, proceeds by evaluating this increase with the help of the binomial formula. He nds that if n increases without limit, the value of alpha f, p, approaches the maximal value, for any xed value of delta, however small. This may be expressed in symbols by lim alpha nf, p, equals, for any value of p. N registered trademark yen. This formula results from transforming the third binomial formula for sequences of adjoining segments. The analogous second binomial formula for sequences of overlapping segments would immediately lead, by the same method, to the corresponding formula. Lim alpha, n, f cent, p, equals n registered trademark yen. Which is valid for sequences of overlapping segments and normal ordinal selection from them, and hence for sequences with aftereaks, which have been studied by Smoluchowski. Formula, itself yields, in case sequences are selected which do not overlap, and which are therefore n-free. May be described as a variant of Bernoulli's theorem, and what I am going to say here about Bernoulli's theorem applies mutatis mutandis to this variant. Bernoulli's theorem, i.e. formula, may be expressed in words as follows. Let us call a long night segment of some xed length, selected from a random sequence alpha, a fair sample if, and only if, the frequency of the ones within this segment deviates from p, i.e. the value of the probability of the ones within the random sequence alpha, by no more than some small xed fraction, which we may freely choose. We can then say that the probability of chancing upon a fair sample approaches as closely as we like if only we make the segments in question sufficiently long. In this formulation the word probability, or value of the probability, occurs twice. How is it to be interpreted or translated here? In the sense of my frequency definition it would have to be translated as follows. I italicize the two translations of the word probability into the frequency language. The overwhelming majority of all sufficiently long night segments will be fair samples, that is to say, their relative frequency will deviate from the frequency value p of the random sequence in question by an arbitrarily xed small amount, or, more brie, the frequency p is realized, approximately, in almost all sufficiently long segments. How we arrive at the value p is irrelevant to our present discussion. It may be, say, the result of a hypothetical estimate. N. Bearing in mind that the Bernoulli frequency alpha f, p, increases monotonically with the increasing length n of the segment and that it decreases monotonically with decreasing n, and that, therefore, the value of the relative frequency is comparatively rarely realized in short segments, we can also say Bernoulli's theorem states that short segments of absolutely free or chance-like sequences will often show relatively great deviations from P and thus relatively great fluctuations, while the longer segments, in most cases, will show smaller and smaller deviations from P with increasing length. Consequently, most deviations in sufficiently long segments will become as small as we like, or in other words, great deviations will become as rare as we like. Accordingly, if we take a very long segment of a random sequence, in order to ND the frequencies within its subsequences by counting, or perhaps by the use of other empirical and statistical methods, then we shall get, in the vast majority of cases, the following result. There is a characteristic average frequency, such that the relative frequencies in the whole segment, and in almost all long subsegments, will deviate only slightly from this average, whilst the relative frequencies of smaller subsegments will deviate further from this average, and the more often, the shorter we choose them. This fact, this statistically ascertainable behavior of night segments, may be referred to as their quasi-convergent behavior, or as the fact that random sequences are statistically stable. Thus Bernoulli's theorem asserts that the smaller segments of chance-like sequences often show large fluctuations, whilst the large segments always behave in a manner suggestive of constancy or convergence, in short, that we ND disorder and randomness in the small, order and constancy in the great. It is this behavior to which the expression the law of great numbers refers. 62 Bernoulli's theorem and the interpretation of probability statements. We have just seen that in the verbal formulation of Bernoulli's theorem the word probability occurs twice. The frequency theorist has no difficulty in translating this word. In both cases, in accordance with its definition, he can give a clear interpretation of Bernoulli's formula and the law of great numbers. Can the adherent of the subjective theory in its logical form do the same? The subjective theorist who wants to deem probability as degree of rational belief is perfectly consistent, and within his rights, when he interprets the words the probability of approaches to I as closely as we like as meaning, it is almost certain that but he merely obscures his difficulties when he continues that the relative frequency will deviate from its most probable value P by less than a given amount, or in the words of Keynes, that the proportion of the event's occurrences will diverge from the most probable proportion P by less than a given amount. This sounds like good sense, at least on RST hearing. But if here too we translate the word probable, sometimes suppressed, in the sense of the subjective theory, then the whole story runs. It is almost certain that the relative frequencies deviate from the value P of the degree of rational belief by less than a given amount, which seems to me complete nonsense. For relative frequencies can be compared only with relative frequencies, and can deviate or not deviate only from relative frequencies. And clearly, it must be inadmissible to give after the deduction of Bernoulli's theorem a meaning to P different from the one which was given to it before the deduction. Thus we see that the subjective theory is incapable of interpreting Bernoulli's formula in terms of the statistical law of great numbers. Derivation of statistical laws is possible only within the framework of the frequency theory. If we start from a strict subjective theory, we shall never arrive at statistical statements, not even if we try to bridge the gulf with Bernoulli's theorem. 63 Bernoulli's theorem and the problem of convergence. From the point of view of epistemology, my deduction of the law of great numbers, outlined above, is unsatisfactory, for the part played in our analysis by the axiom of convergence is far from clear. I have tacitly introduced an axiom of this kind, by conning my investigation to mathematical sequences with frequency limits. Cf. section. Consequently, one might even be tempted to think that our result, the derivation of the law of great numbers, is trivial, for the fact that absolutely free sequences are statistically stable might be regarded as entailed by their convergence, which has been assumed axiomatically, if not implicitly. But this view would be mistaken, as von Mises has clearly shown. For there are sequences which satisfy the axiom of convergence, although Bernoulli's theorem does not hold for them, since with a frequency close to, segments of any length occur in them which may deviate from P to any extent. The existence of the limit P is in these cases due to the fact that the deviations, although they may increase without limit, cancel each other. Such sequences look as if they were divergent in arbitrarily large segments, even though the corresponding frequency sequences are in fact convergent. Thus the law of great numbers is anything but a trivial consequence of the axiom of convergence, and this axiom is quite insouciant for its deduction. This is why my modi axiom of randomness, the requirement of absolute freedom, cannot be dispensed with. Our reconstruction of the theory, however, suggests the possibility that the law of great numbers may be independent of the axiom of convergence. For we have seen that Bernoulli's theorem follows immediately from the binomial formula. Moreover, I have shown that the RST binomial formula can be derived for night sequences and so, of course, without any axiom of convergence. All that had to be assumed was that the reference sequence alpha was at least n, free, an assumption from which the validity of the special multiplication theorem followed, and with it that of the RST binomial formula. In order to make the transition to the limit, and to obtain Bernoulli's theorem, it is only necessary to assume that we may make n as large as we like. From this it can be seen that Bernoulli's theorem is true, approximately, even for night sequences, if they are n-free for an n which is sufficiently large. It seems therefore that the deduction of Bernoulli's theorem does not depend upon an axiom postulating the existence of a frequency limit, but only on absolute freedom or randomness. The limit concept plays only a subordinate role. It is used for the purpose of applying some conception of relative frequency, which, in the RST instance, is only deemed for night classes, and without which the concept of n-freedom cannot be formulated, to sequences that can be continued indefinitely. Moreover, it should not be forgotten that Bernoulli himself deduced his theorem within the framework of the classical theory, which contains no axiom of convergence, also, that the definition of probability as a limit of frequencies is only an interpretation and not the only possible one of the classical formalism. I shall try to justify my conjecture the independence of Bernoulli's theorem of the axiom of convergence by deducing this theorem without assuming anything except n-freedom, to be appropriately deemed. And I shall try to show that it holds even for those mathematical sequences whose primary properties possess no frequency limits. Only if this can be shown shall I regard my deduction of the law of great numbers as satisfactory from the point of view of the epistemologist. For it is a fact of experience, or so at least we are sometimes told, that chance-like empirical sequences show that peculiar behavior which I have described as quasi-convergent or statistically stable. Cf. section. By recording statistically the behavior of long segments, one can establish that the relative frequencies approach closer and closer to a d-night value, and that the intervals within which the relative frequencies fluctuate become smaller and smaller. This so-called empirical fact, so much discussed and analyzed, which is indeed often regarded as the empirical corroboration of the law of great numbers, can be viewed from various angles. Thinkers with inductivist leanings mostly regard it as a fundamental law of nature, not reducible to any simpler statement, as a peculiarity of our world which has simply to be accepted. They believe that expressed in a suitable form, for example in the form of the axiom of convergence, this law of nature should be made the basis of the theory of probability, which would thereby assume the character of a natural science. My own attitude to this so-called empirical fact is different. I am inclined to believe that it is reducible to the chance-like character of the sequences, that it may be derived from the fact that these sequences are n-free. I see the great achievement of Bernoulli and Poisson in the eld of probability theory precisely in their discovery of a way to show that this alleged fact of experience is a tautology, and that from disorder in the small, provided it satisfies a suitably formulated condition of n-freedom, there follows logically a kind of order of stability in the large. If we succeed in deducing Bernoulli's theorem without assuming an axiom of convergence, then we shall have reduced the epistemological problem of the law of great numbers to one of axiomatic independence, and thus to a purely logical question. This deduction would also explain why the axiom of convergence works quite well in all practical applications, in attempts to calculate the approximate behavior of empirical sequences. For even if the restriction to convergent sequences should turn out to be unnecessary, it can certainly not be inappropriate to use convergent mathematical sequences for calculating the approximate behavior of empirical sequences which, on logical grounds, are statistically stable. 64. Elimination of the axiom of convergence. Solution of the fundamental problem of the theory of chance. So far, frequency limits have had no other function in our reconstruction of the theory of probability than that of providing an unambiguous concept of relative frequency applicable to innate sequences, so that with its help we may deem the concept of absolute freedom, from after x. For it is a relative frequency which is required to be insensitive to selection according to predecessors. Earlier we restricted our inquiry to alternatives with frequency limits, thus tacitly introducing an axiom of convergence. Now, so as to free us from this axiom, I shall remove the restriction without replacing it by any other. This means that we shall have to construct a frequency concept which can take over the function of the discarded frequency limit, and which may be applied to all innate reference sequences. One frequency concept fooling these conditions is the concept of a point of accumulation of the sequence of relative frequencies. A value is said to be a point of accumulation of a sequence if after any given element there are elements deviating from a by less than a given amount, however small. That this concept is applicable without restriction to all innate reference sequences may be seen from the fact that for every innate alternative at least one such point of accumulation must exist for the sequence of relative frequencies which corresponds to it. Since relative frequencies can never be greater than nor less than 0, a sequence of them must be bounded by n0. And as an innate bounded sequence, it must, according to a famous theorem of Bolzano and Weierstrass, have at least one point of accumulation. For brevity, every point of accumulation of the sequence of relative frequencies corresponding to an alternative alpha will be called a middle frequency of alpha. We can then say, if a sequence alpha has one and only one middle frequency, then this is at the same time its frequency limit, and conversely, if it has no frequency limit, then it has more than one middle frequency. The idea of a middle frequency will be found very suitable for our purpose. Just as previously it was our estimate, perhaps a hypothetical estimate, that p was the frequency limit of a sequence alpha, so we now work with the estimate that p is a middle frequency of alpha. And provided we take certain necessary precautions, we can make calculations with the help of these estimated middle frequencies, in a way analogous to that in which we calculate with frequency limits. Moreover, the concept of middle frequency is applicable to all possible innate reference sequences, without any restriction. If we now try to interpret our symbol alpha f cent, beta, as a middle frequency, rather than a frequency limit, and if we accordingly alter the definition of objective probability, section, most of our formulae will still be derivable. One difficulty arises, however: middle frequencies are not unique. If we estimate or conjecture that a middle frequency is alpha f cent, beta, equals p, then this does not exclude the possibility that there are values of alpha f cent, beta, other than p. If we postulate that this shall not be so, we thereby introduce, by implication, the axiom of convergence. If on the other hand we deem objective probability without such a postulate of uniqueness, then we obtain, in the RST instance, at least, a concept of probability which is ambiguous, for under certain circumstances a sequence may possess at the same time several middle frequencies which are absolutely free, cf section C of Appendix 4. But this is hardly acceptable, since we are accustomed to work with unambiguous or unique probabilities, to assume, that is to say, that for one and the same property there can be one and only one probability p, within one and the same reference sequence. However, the difficulty of defining a unique probability concept without the limit axiom can easily be overcome. We may introduce the requirement of uniqueness, as is, after all, the most natural procedure, as the last step, after having postulated that the sequence shall be absolutely free. This leads us to propose, as a solution of our problem, the following modification of our definition of chance-like sequences, and of objective probability. Let alpha be an alternative, with one or several middle frequencies. Let the ones of alpha have one and only one middle frequency p that is absolutely free, then we say that alpha is chance-like or random, and that p is the objective probability of the ones within alpha. It will be helpful to divide this definition into two axiomatic requirements. 1. Requirement of randomness: for an alternative to be chance-like, there must be at least one absolutely free middle frequency, i.e. its objective probability p. 2. Requirement of uniqueness: for one and the same property of one and the same chance-like alternative, there must be one and only one probability p. The consistency of the new axiomatic system is ensured by the example previously constructed. It is possible to construct sequences which, whilst they have one and only one probability, yet possess no frequency limit, cf. section B of Appendix 4. This shows that the new axiomatic demands are actually wider, or less exacting, than the old ones. This fact will become even more evident if we state, as we may, our old axioms in the following form. 1. Requirement of randomness, as above. 2. Requirement of uniqueness, as above. Cent. Axiom of convergence: for one and the same property of one and the same chance-like alternative there exists no further middle frequency apart from its probability p. From the proposed system of requirements we can deduce Bernoulli's theorem, and with it all the theorems of the classical calculus of probability. This solves our problem. It is now possible to deduce the law of great numbers within the framework of the frequency theory without using the axiom of convergence. Moreover, not only does the formula of section and the verbal formulation of Bernoulli's theorem remain unchanged, but the interpretation we have given to it also remains unchanged. In the case of a chance-like sequence without a frequency limit, it will still be true that almost all sufficiently long sequences show only small deviations from p. In such sequences, as in chance-like sequences with frequency limits, segments of any length behaving quasi-divergently will of course occur at times, i.e. segments which deviate from p by any amount. But such segments will be comparatively rare, since they must be compensated for by extremely long parts of the sequence in which all, or almost all, segments behave quasi-convergently. As calculation shows, these stretches will have to be longer by several orders of magnitude, as it were, than the divergently behaving segments for which they compensate. This is also the place to solve the fundamental problem of the theory of chance, as it was called in section. The seemingly paradoxical inference from the unpredictability and irregularity of singular events to the applicability of the rules of the probability calculus to them is indeed valid. It is valid provided we can express the irregularity, with a fair degree of approximation, in terms of the hypothetical assumption that one only of the recurring frequencies of the middle frequencies so occurs in any selection according to predecessors that no after x result. For upon these assumptions it is possible to prove that the law of great numbers is tautological. It is admissible and not self-contradictory, as has sometimes been asserted, to uphold the conclusion that in an irregular sequence in which, as it were, anything may happen at one time or another, though some things only rarely, a certain regularity or stability will appear in very large subsequences. Nor is this conclusion trivial, since we need for its specific mathematical tools, the Boltzano and Weierstrass theorem, the concept of n-freedom, and Bernoulli's theorem. The apparent paradox of an argument from unpredictability to predictability, or from ignorance to knowledge, disappears when we realize that the assumption of irregularity can be put in the form of a frequency hypothesis, that of freedom from after x, and that it must be put in this form if we want to show the validity of that argument. It now also becomes clear why the older theories have been unable to do justice to what I call the fundamental problem. The subjective theory, admittedly, can deduce Bernoulli's theorem, but it can never consistently interpret it in terms of frequencies, after the fashion of the law of great numbers, cf. section. Thus it can never explain the statistical success of probability predictions. On the other hand, the older frequency theory, by its axiom of convergence, explicitly postulates regularity in the large. Thus within this theory the problem of inference from irregularity in the small to stability in the large does not arise, since it merely involves inference from stability in the large, axiom of convergence, coupled with irregularity in the small, axiom of randomness, to a special form of stability in the large, Bernoulli's theorem, law of great numbers. The axiom of convergence is not a necessary part of the foundations of the calculus of probability. With this result I conclude my analysis of the mathematical calculus. We now return to the consideration of more distinctively methodological problems, especially the problem of how to decide probability statements. 65. The problem of decidability. In whatever way we may deem the concept of probability, or whatever axiomatic formulations we choose, so long as the binomial formula is derivable within the system, probability statements will not be falsifiable. Probability hypotheses do not rule out anything observable, probability estimates cannot contradict, or be contradicted by, a basic statement, nor can they be contradicted by a conjunction of any night number of basic statements, and accordingly not by any night number of observations either. Let us assume that we have proposed an equal chance hypothesis for some alternative alpha, for example, that we have estimated that tosses with a certain coin will come up and zero with equal frequency, so that f equals f, 0, equals, and let us assume that we nd, empirically, that alpha alpha comes up over and over again without exception, then we shall, no doubt, abandon our estimate in practice, and regard it as falsified. But there can be no question of falsification in a logical sense. For we can surely observe only a night sequence of tosses. And although, according to the binomial formula, the probability of chancing upon a very long night segment with great deviations from is exceedingly small, it must yet always remain greater than 0. A sufficiently rare occurrence of a night segment with even the greatest deviation can thus never contradict the estimate. In fact, we must expect it to occur. This is a consequence of our estimate. The hope that the calculable rarity of any such segment will be a means of falsifying the probability estimate proves illusory, since even a frequent occurrence of a long and greatly deviating segment may always be said to be nothing but one occurrence of an even longer and more greatly deviating segment. Thus there are no sequences of events, given to us extensionally, and therefore no night n-tuple of basic statements, which could falsify a probability statement. Only an innate sequence of events deemed intentionally by a rule could contradict a probability estimate. But this means, in view of the considerations set forth in section, cf section, that probability hypotheses are unfalsifiable because their dimension is innate. We should therefore really describe them as empirically uninformative, as void of empirical content. Yet any such view is clearly unacceptable in face of the successes which physics has achieved with predictions obtained from hypothetical estimates of probabilities. This is the same argument as has been used here much earlier against the interpretation of probability statements as tautologies by the subjective theory. Many of these estimates are not inferior in scientific significance to any other physical hypothesis, for example, to one of a determinist character. And a physicist is usually quite well able to decide whether he may for the time being accept some particular probability hypothesis as empirically confirmed, or whether he ought to reject it as practically falsified, i.e., as useless for purposes of prediction. It is fairly clear that this practical falsification can be obtained only through a methodological decision to regard highly improbable events as ruled out as prohibited. But with what right can they be so regarded? Where are we to draw the line? Where does this high improbability begin? Since there can be no doubt, from a purely logical point of view, about the fact that probability statements cannot be falsified, the equally indubitable fact that we use them empirically must appear as a fatal blow to my basic ideas on method, which depend crucially upon my criterion of demarcation. Nevertheless, I shall try to answer the questions I have raised, which constitute the problem of decidability, by a resolute application of these very ideas. But to do this, I shall have to analyze the logical form of probability statements, taking account both of the logical interrelations between them and of the logical relations in which they stand to basic statements. 66. The logical form of probability statements. Probability estimates are not falsifiable. Neither, of course, are they variable, and this for the same reasons as hold for other hypotheses, seeing that no experimental results, however numerous and favorable, can ever nally establish that the relative frequency of heads is, and will always be. Probability statements and basic statements can thus neither contradict one another nor entail one another. And yet, it would be a mistake to conclude from this that no kind of logical relations hold between probability statements and basic statements. And it would be equally wide of the mark to believe that while logical relations do obtain between statements of these two kinds, since sequences of observations may obviously agree more or less closely with a frequency statement, the analysis of these relations compels us to introduce a special probabilistic logic which breaks the fetters of classical logic. In opposition to such views, I believe that the relations in question can be fully analyzed in terms of the classical logical relations of deducibility and contradiction. From the non-falsiability and non-variability of probability statements, it can be inferred that they have no falsifiable consequences, and that they cannot themselves be consequences of variable statements. But the converse possibilities are not excluded. For it may be, a. that they have unilaterally variable consequences, purely existential consequences, or there is consequences, or, b. that they are themselves consequences of unilaterally falsifiable universal statements, all statements. Possibility, b. will scarcely help to clarify the logical relation between probability statements and basic statements. It is only too obvious that a non-falsifiable statement, i.e. one which says very little, can belong to the consequence class of one which is falsifiable, and which thus says more. What is of greater interest for us is possibility, a. which is by no means trivial, and which in fact turns out to be fundamental for our analysis of the relation between probability statements and basic statements. For we know that from every probability statement, an innate class of existential statements can be deduced, but not vice versa. Thus the probability statement asserts more than does any of these existential statements. For example, let P be a probability which has been estimated, hypothetically, for a certain alternative, and let 0 superscript 1 P superscript 1, then we can deduce from this estimate, for instance, the existential consequence that both ones and zeros will occur in the sequence. Of course, many far less simple consequences also follow, for example, that segments will occur which deviate from P only by a very small amount. But we can deduce much more from this estimate, for example that there will over and over again be an element with the property and another element with the property O, that is to say, that after any element X there will occur in the sequence an element Y with the property, and also an element Z with the property O. A statement of this form, for every X there is a Y with the observable, or extensionally testable, property beta, is both non-falsifiable because it has no falsifiable consequences and non-variable because of the all or for every which made it hypothetical. Nevertheless, it can be better, or less well confirmed in the sense that we may succeed in verifying many, few, or none of its existential consequences. Thus it stands to the basic statement in the relation which appears to be characteristic of probability statements. Statements of the above form may be called universalized existential statements or universalized existential hypotheses. My contention is that the relation of probability estimates to basic statements, and the possibility of their being more, or less, well confirmed, can be understood by considering the fact that from all probability estimates, existential hypotheses are logically deducible. This suggests the question whether the probability statements themselves may not, perhaps, have the form of existential hypotheses. Every hypothetical probability estimate entails the conjecture that the empirical sequence in question is, approximately, chance-like or random. That is to say, it entails the approximate applicability and the truth of the axioms of the calculus of probability. Our question is, therefore, equivalent to the question whether these axioms represent what I have called existential hypotheses. If we examine the two requirements proposed in section, then we see that the requirement of randomness has in fact the form of an existential hypothesis. The requirement of uniqueness, on the other hand, has not this form. It cannot have it, since a statement of the form "there is only one" must have the form of a universal statement. It can be translated as "there are not more than one" or "all are identical." Now it is my thesis here that it is only the existential constituent, as it might be called, of probability estimates, and therefore the requirement of randomness, which establishes a logical relation between them and basic statements. Accordingly, the requirement of uniqueness, as a universal statement, would have no extensional consequences whatever. That a value p with the required properties exists, can indeed be extensionally confirmed, though of course only provisionally, but not that only one such value exists. This latter statement, which is universal, could be extensionally significant only if basic statements could contradict it, that is to say, if basic statements could establish the existence of more than one such value. Since they cannot, for we remember that non-falsiability is bound up with the binomial formula, the requirement of uniqueness must be extensionally without significance. This is the reason why the logical relations holding between a probability estimate and basic statements, and the graded confirmability of the former, are unacted if we eliminate the requirement of uniqueness from the system. By doing this we could give the system the form of a pure existential hypothesis. But we should then have to give up the uniqueness of probability estimates, and thereby, so far as uniqueness is concerned, obtain something different from the usual calculus of probability. Therefore the requirement of uniqueness is obviously not superfluous. What, then, is its logical function? Whilst the requirement of randomness helps to establish a relation between probability statements and basic statements, the requirement of uniqueness regulates the relations between the various probability statements themselves. Without the requirement of uniqueness, some of these might, as existential hypotheses, be derivable from others, but they could never contradict one another. Only the requirement of uniqueness ensures that probability statements can contradict one another, for by this requirement they acquire the form of a conjunction whose components are a universal statement and an existential hypothesis, and statements of this form can stand to one another in exactly the same fundamental logical relations, equivalence, derivability, compatibility, and incompatibility, as can normal universal statements of any theory, for example, a falsifiable theory. If we now consider the axiom of convergence, then we see that it is like the requirement of uniqueness in that it has the form of a non-falsifiable universal statement. But it demands more than our requirement does. This additional demand, however, cannot have any extensional significance either. Moreover, it has no logical or formal but only an intentional significance. It is a demand for the exclusion of all intentionally deemed, i.e. mathematical, sequences without frequency limits. But from the point of view of applications, this exclusion proves to be without significance even intentionally, since in applied probability theory we do not of course deal with the mathematical sequences themselves but only with hypothetical estimates about empirical sequences. The exclusion of sequences without frequency limits could therefore only serve to warn us against treating those empirical sequences as chance-like or random, of which we hypothetically assume that they have no frequency limit. But what possible action could we take in response to this warning? What sort of considerations or conjectures about the possible convergence or divergence of empirical sequences should we indulge in or abstain from, in view of this warning, seeing that criteria of convergence are no more applicable to them than are criteria of divergence? All these embarrassing questions disappear once the axiom of convergence has been got rid of. Our logical analysis thus makes transparent both the form and the function of the various partial requirements of the system, and shows what reasons tell against the axiom of randomness and in favor of the requirement of uniqueness. Meanwhile, the problem of decidability seems to be growing ever more menacing. And although we are not obliged to call our requirements, or axioms, meaningless, it looks as if we were compelled to describe them as non-empirical. But does not this description of probability statements, no matter what words we use to express it, contradict the main idea of our approach? 67. A probabilistic system of speculative metaphysics. The most important use of probability statements in physics is this: certain physical regularities or observable physical eqs are interpreted as macro laws, that is to say, they are interpreted, or explained, as mass phenomena, or as the observable results of hypothetical and not directly observable micro events. The macro laws are deduced from probability estimates by the following method. We show that observations which agree with the observed regularity in question are to be expected with a probability very close to, i.e. with a probability which deviates from by an amount which can be made as small as we choose. When we have shown this, then we say that by our probability estimate we have explained the observable eqt in question as a macro eqt. But if we use probability estimates in this way for the explanation of observable regularities without introducing special precautions, then we may immediately become involved in speculations which in accordance with general usage can well be described as typical of speculative metaphysics. For since probability statements are not falsifiable, it must always be possible in this way to explain, by probability estimates, any regularity we please. Take, for example, the law of gravity. We may contrive hypothetical probability estimates to explain this law in the following way. We select events of some kind to serve as elementary or atomic events, for instance the movement of a small particle. We select also what is to be a primary property of these events, for instance the direction and velocity of the movement of a particle. We then assume that these events show a chance-like distribution. Finally, we calculate the probability that all the particles within a certain night spatial region, and during a certain night period of time a certain cosmic period will with a specious accuracy move, accidentally, in the way required by the law of gravity. The probability calculated will, of course, be very small, negligibly small, in fact, but still not equal to zero. Thus we can raise the question how long an n segment of the sequence would have to be, or in other words, how long a duration must be assumed for the whole process, in order that we may expect, with a probability close to, or deviating from by not more than an arbitrarily small value epsilon, the occurrence of one such cosmic period in which, as the result of an accumulation of accidents, our observations will all agree with the law of gravity. For any value as close to as we choose, we obtain a d-night, though extremely large, night number. We can then say, if we assume that the segment of the sequence has this very great length, or in other words, that the world lasts long enough, then our assumption of randomness entitles us to expect the occurrence of a cosmic period in which the law of gravity will seem to hold good, although in reality nothing ever occurs but random scattering. This type of explanation by means of an assumption of randomness is applicable to any regularity we choose. In fact, we can in this way explain our whole world, with all its observed regularities, as a phase in a random chaos, as an accumulation of purely accidental coincidences. It seems clear to me that speculations of this kind are metaphysical, and that they are without any significance for science. And it seems equally clear that this fact is connected with their non-falsifiability with the fact that we can always and in all circumstances indulge in them. My criterion of demarcation thus seems to agree here quite well with the general use of the word metaphysical. Theories involving probability, therefore, if they are applied without special precautions, are not to be regarded as scientific. We must rule out their metaphysical use if they are to have any use in the practice of empirical science. 68. Probability in physics. The problem of decidability troubles only the methodologist, not the physicist. If asked to produce a practically applicable concept of probability, the physicist might perhaps offer something like a physical definition of probability, on lines such as the following: there are certain experiments which, even if carried out under controlled conditions, lead to varying results. In the case of some of these experiments, those which are chance-like, such as tosses of a coin, frequent repetition leads to results with relative frequencies which, upon further repetition, approximate more and more to some xed value which we may call the probability of the event in question. This value is empirically determinable through long series of experiments to any degree of approximation, which explains, incidentally, why it is possible to falsify a hypothetical estimate of probability. Against definitions on these lines both mathematicians and logicians will raise objections, in particular the following. 1. The definition does not agree with the calculus of probability since, according to Bernoulli's theorem, only almost all very long segments are statistically stable, i.e. behave as if convergent. For that reason, probability cannot be defined by this stability, i.e. by quasi-convergent behavior. For the expression almost all which ought to occur in the definitions is itself only a synonym for very probable. The definition is thus circular, a fact which can be easily concealed, but not removed, by dropping the word almost. This is what the physicist's definition did, and it is therefore unacceptable. 2. When is a series of experiments to be called long? Without being given a criterion of what is to be called long, we cannot know when, or whether, we have reached an approximation to the probability. 3. How can we know that the desired approximation has in fact been reached? Although I believe that these objections are justified, I nevertheless believe that we can retain the physicist's definition. I shall support this belief by the arguments outlined in the previous section. These showed that probability hypotheses lose all informative content when they are allowed unlimited application. The physicist would never use them in this way. Following his example, I shall disallow the unlimited application of probability hypotheses. I propose that we take the methodological decision never to explain physical eaks, i.e. reproducible regularities, as accumulations of accidents. This decision naturally modifies the concept of probability, it narrows it. Thus objection does not eke my position, for I do not assert the identity of the physical and the mathematical concepts of probability at all, on the contrary, I deny it. But in place of, a new objection arises. Cent, when can we speak of accumulated accidents? Presumably in the case of a small probability. But when is a probability small? We may take it that the proposal which I have just submitted rules out the use of the method, discussed in the preceding section, of manufacturing an arbitrarily large probability out of a small one by changing the formulation of the mathematical problem. But in order to carry out the proposed decision, we have to know what we are to regard as small. In the following pages it will be shown that the proposed methodological rule agrees with the physicist's definition, and that the objections raised by questions, sent, and, can be answered with its help. To begin with, I have in mind only one typical case of the application of the calculus of probability. I have in mind the case of certain reproducible macro eaks which can be described with the help of precise, macro, laws such as gas pressure, and which we interpret, or explain, as due to a very large accumulation of microprocesses, such as molecular collisions. Other typical cases, such as statistical fluctuations or the statistics of chance like individual processes, can be reduced without much difficulty to this case. N. Let us take a macro eak of this type, described by a well-corroborated law, which is to be reduced to random sequences of micro-events. Let the law assert that under certain conditions a physical magnitude has the value p. We assume the eak to be precise, so that no measurable fluctuations occur, i.e. no deviations from p beyond that interval, plus or minus phi, the interval of imprecision, cf section, within which our measurements will in any case fluctuate, owing to the imprecision inherent in the prevailing technique of measurement. We now propose the hypothesis that p is a probability within a sequence alpha of micro-events, and further, that n micro-events contribute towards producing the eaked. Then, cf section, we can calculate for every chosen value delta, the probability alpha f, p, i.e. the probability that the value measured will fall within the interval p. The complementary probability may be denoted by epsilon. Thus we have alpha f, p, equals epsilon. According to Bernoulli's theorem, epsilon tends to 0 as n increases without limit. We assume that epsilon is so small that it can be neglected. Question, cent, which concerns what small means, in this assumption, will be dealt with soon. The p is to be interpreted, clearly, as the interval within which the measurements approach the value p. From this we see that the three quantities, epsilon, n, and p correspond to the three questions, cent, and p or delta can be chosen arbitrarily, which restricts the arbitrariness of our choice of epsilon and n. Since it is our task to deduce the exact macro eq p, plus or minus phi, we shall not assume delta to be greater than phi. As far as the reproducible eq p is concerned, the deduction will be satisfactory if we can carry it out for some value delta phi. Here phi is given, since it is determined by the measuring technique. Now let us choose delta so that it is, approximately, equal to phi. Then we have reduced question, to the two other questions, cent, and. By the choice of delta, i.e. of p, we have established a relation between n and epsilon, since to every n there now corresponds uniquely a value of epsilon. Thus, i.e. the question when is n sufficiently long, has been reduced to cent, i.e. the question when is epsilon small, and vice versa. But this means that all three questions could be answered if only we could decide what particular value of epsilon is to be neglected as negligibly small. Now our methodological rule amounts to the decision to neglect small values of epsilon, but we shall hardly be prepared to commit ourselves forever to a finite value of epsilon. If we put our question to a physicist, that is, if we ask him what epsilon he is prepared to neglect 0.00, or 0.00000, or he will presumably answer that epsilon does not interest him at all, that he has chosen not epsilon but n, and that he has chosen n in such a way as to make the correlation between n and p largely independent of any changes of the value epsilon which we might choose to make. The physicist's answer is just id, because of the mathematical peculiarities of the Bernoullian distribution, it is possible to determine for every n the functional dependence between epsilon and p. An examination of this function shows that for every large n there exists a characteristic value of p such that in the neighborhood of this value, p is highly insensitive to changes of epsilon. This insensitiveness increases with increasing n. If we take an n of an order of magnitude which we should expect in the case of extreme mass phenomena, then, in the neighborhood of its characteristic value, p is so highly insensitive to changes of epsilon that p hardly changes at all even if the order of magnitude of epsilon changes. Now the physicist will attach little value to more sharply defined boundaries of p. And in the case of typical mass phenomena, to which this investigation is restricted, p can, we remember, be taken to correspond to the interval of precision plus or minus phi which depends upon our technique of measurement, and this has no sharp bounds but only what I called in section condensation bounds. We shall therefore call n large when the insensitivity of p in the neighborhood of its characteristic value, which we can determine, is at least so great that even changes in order of magnitude of epsilon cause the value of p to fluctuate only within the condensation bounds of plus or minus phi. If n registered trademark yen, then p becomes completely insensitive. But if this is so, then we need no longer concern ourselves with the exact determination of epsilon. The decision to neglect a small epsilon sutsays, even if we have not exactly stated what has to be regarded as small. It amounts to the decision to work with the characteristic values of p above mentioned, which are insensitive to changes of epsilon. The rule that extreme improbabilities have to be neglected, a rule which becomes sufficiently explicit only in the light of the above, agrees with the demand for scientific objectivity. For the obvious objection to our rule is, clearly, that even the greatest improbability always remains a probability, however small, and that consequently even the most improbable processes, i.e. those which we propose to neglect, will someday happen. But this objection can be disposed of by recalling the idea of a reproducible physical eq, an idea which is closely connected with that of objectivity, cf. section. I do not deny the possibility that improbable events might occur. I do not, for example, assert that the molecules in a small volume of gas may not, perhaps, for a short time spontaneously withdraw into a part of the volume, or that in a greater volume of gas spontaneous fluctuations of pressure will never occur. What I do assert is that such occurrences would not be physical acts, because, on account of their immense improbability, they are not reproducible at will. Even if a physicist happened to observe such a process, he would be quite unable to reproduce it, and therefore would never be able to decide what had really happened in this case, and whether he may not have made an observational mistake. If, however, we nd reproducible deviations from a macro act which has been deduced from a probability estimate in the manner indicated, then we must assume that the probability estimate is falsied. Such considerations may help us to understand pronouncements like the following of Eddington's, in which he distinguishes two kinds of physical laws: some things never happen in the physical world because they are impossible, others because they are too improbable. The laws which forbid the RST are primary laws, the laws which forbid the second are secondary laws. Although this formulation is perhaps not beyond criticism, I should prefer to abstain from non-testable assertions about whether or not extremely improbable things occur. It agrees well with the physicist's application of probability theory. Other cases to which probability theory may be applied, such as statistical fluctuations, or the statistics of chance like individual events, are reducible to the case we have been discussing, that of the precisely measurable macro act. By statistical fluctuations I understand phenomena such as the Brownian movement. Here the interval of precision of measurement, plus or minus phi, is smaller than the interval p characteristic of the number n of micro-events contributing to the act, hence measurable deviations from p are to be expected as highly probable. The fact that such deviations occur will be testable, since the fluctuation itself becomes a reproducible act, and to this act my earlier arguments apply. Fluctuations beyond a certain magnitude, beyond some interval p, must not be reproducible, according to my methodological requirements, nor long sequences of fluctuations in one and the same direction, etc. Corresponding arguments would hold for the statistics of chance-like individual events. I may now summarize my arguments regarding the problem of decidability. Our question was, how can probability hypotheses which, we have seen, are non-falsiable play the part of natural laws in empirical science? Our answer is this: probability statements, insofar as they are not falsiable, are metaphysical and without empirical significance, and insofar as they are used as empirical statements they are used as falsiable statements. But this answer raises another question: how is it possible that probability statements which are not falsiable can be used as falsiable statements? The fact that they can be so used is not in doubt. The physicist knows well enough when to regard a probability assumption as falsied. This question, we nd, has two aspects. On the one hand, we must make the possibility of using probability statements understandable in terms of their logical form. On the other hand, we must analyze the rules governing their use as falsiable statements. According to section, accepted basic statements may agree more or less well with some proposed probability estimate. They may represent better, or less well, a typical segment of a probability sequence. This provides the opportunity for the application of some kind of methodological rule, a rule, for instance, which might demand that the agreement between basic statements and the probability estimate should conform to some minimum standard. Thus the rule might draw some arbitrary line and decree that only reasonably representative segments, or reasonably fair samples, are permitted, while atypical or non-representative segments are forbidden. A closer analysis of this suggestion showed us that the dividing line between what is permitted and what is forbidden need not be drawn quite as arbitrarily as might have been thought at RST. And in particular, that there is no need to draw it tolerantly. For it is possible to frame the rule in such a way that the dividing line between what is permitted and what is forbidden is determined, just as in the case of other laws, by the attainable precision of our measurements. Our methodological rule, proposed in accordance with the criterion of demarcation, does not forbid the occurrence of atypical segments, neither does it forbid the repeated occurrence of deviations, which, of course, are typical for probability sequences. What this rule forbids is the predictable and reproducible occurrence of systematic deviations, such as deviations in a particular direction, or the occurrence of segments which are atypical in a D-night way. Thus it requires not a mere rough agreement, but the best possible one for everything that is reproducible and testable, in short, for all reproducible acts. 69 Law and Chance. One sometimes hears it said that the movements of the planets obey strict laws, whilst the fall of a die is fortuitous, or subject to chance. In my view, the difference lies in the fact that we have so far been able to predict the movement of the planets successfully, but not the individual results of throwing dice. In order to deduce predictions, one needs laws and initial conditions. If no suitable laws are available, or if the initial conditions cannot be ascertained, the scientific way of predicting breaks down. In throwing dice, what we lack is, clearly, sufficient knowledge of initial conditions. With sufficiently precise measurements of initial conditions, it would be possible to make predictions in this case also, but the rules for correct dicing, shaking the dice box, are so chosen as to prevent us from measuring initial conditions. The rules of play and other rules determining the conditions under which the various events of a random sequence are to take place I shall call the frame conditions. They consist of such requirements as that the dice shall be true, made from homogeneous material, that they shall be well shaken, etc. There are other cases in which prediction may be unsuccessful. Perhaps it has not so far been possible to formulate suitable laws, perhaps all attempts to end a law have failed, and all predictions have been falsified. In such cases we may despair of ever ending a satisfactory law. But it is not likely that we shall give up trying unless the problem does not interest us much, which may be the case, for example, if we are satisfied with frequency predictions. In no case, however, can we say with finality that there are no laws in a particular field. This is a consequence of the impossibility of verification. This means that my view makes the concept of chance subjective. I speak of chance when our knowledge does not suffice for prediction, as in the case of dicing, where we speak of chance because we have no knowledge of the initial conditions. Conceivably, a physicist equipped with good instruments could predict a throw which other people could not predict. In opposition to this subjective view, an objective view has sometimes been advocated. In so far as this uses the metaphysical idea that events are, or are not, determined in themselves, I shall not examine it further here. Cf. section end. If we are successful with our prediction, we may speak of laws, otherwise we can know nothing about the existence or non-existence of laws or of irregularities. Perhaps more worth considering than this metaphysical idea is the following view. We encounter chance in the objective sense, it may be said, when our probability estimates are corroborated, just as we encounter causal regularities when our predictions deduced from laws are corroborated. The definition of chance implicit in this view may not be altogether useless, but it should be strongly emphasized that the concept so deemed is not opposed to the concept of law. It was for this reason that I called probability sequences chance-like. In general, a sequence of experimental results will be chance-like if the frame conditions which deem the sequence differ from the initial conditions, when the individual experiments, carried out under identical frame conditions, will proceed under different initial conditions, and so yield different results. Whether there are chance-like sequences whose elements are in no way predictable, I do not know. From the fact that a sequence is chance-like we may not even infer that its elements are not predictable, or that they are due to chance in the subjective sense of insouciant knowledge, and least of all may we infer from this fact the objective fact that there are no laws. Not only is it impossible to infer from the chance-like character of the sequence anything about the conformity to law, or otherwise, of the individual events, it is not even possible to infer from the corroboration of probability estimates that the sequence itself is completely irregular. For we know that chance-like sequences exist which are constructed according to a mathematical rule. Cf. Appendix 4. The fact that a sequence has a Bernoullian distribution is not a symptom of the absence of law, and much less identical with the absence of law by definition. In the success of probability predictions we must see no more than a symptom of the absence of simple laws in the structure of the sequence, cf. sections end, as opposed to the events constituting it. The assumption of freedom from aftereffect, which is equivalent to the hypothesis that such simple laws are not discoverable, is corroborated, but that is all. 70. The deducibility of macro laws from micro laws. There is a doctrine which has almost become a prejudice, although it has recently been criticized severely, the doctrine that all observable events must be explained as macro events, that is to say, as averages or accumulations or summations of certain micro events. The doctrine is somewhat similar to certain forms of materialism. Like other doctrines of its kind, this seems to be a metaphysical hypostatization of a methodological rule which in itself is quite unobjectionable. I mean the rule that we should see whether we can simplify or generalize or unify our theories by employing explanatory hypotheses of the type mentioned, that is to say, hypotheses explaining observable effects as summations or integrations of micro-events. In evaluating the success of such attempts, it would be a mistake to think that non-statistical hypotheses about the micro-events and their laws of interaction could ever be sufficient to explain macro-events. For we should need, in addition, hypothetical frequency estimates, since statistical conclusions can only be derived from statistical premises. These frequency estimates are always independent hypotheses which, at times, may indeed occur to us whilst we are engaged in studying the laws pertaining to micro-events, but which can never be derived from these laws. Frequency estimates form a special class of hypotheses. They are prohibitions which, as it were, concern regularities in the large. Von Mises has stated this very clearly. Not even the tiniest little theorem in the kinetic theory of gases follows from classical physics alone, without additional assumptions of a statistical kind. Statistical estimates, or frequency statements, can never be derived simply from laws of a deterministic kind, for the reason that in order to deduce any prediction from such laws, initial conditions are needed. In their place, assumptions about the statistical distribution of initial conditions, that is to say specific statistical assumptions, enter into every deduction in which statistical laws are obtained from micro-assumptions of a deterministic or precise character. It is a striking fact that the frequency assumptions of theoretical physics are to a great extent equal chance hypotheses, but this by no means implies that they are self-evident or a priori valid. That they are far from being so may be seen from the wide differences between classical statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. These show how special assumptions may be combined with an equal chance hypothesis, leading in each case to different definitions of the reference sequences and the primary properties for which equal distribution is assumed. The following example may perhaps illustrate the fact that frequency assumptions are indispensable even when we may be inclined to do without them. Imagine a waterfall. We may discern some odd kind of regularity. The size of the currents composing the fall varies, and from time to time a splash is thrown from the main stream, yet throughout all such variations a certain regularity is apparent which strongly suggests a statistical effect. Disregarding some unsolved problems of hydrodynamics, concerning the formation of vortices, etc., we can, in principle, predict the path of any volume of water, say a group of molecules, with any desired degree of precision, if sufficiently precise initial conditions are given. Thus we may assume that it would be possible to foretell of any molecule, far above the waterfall, at which point it will pass over the edge, where it will reach bottom, etc. In this way the path of any number of particles may, in principle, be calculated, and given sufficient initial conditions we should be able, in principle, to deduce any one of the individual statistical fluctuations of the waterfall. But only this or that individual fluctuation could be so obtained, not the recurring statistical regularities we have described, still less the general statistical distribution as such. In order to explain these we need statistical estimates, at least the assumption that certain initial conditions will again and again recur for many different groups of particles, which amounts to a universal statement. We obtain a statistical result if, and only if, we make such specific statistical assumptions, for example, assumptions concerning the frequency distribution of recurring initial conditions. 71 Formally singular probability statements. I call a probability statement formally singular when it ascribes a probability to a single occurrence, or to a single element of a certain class of occurrences. For example, the probability of throwing VE with the next throw of this die is /cent, or the probability of throwing VE with any single throw of this die is /cent. From the standpoint of the frequency theory, such statements are as a rule regarded as not quite correct in their formulation, since probabilities cannot be ascribed to single occurrences, but only to innate sequences of occurrences or events. It is easy, however, to interpret these statements as correct, by appropriately defining formally singular probabilities with the help of the concept of objective probability or relative frequency. I use alpha pk, beta, to denote the formally singular probability that a certain occurrence k has the property beta, in its capacity as an element of a sequence alpha in symbols, k epsilon alpha, and I then deem the formally singular probability as follows. Alpha pk, beta, equals alpha f, beta, k epsilon alpha, definition. This can be expressed in words as, the formally singular probability that the event k has the property beta given that k is an element of the sequence alpha is, by definition, equal to the probability of the property beta within the reference sequence alpha. This simple, almost obvious, definition proves to be surprisingly useful. It can even help us to clarify some intricate problems of modern quantum theory. Cf sections. As the definition shows, a formally singular probability statement would be incomplete if it did not explicitly state a reference class. But although alpha is often not explicitly mentioned, we usually know in such cases which alpha is meant. Thus the RST example given above does not specify any reference sequence alpha, but it is nevertheless fairly clear that it relates to all sequences of throws with true dice. In many cases there may be several die-errant reference sequences for an event k. In these cases it may be only too obvious that die-errant formally singular probability statements can be made about the same event. Thus the probability that an individual man k will die within a given period of time may assume very die-errant values according to whether we regard him as a member of his age group, or of his occupational group, etc. It is not possible to lay down a general rule as to which out of several possible reference classes should be chosen. The narrowest reference class may often be the most suitable, provided that it is numerous enough to allow the probability estimate to be based upon reasonable statistical extrapolation, and to be supported by a sufficient amount of corroborating evidence. Not a few of the so-called paradoxes of probability disappear once we realize that die-errant probabilities may be ascribed to one and the same occurrence or event, as an element of die-errant reference classes. For example, it is sometimes said that the probability alpha pk, beta, of an event before its occurrence is die-errant from the probability of the same event after it has occurred. Before, it may equal /, while afterwards it can only be equal to or 0. This view is, of course, quite mistaken. Alpha pk, beta, is always the same, both before and after the occurrence. Nothing has changed except that, on the basis of the information k epsilon beta, or k epsilon beta, beta information which may be supplied to us upon observing the occurrence, we may choose a new reference class, namely beta, or beta k. And then ask what is the value of beta pk, beta. The value of this probability is of course, just as p, beta, equals 0. Statements informing us about the actual outcome of single occurrences, statements which are not about some frequency but rather of the form k epsilon phi, cannot change the probability of these occurrences. They may, however, suggest to us the choice of another reference class. The concept of a formally singular probability statement provides a kind of bridge to the subjective theory, and thereby also, as will be shown in the next section, to the theory of range. For we might agree to interpret formally singular probability as degree of rational belief, following Keynes, provided we allow our rational beliefs to be guided by an objective frequency statement. This then is the information upon which our beliefs depend. In other words, it may happen that we know nothing about an event except that it belongs to a certain reference class in which some probability estimate has been successfully tested. This information does not enable us to predict what the property of the event in question will be, but it enables us to express all we know about it by means of a formally singular probability statement which looks like an indefinite prediction about the particular event in question. Thus I do not object to the subjective interpretation of probability statements about single events, i.e. to their interpretation as indefinite predictions, as confessions, so to speak, of our descent knowledge about the particular event in question, concerning which, indeed, nothing follows from a frequency statement. I do not object, that is to say, so long as we clearly recognize that the objective frequency statements are fundamental, since they alone are empirically testable. I reject, however, any interpretation of these formally singular probability statements, these indefinite predictions, as statements about an objective state of affairs, other than the objective statistical state of affairs. What I have in mind is the view that a statement about the probability/indicing is not a mere confession that we know nothing denied, subjective theory, but rather an assertion about the next throw, an assertion that its result is objectively both indeterminate and undetermined, something which as yet hangs in the balance. I regard all attempts at this kind of objective interpretation, discussed at length by Jeans, among others, as mistaken. Whatever indeterministic airs these interpretations may give themselves, they all involve the metaphysical idea that not only can we deduce and test predictions, but that, in addition, nature is more or less determined, or undetermined, so that the success, or failure, of predictions is to be explained not by the laws from which they are deduced, but over and above this by the fact that, at present I think that the question of the relation between the various interpretations of probability theory can be tackled in a much simpler way by giving a formal system of axioms or postulates and proving that it is satisfied by the various interpretations. Thus I regard most of the considerations advanced in the rest of this chapter, sections and as being superseded. See Appendix 4, and Chapters 2, 3, and V of my postscript. But I still agree with most of what I have written, provided my reference classes are determined by the conditions denning an experiment, so that the frequencies may be considered as the result of propensities. I do not now object to the view that an event may hang in the balance, and I even believe that probability theory can best be interpreted as a theory of the propensities of events to turn out one way or another. See my postscript. But I should still object to the view that probability theory must be so interpreted. That is to say, I regard the propensity interpretation as a conjecture about the structure of the world. Nature is actually constituted, or not constituted, according to these laws. 72. The theory of range. In section I said that a statement which is falsifiable to a higher degree than another statement can be described as the one which is logically more improbable, and the less falsifiable statement as the one which is logically more probable. The logically less probable statement entails the logically more probable one. Between this concept of logical probability and that of objective or formally singular numerical probability there are entities. Some of the philosophers of probability, Bolzano, von Kreis, Weismann, have tried to base the calculus of probability upon the concept of logical range, and thus upon a concept which, cf. section, coincides with that of logical probability, and in doing so, they also tried to work out the entities between logical and numerical probability. Weismann has proposed to measure the degree of interrelatedness between the logical ranges of various statements, their ratios, as it were, by means of the relative frequencies corresponding to them, and thus to treat the frequencies as determining a system of measurement for ranges. I think it is feasible to erect a theory of probability on this foundation. Indeed, we may say that this plan amounts to the same thing as correlating relative frequencies with certain indefinite predictions as we did in the foregoing section, when denning formally singular probability statements. It must be said, however, that this method of denning probability is only practicable when a frequency theory has already been constructed. Otherwise one would have to ask how the frequencies used in denning the system of measurement were deemed in their turn. If, however, a frequency theory is at our disposal already, then the introduction of the theory of range becomes really superfluous. But in spite of this objection, I regard the practicability of Weismann's proposal as significant. It is satisfactory to ND that a more comprehensive theory can bridge the gaps which at RST appeared unbridgeable between the various attempts to tackle the problem, especially between the subjective and the objective interpretations. Yet Weismann's proposal calls for some slight modification. His concept of a ratio of ranges, cf. note to section, not only presupposes that ranges can be compared with the help of their subclass relations, or their entailment relations, but it also presupposes, more generally, that even ranges which only partially overlap, ranges of non-comparable statements, can be made comparable. This latter assumption, however, which involves considerable difficulties, is superfluous. It is possible to show that in the cases concerned, such as cases of randomness, the comparison of subclasses and that of frequencies must lead to analogous results. This justifies the procedure of correlating frequencies to ranges in order to measure the latter. In doing so, we make the statements in question, non-comparable by the subclass method, comparable. I will indicate roughly how the procedure described might be justified. If between two property classes gamma and beta the subclass relation gamma I beta holds, then we have K, FSB, K epsilon gamma, FSB, K epsilon beta, cf section. So that the logical probability or the range of the statement, K epsilon gamma, must be smaller than, or equal to, that of, K epsilon beta. It will be equal only if there is a reference class alpha, which may be the universal class, with respect to which the following rule holds, which may be said to have the form of a law of nature. X epsilon, alpha dot beta, registered trademark, X epsilon gamma. If this law of nature does not hold, so that we may assume randomness in this respect, then the inequality holds. But in this case we obtain, provided alpha is denumerable, and acceptable as a reference sequence. Alpha f, gamma, alpha f, beta. This means that, in the case of randomness, a comparison of ranges must lead to the same inequality as a comparison of relative frequencies. Accordingly, if we have randomness, we may correlate relative frequencies with the ranges in order to make the ranges measurable. But this is just what we did, although indirectly, in section, when we deemed the formally singular probability statement. Indeed, from the assumptions made, we might have inferred immediately that alpha pk, gamma, alpha pk, beta. So we have come back to our starting point, the problem of the interpretation of probability. And we now ND that the connect between objective and subjective theories, which at RST seemed so obdurate, may be eliminated altogether by the somewhat obvious definition of formally singular probability. Some observations on quantum theory. Our analysis of the problem of probability has placed instruments at our disposal which we may now put to the test, by applying them to one of the topical problems of modern science, and I will try, with their help, to analyze, and to clarify, some of the more obscure points of modern quantum theory. My somewhat audacious attempt to tackle, by philosophical or logical methods, one of the central problems of physics, is bound to arouse the suspicion of the physicist. I admit that his skepticism is healthy and his suspicions well-founded, yet I have some hope that I may be able to overcome them. Meanwhile, it is worth remembering that in every branch of science, questions may crop up which are mainly logical. It is a fact that quantum physicists have been eagerly participating in epistemological discussions. This may suggest that they themselves feel that the solution of some of the still unsolved problems in quantum theory has to be sought in the no man's land that lies between logic and physics. I will begin by setting down in advance the main conclusions which will emerge from my analysis. 1. There are some mathematical formulae in quantum theory which have been interpreted by Heisenberg in terms of his uncertainty principle, that is, as statements about ranges of uncertainty due to the limits of precision which we may attain in our measurements. These formulae, as I shall try to show, are to be interpreted as formally singular probability statements, cf. section, which means that they in their turn must be interpreted statistically. So interpreted, the formulae in question assert that certain relations hold between certain ranges of statistical dispersion or variance or scatter. They will be here called statistical scatter relations. 2. Measurements of a higher degree of precision than is permitted by the uncertainty principle are not, I shall try to show, incompatible with the system of formulae of quantum theory, or with its statistical interpretation. Thus quantum theory would not necessarily be refuted if measurements of such a degree of precision should ever become possible. 3. The existence of limits of attainable precision which was asserted by Heisenberg would therefore not be a logical consequence deducible from the formulae of the theory. It would be, rather, a separate or an additional assumption. 4. Moreover, this additional assumption of Heisenberg's actually contradicts, as I shall try to show, the formulae of quantum theory if they are statistically interpreted. For not only are more precise measurements compatible with the quantum theory, but it is even possible to describe imaginary experiments which show the possibility of more exact measurements. In my view, it is this contradiction which creates all those difficulties by which the admirable structure of modern quantum physics is beset, so much so that Turing could say of quantum theory that it has remained an impenetrable mystery to its creators, on their own admission. What follows here might be described, perhaps, as an inquiry into the foundations of quantum theory. In this, I shall avoid all mathematical arguments and, with one single exception, all mathematical formulae. This is possible because I shall not question the correctness of the system of the mathematical formulae of quantum theory. I shall only be concerned with the logical consequences of its physical interpretation, which is due to Born. As to the controversy over causality, I propose to dissent from the indeterminist metaphysic so popular at present. What distinguishes it from the determinist metaphysic until recently in vogue among physicists is not so much its greater lucidity as its greater sterility. In the interests of clarity, my criticism is often severe. It may therefore be just as well to say here that I regard the achievement of the creators of modern quantum theory as one of the greatest in the whole history of science. 73. Heisenberg's program and the uncertainty relations. When he attempted to establish atomic theory on a new basis, Heisenberg started with an epistemological program, to rid the theory of unobservables, that is, of magnitudes inaccessible to experimental observation, to rid it, one might say, of metaphysical elements. Such unobservable magnitudes did occur in Bohr's theory, which preceded Heisenberg's own. Nothing observable by experiment corresponded to the orbits of the electrons or even to the frequencies of their revolutions, for the emitted frequencies which could be observed as spectral lines could not be identified with the frequencies of the electrons' revolutions. Heisenberg hoped that by eliminating these unobservable magnitudes, he might manage to cure Bohr's theory of its shortcomings. There is a certain similarity between this situation and the one with which Einstein was confronted when trying to reinterpret the Lorentz-Fitzgerald hypothesis of contraction. This hypothesis tried to explain the negative result of the experiments of Michelson and Morley by making use of unobservable magnitudes such as the movements relative to Lorentz's immobile ether, i.e. of magnitudes inaccessible to experimental testing. Both in this case and in that of Bohr's theory, the theories needing reform explained certain observable natural processes, but both made use of the unsatisfactory assumption that physical events and physically deemed magnitudes exist which nature succeeds in hiding from us by making them forever inaccessible to observational tests. Einstein showed how the unobservable events involved in Lorentz's theory could be eliminated. One might be inclined to say the same of Heisenberg's theory, or at least of its mathematical content. However, there still seems to be room for improvement. Even from the point of view of Heisenberg's own interpretation of his theory, it does not seem that his program has been fully carried out. Nature still succeeds in hiding from us most cunningly some of the magnitudes embodied in the theory. This state of affairs is connected with the so-called uncertainty principle enunciated by Heisenberg. It may, perhaps, be explained as follows. Every physical measurement involves an exchange of energy between the object measured and the measuring apparatus, which might be the observer himself. A ray of light, for example, might be directed upon the object, and part of the dispersed light reflected by the object might be absorbed by the measuring apparatus. Any such exchange of energy will alter the state of the object which, after being measured, will be in a state different from before. Thus the measurement yields, as it were, knowledge of a state which has just been destroyed by the measuring process itself. This interference by the measuring process with the object measured can be neglected in the case of macroscopic objects, but not in the case of atomic objects, for these may be very strongly affected, for example by irradiation with light. It is thus impossible to infer from the result of the measurement the precise state of an atomic object immediately after it has been measured. Therefore the measurement cannot serve as basis for predictions. Admittedly, it is always possible to ascertain, by means of new measurements, the state of the object after the previous measurement, but the system is thereby again interfered with in an incalculable way. And admittedly, it is always possible to arrange our measurements in such a way that certain of the characteristics of the state to be measured, for example the momentum of the particle, are not disturbed. But this can only be done at the price of interfering the more severely with certain other characteristic magnitudes of the state to be measured, in this case the position of the particle. If two magnitudes are mutually correlated in this way, then the theorem holds for them that they cannot simultaneously be measured with precision, although each may be separately so measured. Thus if we increase the precision of one of the two measurements, say the momentum px, thereby reducing the range or interval of error px, then we are bound to decrease the precision of the measurement of the position co-ordinate x, i.e. to expand the interval x. In this way, the greatest precision attainable is, according to Heisenberg, limited by the uncertainty relation h x px pi. Similar relations hold for the other co-ordinates. The formula tells us that the product of the two ranges of error is at least of the order of magnitude of h, where h is Planck's quantum of action. It follows from this formula that a completely precise measurement of one of the two magnitudes will have to be purchased at the price of complete indeterminacy in the other. According to Heisenberg's uncertainty relations, every measurement of the position interferes with the measurement of the corresponding component of the momentum. Thus it is in principle impossible to predict the path of a particle. In the new mechanics, the concept path has no finite meaning whatever. But here the RST difficulty arises. The uncertainty relations apply only to the magnitudes, characteristic of physical states, which belong to the particle after the measurement has been made. The position and momentum of an electron up to the instant of measuring can be ascertained in principle with unlimited precision. This follows from the very fact that it is after all possible to carry out several measuring operations in succession. Accordingly, by combining the results of a. two measurements of position, b. measurement of position preceded by measurement of momentum, and c. measurement of position followed by measurement of momentum, it would be possible to calculate, with the help of the data obtained, the precise position and momentum co-ordinates for the whole period of time between the two measurements. To start with, we may convey our considerations only to this period. But these precise calculations are, according to Heisenberg, useless for prediction. It is therefore impossible to test them. This is so because the calculations are valid for the path between the two experiments only if the second is the immediate successor of the RST, in the sense that no interference has occurred between them. Any test that might be arranged for the purpose of checking the path between the two experiments is bound to disturb it so much that our calculations of the exact path become invalid. Heisenberg says about these exact calculations, whether one should attribute any physical reality to the calculated past history of the electron is a pure matter of taste. By this he clearly wishes to say that such untestable calculations of paths are from the physicist's point of view without any significance. Schlick comments on this passage of Heisenberg's as follows: I would have expressed myself even more strongly, in complete agreement with the fundamental views of both Bohr and Heisenberg themselves, which I believed to be incontestable. If a statement concerning the position of an electron in atomic dimensions is not variable, then we cannot attribute any sense to it. It becomes impossible to speak of the path of a particle between 2 points at which it has been observed. Similar remarks are to be found in March, Whale, and others. Yet, as we have just heard, it is possible to calculate such a senseless or metaphysical path in terms of the new formalism. And this shows that Heisenberg has failed to carry through his program. For this state of affairs only allows of two interpretations. The RST would be that the particle has an exact position and an exact momentum, and therefore also an exact path, but that it is impossible for us to measure them both simultaneously. If this is so, then nature is still bent on hiding certain physical magnitudes from our eyes, not indeed the position, nor yet the momentum, of the particle, but the combination of these two magnitudes, the position cum momentum, or the path. This interpretation regards the uncertainty principle as a limitation of our knowledge, thus it is subjective. The other possible interpretation, which is an objective one, asserts that it is inadmissible or incorrect or metaphysical to attribute to the particle anything like a sharply defined position cum momentum or path. It simply has no path, but only either an exact position combined with an inexact momentum, or an exact momentum combined with an inexact position. But if we accept this interpretation, then, again, the formalism of the theory contains metaphysical elements, for a path or position cum momentum of the particle, as we have seen, is exactly calculable for those periods of time during which it is in principle impossible to test it by observation. It is illuminating to see how the champions of the uncertainty relation vacillate between a subjective and an objective approach. Schlick, for instance, writes, immediately after upholding the objective view, as we have seen, of natural events themselves, it is impossible to assert meaningfully any such thing as haziness or inaccuracy. It is only to our own thoughts that anything of this sort can apply, more especially, if we do not know which statements are true, a remark which is obviously directed against that very same objective interpretation which assumes that it is not our knowledge, but the momentum of the particle, which gets blurred or smeared, as it were, by having its position precisely measured. Similar vacillations are shown by many other authors. But whether one decides in favor of the objective or the subjective view, the fact remains that Heisenberg's program has not been carried out and that he has not succeeded in his self-imposed task of expelling all metaphysical elements from atomic theory. Nothing whatever is therefore to be gained by attempting, with Heisenberg, to fuse the two opposing interpretations by a remark such as an objective physics in this sense, i.e. a sharp division of the world into object and subject, has indeed ceased to be possible. Heisenberg has not so far accomplished his self-imposed task, he has not yet purged quantum theory of its metaphysical elements. 74. A brief outline of the statistical interpretation of quantum theory. In his derivation of the uncertainty relations, Heisenberg follows Bohr in making use of the idea that atomic processes can be just as well represented by the quantum theoretical image of a particle as by the quantum theoretical image of a wave. This idea is connected with the fact that modern quantum theory has advanced along two different roads. Heisenberg started from the classical particle theory of the electron, which he reinterpreted according to quantum theory, whilst Schrödinger started from the, likewise classical, wave theory of de Broglie. He coordinated with each electron a wave packet, i.e. a group of oscillations which by interference strengthen each other within a small region and extinguish each other outside it. Schrödinger later showed that his wave mechanics led to results mathematically equivalent to those of Heisenberg's particle mechanics. The paradox of the equivalence of two so fundamentally different images as those of particle and wave was resolved by Born's statistical interpretation of the two theories. He showed that the wave theory too can be taken as a particle theory, for Schrödinger's wave equation can be interpreted in such a way that it gives us the probability of ending the particle within any given region of space. The probability is determined by the square of the amplitude of the wave. It is great within the wave packet where the waves reinforce each other, and vanishes outside it. That the quantum theory should be interpreted statistically was suggested by various aspects of the problem's situation. Its most important task, the deduction of the atomic spectra, had to be regarded as a statistical task ever since Einstein's hypothesis of photons, or light quanta. For this hypothesis interpreted the observed light as mass phenomena, as due to the incidence of many photons. The experimental methods of atomic physics have, under the guidance of experience, become concerned, exclusively, with statistical questions. Quantum mechanics, which furnishes the systematic theory of the observed regularities, corresponds in every way to the present state of experimental physics, for it connects itself, from the outset, to statistical questions and to statistical answers. It is only in its application to problems of atomic physics that quantum theory obtains results which differ from those of classical mechanics. In its application to macroscopic processes, its formulae yield with close approximation those of classical mechanics. According to quantum theory, the laws of classical mechanics are valid if they are regarded as statements about the relations between statistical averages, says March. In other words, the classical formulae can be deduced as macro laws. In some expositions, the attempt is made to explain the statistical interpretation of the quantum theory by the fact that the precision attainable in measuring physical magnitudes is limited by Heisenberg's uncertainty relations. It is argued that, owing to this uncertainty of measurements in any atomic experiments, the result will not in general be determinate, i.e., if the experiment is repeated several times under identical conditions, several different results may be obtained. If the experiment is repeated a large number of times, it will be found that each particular result will be obtained in a finite fraction of the total number of times, so that one can say there is a finite probability of its being obtained any time the experiment is performed. Dirac. March 2 writes, with reference to the uncertainty relation between the present and the future, there hold only probability relations, from which it becomes clear that the character of the new mechanics must be that of a statistical theory. I do not think that this analysis of the relations between the uncertainty formulae and the statistical interpretation of the quantum theory is acceptable. It seems to me that the logical relation is just the other way round. For we can derive the uncertainty formulae from Schrödinger's wave equation, which is to be interpreted statistically, but not this latter from the uncertainty formulae. If we are to take due account of these relations of derivability, then the interpretation of the uncertainty formulae will have to be revised. 75. A statistical reinterpretation of the uncertainty formulae. Since Heisenberg, it is accepted as an established fact that any simultaneous measurements of position and momentum with a precision exceeding that permitted by his uncertainty relations would contradict quantum theory. The prohibition of exact measurements, it is believed, can be logically derived from quantum theory, or from wave mechanics. On this view, the theory would have to be regarded as falsified if experiments resulting in measurements of forbidden accuracy could be carried out. I believe this view to be false. Admittedly, it is true that Heisenberg's H formulae, xp, x pi, etc., result as logical conclusions from the theory, but the interpretation of these formulae as rules limiting attainable precision of measurement, in Heisenberg's sense, does not follow from the theory. Therefore, measurements more exact than those permissible according to Heisenberg cannot logically contradict the quantum theory, or wave mechanics. I shall accordingly draw a sharp distinction between the formulae, which I shall call the Heisenberg formulae for short, and their interpretation also due to Heisenberg as uncertainty relations, that is, as statements imposing limitations upon the attainable precision of measurement. When working out the mathematical deduction of the Heisenberg formulae, one has to employ the wave equation or some equivalent assumption, i.e., an assumption which can be statistically interpreted, as we saw in the preceding section. But if this interpretation is adopted, then the description of a single particle by a wave packet is undoubtedly nothing else but a formally singular probability statement, cf. section. The wave amplitude determines, as we have seen, the probability of detecting the particle at a certain place, and it is just this kind of probability statement, the kind that refers to a single particle, or event, which we have called formally singular. If one accepts the statistical interpretation of quantum theory, then one is bound to interpret those statements such as the Heisenberg formulae, which can be derived from the formally singular probability statements of the theory, as probability statements in their turn, and again as formally singular, if they apply to a single particle. They too must therefore be interpreted, ultimately, as statistical assertions. As against the subjective interpretation, the more precisely we measure the position of a particle, the less we can know about its momentum. I propose that an objective and statistical interpretation of the uncertainty relations should be accepted as being the fundamental one. It may be phrased somewhat as follows. Given an aggregate of particles and a selection, in the sense of a physical separation, of those which, at a certain instant, and with a certain given degree of precision, have a certain position x, we shall nd that their momenta px will show random scattering, and the range of scatter, px, will thereby the greater, the smaller we have made x, i.e. the range of scatter or imprecision allowed to the positions. And vice versa, if we select, or separate, those particles whose momenta px all fall within a prescribed range px, then we shall nd that their positions will scatter in a random manner, within a range x, which will be the greater, the smaller we have made px, i.e. the range of scatter or imprecision allowed to the momenta. And nally, if we try to select those particles which have both the properties x and px, then we can physically carry out such a selection, that is, physically separate the particles only if both ranges h are made sufficiently great to satisfy the equation x px. This pi objective interpretation of the Heisenberg formulae takes them as asserting that certain relations hold between certain ranges of scatter, and I shall refer to them, if they are interpreted in this way, as the statistical scatter relations. In my statistical interpretation I have so far made no mention of measurement, I have referred only to physical selection. It is now necessary to clarify the relation between these two concepts. I speak of physical selection or physical separation if, for example, we screen O, from a stream of particles, all except those which pass through a narrow aperture x, that is, through a range x allowed to their position. And I shall say of the particles belonging to the ray thus isolated that they have been selected physically, or technically, according to their property x. It is only this process, or its result, the physically or technically isolated ray of particles, which I describe as a physical selection in contradistinction to a merely mental or imagined selection, such as we make when speaking of the class of all those particles which have passed, or will pass, through the range p, that is, of a class within a wider class of particles from which it has not been physically screened O. Now every physical selection can of course be regarded as a measurement, and can actually be used as such. If, say, a ray of particles is selected by screening O or shutting out all those which do not pass through a certain positional range, place selection, and if later the momentum of one of these particles is measured, then we can regard the place selection as a measurement of position, because we learn from it that the particle has passed through a certain position, though when it was there we may sometimes not know, or may only learn from another measurement. On the other hand, we must not regard every measurement as a physical selection. Imagine, for example, a monochromatic ray of electrons ying in the direction x. By using a Geiger counter, we can then record those electrons that arrive at a certain position. By the time intervals between the impacts upon the counter, we may also measure spatial intervals, that is to say, we measure their positions in the x direction up to the moment of impact. But in taking these measurements we do not make a physical selection of the particles according to their positions in the x direction. And indeed, these measurements will generally yield a completely random distribution of the positions in the x direction. Thus in their physical application, our statistical scatter relations come to this. If one tries, by whatever physical means, to obtain as homogeneous an aggregate of particles as possible, then this attempt will encounter a finite barrier in these scatter relations. For example, we can obtain by means of physical selection a plane monochromatic ray, say, a ray of electrons of equal momentum. But if we attempt to make this aggregate of electrons still more homogeneous, perhaps by screening O part of it so as to obtain electrons which not only have the same momentum but have also passed through some narrow slit determining a positional range x, then we are bound to fail. We fail because any selection according to the position of the particles amounts to an interference with the system which will result in increased scattering of the momentum components px, so that the scattering will increase, in accordance with the law expressed by the Heisenberg formula, with the narrowing of the slit. And conversely, if we are given a ray selected according to position by being passed through a slit, and if we try to make it parallel, or plane, and monochromatic, then we have to destroy the selection according to position, since we cannot avoid increasing the width of the ray. In the ideal case, for example, if the px components of the particles are all to become equal to O, the width would have to become inite. If the homogeneity of a selection has been increased as far as possible, i.e. as far as the Heisenberg formulae permit, so that the sign of equality in these formulae becomes valid, then this selection may be called a pure case. Using this terminology, we can formulate the statistical scatter relations thus: there is no aggregate of particles more homogeneous than a pure case. It has not till now been taken sufficiently into account that to the mathematical derivation of the Heisenberg formulae from the fundamental equations of quantum theory there must correspond, precisely, a derivation of the interpretation of the Heisenberg formulae from the interpretation of these fundamental equations. March, for instance, has described the situation just the other way round. As indicated in the previous section, the statistical interpretation of quantum theory appears in his presentation as a consequence of the Heisenberg limitation upon attainable precision. Weyl, on the other hand, gives a strict derivation of the Heisenberg formulae from the wave equation, an equation which he interprets in statistical terms. Yet he interprets the Heisenberg formulae which he has just derived from a statistically interpreted premise as limitations upon attainable precision. And he does so in spite of the fact that he notices that this interpretation of the formulae runs counter in some respects to the statistical interpretation of Born. For according to Weyl, Born's interpretation is subject to a correction in the light of the uncertainty relations. It is not merely the case that position and velocity of a particle are just subject to statistical laws, while being precisely determined in every single case. Rather, the very meaning of these concepts depends on the measurements needed to ascertain them, and an exact measurement of the position robs us of the possibility of ascertaining the velocity. The connect perceived by Weyl between Born's statistical interpretation of quantum theory and Heisenberg's limitations upon attainable precision does indeed exist, but it is sharper than Weyl thinks. Not only is it impossible to derive the limitations of attainable precision from the statistically interpreted wave equation, but the fact, which I have still to demonstrate, that neither the possible experiments nor the actual experimental results agree with Heisenberg's interpretation can be regarded as a decisive argument, as a kind of experimentum crucis, in favor of the statistical interpretation of the quantum theory. 76. An attempt to eliminate metaphysical elements by inverting Heisenberg's program, with applications. If we start from the assumption that the formulae which are peculiar to quantum theory are probability hypotheses, and thus statistical statements, then it is difficult to see how prohibitions of single events could be deduced from a statistical theory of this character, except perhaps in the cases of probabilities equal to 1 or to 0. The belief that single measurements can contradict the formulae of quantum physics seems logically untenable, just as untenable as the belief that a contradiction might one day be detected between a formally singular probability statement alpha pk, beta, equals p, say, the probability that the throw k will be ave equals slash, and one of the following two statements, k epsilon beta, the throw is in fact ave, or k epsilon beta, the throw is in fact not ave. These simple considerations provide us with the means of refute any of the alleged proofs which have been designed to show that exact measurements of position and momentum would contradict the quantum theory, or which have been designed, perhaps, to show that the mere assumption that any such measurements are physically possible must lead to contradictions within the theory. For any such proof must make use of quantum theoretical considerations applied to single particles, which means that it has to make use of formally singular probability statements, and further, that it must be possible to translate the proof word for word, as it were into the statistical language. If we do this, then we nd that there is no contradiction between the single measurements which are assumed to be precise, and the quantum theory in its statistical interpretation. There is only an apparent contradiction between these precise measurements and certain formally singular probability statements of the theory. In Appendix V, an example of this type of proof will be examined. But whilst it is wrong to say that the quantum theory rules out exact measurements, it is yet correct to say that from formulae which are peculiar to the quantum theory, provided they are interpreted statistically, no precise singular predictions can be derived. I do not count either the law of conservation of energy nor the law of conservation of momentum among the formulae peculiar to quantum theory. This is so because, in view of the scatter relations, we must fail, more especially, to produce precise initial conditions, by experimentally manipulating the system, i.e. by what we have called physical selection. Now, it is indeed true that the normal technique of the experimenter is to produce or to construct initial conditions, and this allows us to derive from our statistical scatter relations the theorem which, however, only holds for this constructive experimental technique that from quantum theory we cannot obtain any singular predictions, but only frequency predictions. This theorem sums up my attitude to all those imaginary experiments discussed by Heisenberg, who here largely follows Bohr, with the object of proving that it is impossible to make measurements of a precision forbidden by his uncertainty principle. The point is in every case the same: the statistical scatter makes it impossible to predict what the path of the particle will be after the measuring operation. It might well seem that not much has been gained by our reinterpretation of the uncertainty principle. For even Heisenberg asserts in the main, as I have tried to show, no more than that our predictions are subject to this principle, and as in this matter I agree with him up to a point, it might be thought that I am only quarreling about words rather than debating any substantial issue. But this would hardly do justice to my argument. Indeed, I think that Heisenberg's view and mine are diametrically opposed. This will be shown at length in my next section. Meanwhile, I shall attempt to resolve the typical difficulties inherent in Heisenberg's interpretation, and I shall try to make clear how, and why, these difficulties arise. First, we must examine the difficulty over which, as we have seen, Heisenberg's program comes to grief. It is the occurrence, in the formalism, of precise statements of position cum momentum, or in other words, of exact calculations of a path, cf. section, whose physical reality Heisenberg is obliged to leave in doubt, while others, such as Schlick, deny it outright. But the experiments in question, A, B, and C section can all be interpreted in statistical terms. For example, combination, C, i.e. a measurement of position followed by a measurement of momentum, may be realized by an experiment such as the following. We select a ray according to position with the help of a diaphragm with a narrow slit, position measurement. We then measure the momentum of those particles which were traveling from the slit in a d-night direction. This second measurement will of course produce a new scatter of positions. The two experiments together will then determine precisely the path of all those particles which belong to the second selection, insofar as this path lies between the two measurements. Both position and momentum between the two measurements can be precisely calculated. Now these measurements and calculations, which correspond precisely to the elements regarded as superfluous in Heisenberg's interpretation, are on my interpretation of the theory anything but superfluous. Admittedly, they do not serve as initial conditions or as a basis for the derivation of predictions, but they are indispensable nevertheless. They are needed for testing our predictions, which are statistical predictions. For what our statistical scatter relations assert is that the momentum must scatter when positions are more exactly determined, and vice versa. This is a prediction which would not be testable, or falsifiable, if we were not in a position to measure and calculate, with the help of experiments of the kind described, the various scattered momenta which occur immediately after any selection according to position has been made. The statistically interpreted theory, therefore, not only does not rule out the possibility of exact single measurements, but would be untestable, and thus metaphysical, if these were impossible. So the fulfillment of Heisenberg's program, the elimination of metaphysical elements, is here achieved, but by a method the very opposite of his. For while he tried to exclude magnitudes which he regarded as inadmissible, though without entirely succeeding, I invert the attempt, so to speak, by showing that the formalism which contains these magnitudes is correct just because the magnitudes are not metaphysical. Once we have given up the dogma embodied in Heisenberg's limitation upon attainable precision, there is no longer any reason why we should doubt the physical significance of these magnitudes. The scatter relations are frequency predictions about paths, and therefore these paths must be measurable in precisely the same way as, say, throws of VE must be empirically ascertainable if we are to be able to test our frequency predictions about these paths, or about these throws. Heisenberg's rejection of the concept of path, and his talk of non-observable magnitudes, clearly show the ignorance of philosophical and especially of positivistic ideas. Under the same ignorance, March writes, one may say perhaps without fear of being misunderstood that for the physicist a body has reality only in the instant in which he observes it. Naturally nobody is so mad as to assert that a body ceases to exist the moment we turn our backs to it, but it does cease, in that moment, to be an object of inquiry for the physicist, because there exists no possibility of saying anything about it which is based on experiment. In other words, the hypothesis that a body moves in this or that path whilst it is not being observed is non-variable. This, of course, is obvious, but uninteresting. What is important, however, is that this and similar hypotheses are falsifiable. On the basis of the hypothesis that it moves along a certain path we are able to predict that the body will be observable in this or that position, and this is a prediction which can be refuted. That the quantum theory does not exclude this kind of procedure will be seen in the next section. But in fact what we have said here is quite sufficient, for it disposes of all the difficulties connected with the meaninglessness of the concept of path. How much this helps to clear the air will best be realized if we remember the drastic conclusions which were drawn from the alleged failure of the concept of path. Schlick formulates them thus: perhaps the most concise way of describing the situation under review is to say, as the most eminent investigators of quantum problems do, that the validity of the ordinary spatio-temporal concepts is confined to the sphere of the macroscopically observable, and that they are not applicable to atomic dimensions. Here Schlick is probably alluding to Bohr, who writes, therefore one may assume that where the general problem of quantum theory is concerned, it is not a mere question of a change of mechanical and electrodynamic theories, a change which may be described in terms of ordinary physical concepts, but the deep-seated failure of our spatio-temporal images which till now have been used in the description of natural phenomena. Heisenberg adopted this idea of Bohr's, namely the renunciation of spatio-temporal descriptions, as the basis of his program of research. His success seemed to show that this was a fruitful renunciation. But in fact, the program was never carried through. The frequent and unavoidable, if surreptitious, use of spatio-temporal concepts now seems justiciable in the light of our analysis. For this has shown that the statistical scatter relations are statements about the scatter of position cum momentum, and therefore statements about paths. Now that we have shown that the uncertainty relations are formally singular probability statements, we can also unravel the tangled web of their objective and subjective interpretations. We learned in section that every formally singular probability statement can also be interpreted subjectively, as an indefinite prediction, a statement concerning the uncertainty of our knowledge. We have also seen under what assumptions the just and necessary attempt to interpret a statement of this kind objectively is bound to fail. It is bound to fail if one tries to substitute for the statistical objective interpretation a singular objective interpretation, by attributing the uncertainty directly to the single event. Yet if one interprets the Heisenberg formulae, directly, in a subjective sense, then the position of physics as an objective science is imperiled, for to be consistent one would also have to interpret Schrödinger's probability waves subjectively. This conclusion is drawn by Jeans, who says, In brief, the particle picture tells us that our knowledge of an electron is indeterminate, the wave picture that the electron itself is indeterminate, regardless of whether experiments are performed upon it or not. Yet the content of the uncertainty principle must be exactly the same in the two cases. There is only one way of making it so. We must suppose that the wave picture provides a representation not of objective nature, but only of our knowledge of nature. Schrödinger's waves are thus for Jean's subjective probability waves, waves of our knowledge. And with this, the whole subjectivist probability theory invades the realm of physics. The arguments I have rejected the use of Bernoulli's theorem as a bridge from Nescience to statistical knowledge, and similar arguments, cf. section, become inescapable. Jeans formulates the subjectivist attitude of modern physics as follows: Heisenberg attacked the enigma of the physical universe by giving up the main enigma, the nature of the objective universe, as insoluble, and concentrating on the minor puzzle of coordinating our observations of the universe. Thus it is not surprising that the wave picture which now emerged should prove to be concerned solely with our knowledge of the universe as obtained through our observations. Such conclusions will no doubt appear highly acceptable to the positivists. Yet my own views concerning objectivity remain untouched. The statistical statements of quantum theory must be intersubjectively testable in the same way as any other statements of physics. And my simple analysis preserves not only the possibility of spatio-temporal descriptions, but also the objective character of physics. It is interesting that there exists a counterpart to this subjective interpretation of the Schrödinger waves, a non-statistical and thus a directly, i.e. singular, objective interpretation. Schrödinger himself in his famous collected papers on wave mechanics has proposed some such interpretation of his wave equation, which as we have seen is a formally singular probability statement. He tried to identify the particle immediately with the wave packet itself. But his attempt led straight to those difficulties which are so characteristic of this kind of interpretation, I mean the ascription of uncertainty to the physical objects themselves, objectivized uncertainties. Schrödinger was forced to assume that the charge of the electron was blurred or smeared in space, with a charge density determined by the wave amplitude, an assumption which turned out to be incompatible with the atomic structure of electricity. Born's statistical interpretation solved the problem, but the logical connection between the statistical and the non-statistical interpretations remained obscure. Thus it happened that the peculiar character of other formally singular probability statements such as the uncertainty relations remained unrecognized, and that they could continue to undermine the physical basis of the theory. I may conclude perhaps with an application of what has been said in cf. for instance Weyl, Gruppentheorie und Quantenmechanik, p. English translation pp. F. This section to an imaginary experiment proposed by Einstein and called by Jeans one of the most occult parts of the new quantum theory, though I think that our interpretation makes it perfectly clear, if not trivial. Imagine a semi-translucent mirror, i.e. a mirror which reeks part of the light, and lets part of it through. The formally singular probability that one given photon, or light quantum, passes through the mirror, alpha pk, beta, may be taken to be equal to the probability that it will be reacted. We therefore have p beta equals alpha k beta. This probability estimate, as we know, is deemed by objective statistical probabilities, that is to say, it is equivalent to the hypothesis that one half of a given class alpha of light quanta will pass through the mirror whilst the other half will be reacted. Now let a photon k fall upon the mirror, and let it next be experimentally ascertained that this photon has been reacted, then the probabilities seem to change suddenly, as it were, and discontinuously. It is as though before the experiment they had both been equal to, while after the fact of the reaction became known, they had suddenly turned into 0 and 2, respectively. It is plain that this example is really the same as that given in section. And it hardly helps to clarify the situation if this experiment is described, as by Heisenberg, in such terms as the following: by the experiment, i.e. the measurement by which we nd the reacted photon, a kind of physical action, a reduction of wave packets, is exerted from the place where the reacted half of the wave packet is found upon another place as distant as we choose where the other half of the packet just happens to be, a description to which he adds, this physical action is one which spreads with superluminal velocity. Alpha k beta. This is unhelpful since our original probabilities, alpha pk, beta, and p, remain equal to. All that has happened is the choice of a new refer. Ins class beta or beta, instead of alpha, a choice strongly suggested to us by the result of the experiment, i.e. by the information k epsilon beta or k epsilon beta, respectively. Saying of the logical consequences of this choice, or, perhaps, of the logical consequences of this information, that they spread with superluminal velocity is about as helpful as saying that twice 2 turns with superluminal velocity into 4. A further remark of Heisenberg's, to the effect that this kind of propagation of a physical action cannot be used to transmit signals, though true, hardly improves matters. The fate of this imaginary experiment is a reminder of the urgent need to distinguish and to deem the statistical and the formally singular probability concepts. It also shows that the problem of interpretation to which quantum theory has given rise can only be approached by way of a logical analysis of the interpretation of probability statements. 77 Decisive experiments. I have now carried out the RST2 parts of my program outlined in the introduction preceding section. I have shown that the Heisenberg formulae can be statistically interpreted, and therefore, that their interpretation as limitations upon attainable precision does not follow logically from the quantum theory, which therefore could not be contradicted merely by our attaining a higher degree of precision in our measurements. So far, so good, someone might retort. I won't deny that it may be possible to view quantum mechanics in this way. But it still does not seem to me that the real physical core of Heisenberg's theory, the impossibility of making exact singular predictions, has even been touched by your arguments. If asked to elaborate his thesis by means of a physical example, my opponent might proceed as follows: imagine a beam of electrons, like one in a cathode tube. Assume the direction of this beam to be the x direction. We can obtain various physical selections from this beam. For example, we may select or separate a group of electrons according to their position in the x direction, i.e. according to their x coordinates at a certain instant. This could be done, perhaps, by means of a shutter which we open for a very short time. In this way we should obtain a group of electrons whose extension in the x direction is very small. According to the scatter relations, the momenta of the various electrons of this group would differ widely in the x direction, and therefore also their energies. As you rightly stated, we can test such statements about scattering. We can do this by measuring the momenta or the energies of single electrons, and as we know the position, we shall thus obtain both position and momentum. A measurement of this kind may be carried out, for example, by letting the electrons impinge upon a plate whose atoms they would excite. We shall then nd, among other things, some excited atoms whose excitation requires energy in excess of the average energy of these electrons. Thus I admit that you were quite right in stressing that such measurements are both possible and significant. But and now comes my objection: in making any such measurement we must disturb the system we are examining, i.e. either the single electrons, or if we measure many, as in our example, the whole electron beam. Admittedly, the theory would not be logically contradicted if we could know the momenta of the various electrons of the group before disturbing it, so long, of course, as this would not enable us to use our knowledge so as to eke a forbidden selection. But there is no way of obtaining any such knowledge concerning the single electrons without disturbing them. To conclude, it remains true that precise single predictions are impossible. To this objection I should reply that it would not be surprising if it were correct. It is after all obvious that from a statistical theory exact singular predictions can never be derived, but only indefinite, i.e. formally singular, single predictions. But what I assert at this stage is that although the theory does not supply any such predictions, it does not rule them out either. One could speak of the impossibility of singular predictions only if it could be asserted that disturbing the system or interfering with it must prevent every kind of predictive measurement. But that is just what I assert, my opponent will say. I assert, precisely, the impossibility of any such measurement. You assume that it is possible to measure the energy of one of these moving electrons without forcing it out of its path and out of the electron group. This is the assumption which I regard as untenable. For assuming that I possessed any apparatus with which I could make such measurements, then I should with this or some similar apparatus be able to produce aggregates of electrons which all, a, were limited as to their position, and, b, had the same momentum. That the existence of such aggregates would contradict the quantum theory is, of course, your view too, since it is ruled out by your own scatter relations, as you call them. Thus you could only reply that it is possible to conceive of an apparatus which would allow us to take measurements but not to make selections. I admit that this answer is logically permissible, but as a physicist I can only say that my instincts revolt against the idea that we could measure the momenta of electrons while being unable to eliminate, for instance, all those whose momentum exceeds, or falls short of, some given amount. My RST answer to this would be that it all sounds quite convincing. But a strict proof of the contention that, if a predictive measurement is possible, the corresponding physical selection or separation would also be possible, has not been given, and it cannot be given, as will be seen soon. None of these arguments prove that the precise predictions would contradict the quantum theory. They all introduce an additional hypothesis. For the statement, which corresponds to Heisenberg's view, that exact single predictions are impossible, turns out to be equivalent to the hypothesis that predictive measurements and physical selections are inseparably linked. With this new theoretical system, the conjunction of the quantum theory with this auxiliary hypothesis of linkage, my conception must indeed clash. With this point of my program has been carried out. But point has still to be established, that is, we have still to show that the system which combines the statistically interpreted quantum theory, including, we assume, the conservation laws for momentum and energy, with the hypothesis of linkage, is self-contradictory. There is, I suppose, a deep-seated presumption that predictive measurement and physical selection are always linked. The prevalence of this presumption may explain why the simple arguments which would establish the opposite have never been worked out. I wish to stress that the mainly physical considerations now to be presented do not form part of the assumptions or premises of my logical analysis of the uncertainty relations, although they might be described as its fruit. In fact, the analysis so far carried out is quite independent of what follows, especially of the imaginary physical experiment described below, which is intended to establish the possibility of arbitrarily precise predictions of the path of single particles. By way of introduction to this imaginary experiment, I will discuss a few simpler experiments. These are intended to show that we can without difficulty make arbitrarily precise path predictions, and also test them. At this stage I only consider predictions which do not refer to finite single particles, but refer to all particles within a finite small space-time region, x.y.z.t. In each case there is only a certain probability that particles are present in that region. We again imagine a beam, an electron or light beam, of particles traveling in the x direction. But this time we assume it to be monochromatic, so that all the particles are traveling along parallel paths in the x direction with the same known momentum. The components in the other directions of the momentum will then also be known, that is, known to be equal to 0. Now instead of determining the position in the x direction of a group of particles by means of a physical selection instead, that is, of isolating the group of particles from the rest of the beam by technical means, as we did above, we shall be content to differentiate this group from the rest merely by focusing our attention upon it. For example, we may focus our attention upon all those particles which have, with a given precision, in a given instant the place coordinate x, and which therefore do not spread beyond an arbitrarily small range x. Of each of these particles we know the momentum precisely. We therefore know for each future instant precisely where this group of particles is going to be. It is clear that the mere existence of such a group of particles does not contradict quantum theory, only its separate existence, that is, the possibility of selecting it physically, would contradict the theory. We can carry out the same kind of imaginary selection in connection with the other space coordinates. The physically selected monochromatic beam would have to be very wide in the y and z directions, infinitely wide in the case of an ideal monochromatic beam, because in these directions the momentum is supposed to be selected with precision, i.e. to be equal to O, so that positions in these directions must be widely spread. Nevertheless, we can again focus our attention upon a very narrow partial ray. Again, we shall not only know the position but also the momentum of every particle of this ray. We shall therefore be able to predict for every particle of this narrow ray, which we have, as it were, selected in imagination, at which point, and with what momentum, it will impinge upon a photographic plate set in its path, and of course we can test this prediction empirically, as with the former experiment. Imaginary selections, analogous to the one just made from a pure case of a particular type, can be made from other types of aggregates. For example, we may take a monochromatic beam from which a physical selection has been made by means of a very small slit y, thus taking as our physical starting point a physical selection corresponding to the merely imagined selection of the preceding example. We do not know of any of the particles in which direction it will turn after passing through the slit, but if we consider 1D direction we can calculate precisely the momentum component of all particles that did turn in this particular direction. Thus the particles which after having passed through the slit travel in 1D direction again form an imagined selection. We are able to predict their position and their momentum, or in short, their paths, and again, by putting a photographic plate in their path, we can test our predictions. The situation is in principle the same, even though empirical tests are somewhat more difficult, in the case of the RST example we considered, namely the selection of particles according to their position in the direction of travel. If we produce a physical selection corresponding to this case, then diarrhent particles will travel with diarrhent velocities, because of the spread of the momenta. The group of particles will thus spread over an increasing range in the x direction as it proceeds. The packet will get wider. We can then work out the momentum of a partial group of these particles, selected in imagination, which, in a given moment, will be at a given position in the x direction. The momentum will be the greater the farther ahead is the selected partial group, and vice versa. The empirical test of the prediction made in this way could be carried out by substituting for the photographic plate a moving strip of photographic LM. As we could know of each point in the band the time of its exposure to the impact of the electrons, we could also predict for each point on the band with what momentum the impacts would occur. These predictions we could test, for example by inserting a LDR in front of the moving band or perhaps in front of the Geiger counter, a LDR in the case of light rays, in the case of electrons an electric eld at right angles to the direction of the ray, followed by a selection according to direction, allowing only those particles to pass which possess a given minimum momentum. We could then ascertain whether these particles really did arrive at the predicted time or not. The precision of the measurements involved in these tests is not limited by the uncertainty relations. These are meant to apply, as we have seen, mainly to those measurements which are used for the deduction of predictions, and not for testing them. They are meant to apply, that is to say, to predictive measurements rather than to non-predictive measurements. In sections and I examined three cases of such non-predictive measurements, namely, a. measurement of two positions, b. measurement of position preceded or, c. succeeded by a measurement of momentum. The above discussed measurement by means of a LDR in front of a LM strip of a Geiger counter exemplifies, b. i.e. a selection according to momentum followed by a measurement of position. This is presumably just that case which, according to Heisenberg, cf. section, permits a calculation about the past of the electron. For while in cases, A, and, C, only calculations for the time between the two measurements are possible, it is possible in case, b. To calculate the path prior to the RST measurement, provided this measurement was a selection according to a given momentum, for such a selection does not disturb the position of the particle. Heisenberg, as we know, questions the physical reality of this measurement, because it permits us to calculate the momentum of the particle only upon its arrival at a precisely measured position and at a precisely measured time. The measurement seems to lack predictive content because no testable conclusion can be derived from it. Yet I shall base my imaginary experiment, intended to establish the possibility of precisely predicting the position and momentum of a d-night particle, upon this particular measuring arrangement which at RST site is apparently non-predictive. As I am about to derive such far-reaching consequences from the assumption that precise non-predictive measurements of this type are possible, it seems proper to discuss the admissibility of this assumption. This is done in Appendix 6. With the imaginary experiment that follows here, I directly challenge the method of arguing which Bohr and Heisenberg have used in order to justify the interpretation of the Heisenberg formulae as limitations upon attainable precision. For they tried to justify this interpretation by showing that no imaginary experiment can be devised which will produce more exact predictive measurements. But this method of arguing can clearly not exclude the possibility that an imaginary experiment might someday be devised which, using known physical eques and laws, would show that such measurements are possible after all. It was taken for granted that any such experiment would contradict the formalism of the quantum theory, and it appears that this idea determined the direction of the search for such experiments. My analysis, the carrying out of the points of my program, has however cleared the way for an imaginary experiment to be devised which shows, in full agreement with quantum theory, that the precise measurements in question are possible. To carry out this experiment, I shall make use of imaginary selection, as before, but shall choose an arrangement such that, if a particle which is characterized by the selection really exists, we shall be able to ascertain the fact. My experiment, in a way, forms a kind of idealization of the experiments of Compton-Simon and Bode-Geiger. Since we wish to obtain singular predictions, we cannot operate with statistical assumptions only. The non-statistical laws of the conservation of energy and momentum will have to be used. We can exploit the fact that these laws permit us to calculate what occurs when the particles collide, provided we are given two of the four magnitudes which describe the collision, i.e. of the momenta and b before, and b after the collision, and one component of a third one. The method of calculation is well known as part of the theory of the Compton-Echt. Let us now imagine the following experimental arrangement. C. Gur. We cross two particle beams, of which one at most may be a light ray, and one at most may be electrically non-neutral, which are both pure cases in the sense that the beam A is monochromatic, that is, a selection according to the momentum A, whilst the beam B passes through a narrow slit SL and is thereby subjected to a physical selection according to position. The B particles may be supposed to have the absolute momentum B. Some of the particles of these two beams will collide. We now imagine two narrow partial rays A and B which intersect at the place P. The momentum of A is known, it is A. The momentum of the partial ray B becomes calculable as soon as we have decided upon a d-night direction for it, let it be B. We now choose a direction px. Attending to those particles of the partial ray A which after the collision travel in the direction px, we can calculate their momentum A, and also B, i.e. the momentum after collision of the particles with which they collided. To every particle of A which was detected at the point P with the momentum A, in the direction x, there must correspond a second particle, of B, which was detected at P with the momentum B, in the calculable direction π. We now place an apparatus at x, for instance a Geiger counter or a moving LM strip which records the impacts of particles arriving from P at the arbitrarily restricted region x. Then we can say, as we note any such recording of a particle, we learn at the same time that a second particle must be traveling from P with the momentum B towards y. And we also learn from the recording where this second particle was at any given moment, for we can calculate from the time of the impact of the RST particle at x, and from its known velocity, the moment of its collision at p. By using another Geiger counter at y, or the moving Lm band, we can test our predictions for the second particle. The precision of these predictions as well as that of the measurements undertaken to test them is in principle not subject to any of the limitations due to the uncertainty principle, as regards both the position co-ordinate and the component of the momentum in the direction π. For my imaginary experiment reduces the question of the precision with which predictions can be made about a B particle dictated in P to the question of the precision attainable in taking measurements at x. These, at RST, seem to be non-predictive measurements of the time, position, and momentum of the corresponding RST particle A. The momentum of this particle in the px direction as well as the time of its impact at x, i.e. of its position in the ps direction, can be measured with any desirable degree of precision, cf. Appendix 6, if we make a momentum selection. By interposing, for instance, an electrical eld or ailter in front of the Geiger counter, before we measure the position. But in consequence of this, as will be shown more fully in Appendix 7, we can make predictions with any degree of precision about the B particle traveling in the π direction. This imaginary experiment allows us to see not only that precise single predictions can be made, but also under what conditions they can be made, or better, under what conditions they are compatible with the quantum theory. They can be made only if we can obtain knowledge about the state of the particle without being able to create the state at will. Thus we really obtain our knowledge after the event, as it were, since at the time when we obtain it the particle will already have assumed its state of motion. Yet we can still make use of this knowledge to deduce from it testable predictions. If the B particle in question is a photon, for instance, we might be able to calculate the time of its arrival on Sirius. The impacts of particles arriving at x will succeed each other at irregular time intervals, which means that the particles of the partial ray B about which we are making predictions will also succeed each other after irregular time intervals. It would contradict the quantum theory if we could alter the state of things by, for example, making these time intervals equal. Thus we are able, as it were, to take aim and to predetermine the force of the bullet. We can also, and this before the bullet hits the target y, calculate the exact time at which the shot was read at p. Yet we cannot freely choose the moment of ring, but have to wait till the gun goes a. Nor can we prevent uncontrolled shots being read in the direction of our target, from the neighborhood of p. It is clear that our experiment and Heisenberg's interpretation are incompatible. But since the possibility of carrying out this experiment can be deduced from the statistical interpretation of quantum physics, with the addition of the laws of energy and momentum, it appears that Heisenberg's interpretation, in contradicting it, must also contradict the statistical interpretation of quantum theory. In view of the experiments of Compton-Simon and Bode-Geiger, it would seem that it is possible to carry out our experiment. It can be regarded as a kind of experiment crucis to decide between Heisenberg's conception and a consistently statistical interpretation of quantum theory. 78. Indeterminist metaphysics. It is the task of the natural scientist to search for laws which will enable him to deduce predictions. This task may be divided into two parts. On the one hand, he must try to discover such laws as will enable him to deduce single predictions, causal or deterministic laws or precision statements. On the other hand, he must try to advance hypotheses about frequencies, that is, laws asserting probabilities, in order to deduce frequency predictions. There is nothing in these two tasks to make them in any way mutually incompatible. It is clearly not the case that whenever we make precision statements we shall make no frequency hypotheses, for some precision statements are, as we have seen, macro laws which are derivable from frequency assumptions. Nor is it the case that whenever in a particular ELD frequency statements are well confirmed, we are entitled to conclude that in this ELD no precision statements can be made. This situation seems plain enough. Yet the second of the two conclusions we have just rejected has been drawn again and again. Again and again we meet with the belief that where fortuity rules, regularity is ruled out. I have critically examined this belief in section The dualism of macro and micro laws, I mean the fact that we operate with both, will not be easily overcome, to judge by the present state of scientific development. What might be logically possible, however, is a reduction of all known precision statements by interpreting them as macro laws to frequency statements. The converse reduction is not possible. Frequency statements can never be deduced from precision statements, as we have seen in section 0. They need their own assumptions, which must be specifically statistical. Only from probability estimates can probabilities be calculated. This is the logical situation. It encourages neither a deterministic nor an indeterministic view. And should it ever become possible to work in physics with nothing but frequency statements, then we should still not be entitled to draw indeterminist conclusions, which is to say that we should still not be entitled to assert that there are no precise laws in nature, no laws from which predictions about the course of single or elementary processes can be deduced. The scientist will never let anything stop him searching for laws, including laws of this kind. And however successfully we might operate with probability estimates, we must not conclude that the search for precision laws is vain. These reactions are not by any means the outcome of the imaginary experiment described in section, quite the contrary. Let us assume that the uncertainty relations are not refuted by this experiment, for whatever reason, say, because the experimentum crucis described in Appendix 6 would decide against the quantum theory. Even then they could only be tested as frequency statements and could only be corroborated as frequency statements. Thus in no case should we be entitled to draw indeterministic conclusions from the fact that they are well corroborated. Is the world ruled by strict laws or not? This question I regard as metaphysical. The laws we nd are always hypotheses, which means that they may always be superseded, and that they may possibly be deduced from probability estimates. Yet denying causality would be the same as attempting to persuade the theorist to give up his search, and that such an attempt cannot be backed by anything like a proof has just been shown. The so-called causal principle or causal law, however it may be formulated, is very different in character from a natural law, and I cannot agree with Schlick when he says, the causal law can be tested as to its truth, in precisely the same sense as any other natural law. The belief in causality is metaphysical. It is nothing but a typical metaphysical hypostatization of a well-justified methodological rule, the scientist's decision never to abandon his search for laws. The metaphysical belief in causality seems thus more fertile in its various manifestations than any indeterminist metaphysics of the kind advocated by Heisenberg. Indeed, we can see that Heisenberg's comments have had a crippling effect on research. Connections which are not far to seek may easily be overlooked if it is continually repeated that the search for any such connections is meaningless. Heisenberg's formulae, like similar statements which can only be corroborated by their statistical consequences, do not necessarily lead to indeterminist conclusions. But this in itself does not prove that there can be no other empirical statement which justifies these or similar conclusions. For example, the conclusion that the methodological rule mentioned, the decision never to abandon the search for laws, cannot fool its purpose, perhaps because it is futile or meaningless or impossible, cf. note to section, to search for laws and for singular predictions. But there could not be an empirical statement having methodological consequences which could compel us to abandon the search for laws. For a statement supposed to be free from metaphysical elements can have indeterminist conclusions only if these are falsifiable. But they can be shown to be false only if we succeed in formulating laws, and in deducing predictions from them which are corroborated. Accordingly, if we assume that these indeterminist conclusions are empirical hypotheses, we ought to try hard to test them, i.e. to falsify them. And this means that we ought to search for laws and predictions. Thus we cannot obey an exhortation to abandon this search without repudiating the empirical character of these hypotheses. This shows that it would be self-contradictory to think that any empirical hypothesis could exist which might compel us to abandon the search for laws. I do not intend to show here in detail how so many attempts to establish indeterminism reveal a mode of thought which can only be described as determinist, in the metaphysical sense. Heisenberg, for instance, tries to give a causal explanation why causal explanations are impossible. I may just remind the reader of the attempts to demonstrate that the uncertainty relations close some avenues of possible research, as does the principle of the constancy of light velocity, the analogy between the two constants c and h, the velocity of light and Planck's constant, was interpreted by saying that both set a limit, in principle, to the possibilities of research. Questions raised in the attempt to grope beyond these barriers were dismissed by the well-known method of dismissing unpalatable problems as pseudo. In my view, there is indeed an analogy between the two constants c and h, one which, incidentally, ensures that the constant h is no more a barrier to research than the constant c. The principle of the constancy of light velocity, and of the impossibility of exceeding this velocity, does not forbid us to search for velocities which are greater than that of light, for it only asserts that we shall not nd any, that is to say, that we shall be unable to produce signals that travel faster than light. And similarly, the Heisenberg formulae ought not to be interpreted as forbidding the search for superpure cases, for they only assert that we shall not nd any, and, in particular, that we cannot produce any. The laws forbidding velocities greater than that of light and superpure cases challenge the investigator, as do other empirical statements, to search for the forbidden. For he can test empirical statements only by trying to falsify them. From an historical point of view, the emergence of indeterminist metaphysics is understandable enough. For a long time, physicists believed in determinist metaphysics. And because the logical situation was not fully understood, the failure of the various attempts to deduce the light spectra which are statistical leaks from a mechanical model of the atom was bound to produce a crisis for determinism. Today we see clearly that this failure was inevitable, since it is impossible to deduce statistical laws from a non-statistical, mechanical, model of the atom. But at that time, about the time of the theory of Bohr, Kramers, and Slater, it could not but seem as if in the mechanism of each single atom, probabilities were taking the place of strict laws. The determinist edus was wrecked mainly because probability statements were expressed as formally singular statements. On the ruins of determinism, indeterminism rose, supported by Heisenberg's uncertainty principle. But it sprang, as we now see, from that same misunderstanding of the meaning of formally singular probability statements. The lesson of all this is that we should try to nd strict laws prohibitions that can founder upon experience. Yet we should abstain from issuing prohibitions that draw limits to the possibilities of research. 0. Corroboration, or how a theory stands up to tests. Theories are not variable, but they can be corroborated. The attempt has often been made to describe theories as being neither true nor false, but instead more or less probable. Inductive logic, more especially, has been developed as a logic which may ascribe not only the two values true and false to statements, but also degrees of probability, a type of logic which will here be called probability logic. According to those who believe in probability logic, induction should determine the degree of probability of a statement. And a principle of induction should either make it sure that the induced statement is probably valid or else it should make it probable, in its turn, for the principle of induction might itself be only probably valid. Yet in my view, the whole problem of the probability of hypotheses is misconceived. Instead of discussing the probability of a hypothesis, we should try to assess what tests, what trials, it has withstood, that is, we should try to assess how far it has been able to prove its fitness to survive by standing up to tests. In brief, we should try to assess how far it has been corroborated. 79. Concerning the so-called verification of hypotheses. The fact that theories are not variable has often been overlooked. People often say of a theory that it is varied when some of the predictions derived from it have been varied. They may perhaps admit that the verification is not completely impeccable from a logical point of view, or that a statement can never be nally established by establishing some of its consequences. But they are apt to look upon such objections as due to somewhat unnecessary scruples. It is quite true, they say, and even trivial, that we cannot know for certain whether the sun will rise tomorrow, but this uncertainty may be neglected, the fact that theories may not only be improved but that they can also be falsified by new experiments presents to the scientist a serious possibility which may at any moment become actual, but never yet has a theory had to be regarded as falsified owing to the sudden breakdown of a well-confirmed law. It never happens that old experiments one day yield new results. What happens is only that new experiments decide against an old theory. The old theory, even when it is superseded, often retains its validity as a kind of limiting case of the new theory. It still applies, at least with a high degree of approximation, in those cases in which it was successful before. In short, regularities which are directly testable by experiment do not change. Admittedly, it is conceivable, or logically possible, that they might change, but this possibility is disregarded by empirical science and does not eke its methods. On the contrary, scientific method presupposes the immutability of natural processes, or the principle of the uniformity of nature. There is something to be said for the above argument, but it does not eke my thesis. It expresses the metaphysical faith in the existence of regularities in our world, a faith which I share, and without which practical action is hardly conceivable. Yet the question before us, the question which makes the non-variability of theories significant in the present context, is on an altogether different plane. Consistently with my attitude towards other metaphysical questions, I abstain from arguing for or against faith in the existence of regularities in our world. But I shall try to show that the non-variability of theories is methodologically important. It is on this plane that I oppose the argument just advanced. I shall therefore take up as relevant only one of the points of this argument, the reference to the so-called principle of the uniformity of nature. This principle, it seems to me, expresses in a very superficial way an important methodological rule, and one which might be derived, with advantage, precisely from a consideration of the non-variability of theories. Let us suppose that the sun will not rise tomorrow, and that we shall nevertheless continue to live, and also to pursue our scientific interests. Should such a thing occur, science would have to try to explain it, i.e., to derive it from laws. Existing theories would presumably require to be drastically revised. But the revised theories would not merely have to account for the new state of affairs, our older experiences would also have to be derivable from them. From the methodological point of view, one sees that the principle of the uniformity of nature is here replaced by the postulate of the invariance of natural laws, with respect to both space and time. I think, therefore, that it would be a mistake to assert that natural regularities do not change. This would be a kind of statement that can neither be argued against nor argued for. What we should say is, rather, that it is part of our definition of natural laws if we postulate that they are to be invariant with respect to space and time, and also if we postulate that they are to have no exceptions. Thus, from a methodological point of view, the possibility of falsifying a corroborated law is by no means without significance. It helps us to end out what we demand and expect from natural laws. And the principle of the uniformity of nature can again be regarded as a metaphysical interpretation of a methodological rule like its near relative, the law of causality. One attempt to replace metaphysical statements of this kind by principles of method leads to the principle of induction, supposed to govern the method of induction, and hence that of the verification of theories. But this attempt fails, for the principle of induction is itself metaphysical in character. As I have pointed out in section, the assumption that the principle of induction is empirical leads to an innate regress. It could therefore only be introduced as a primitive proposition, or a postulate, or an axiom. This would perhaps not matter so much, were it not that the principle of induction would have in any case to be treated as a non-falsifiable statement. For if this principle, which is supposed to validate the inference of theories, were itself falsifiable, then it would be falsified with the RST falsified theory, because this theory would then be a conclusion, derived with the help of the principle of induction, and this principle, as a premise, will of course be falsified by the modus tollens whenever a theory is falsified which was derived from it. But this means that a falsifiable principle of induction would be falsified anew with every advance made by science. It would be necessary, therefore, to introduce a principle of induction assumed not to be falsifiable. But this would amount to the misconceived notion of a synthetic statement which is a priori valid, i.e., an irrefutable statement about reality. Thus, if we try to turn our metaphysical faith in the uniformity of nature and in the variability of theories into a theory of knowledge based on inductive logic, we are left only with the choice between an innate regress and a priorism. 80. The probability of a hypothesis and the probability of events. Criticism of probability logic. Even if it is admitted that theories are never nulli verid, may we not succeed in making them secure to a greater or lesser extent more probable, or less so? After all, it might be possible that the question of the probability of a hypothesis could be reduced, say, to that of the probability of events, and thus be made susceptible to mathematical and logical handling. Like inductive logic in general, the theory of the probability of hypotheses seems to have arisen through a confusion of psychological with logical questions. Admittedly, our subjective feelings of conviction are of different intensities, and the degree of confidence with which we await the fulfillment of a prediction and the further corroboration of a hypothesis is likely to depend, among other things, upon the way in which this hypothesis has stood up to test so far upon its past corroboration. But that these psychological questions do not belong to epistemology or methodology is pretty well acknowledged even by the believers in probability logic. They argue, however, that it is possible, on the basis of inductivist decisions, to ascribe degrees of probability to the hypotheses themselves, and further, that it is possible to reduce this concept to that of the probability of events. The probability of a hypothesis is mostly regarded as merely a special case of the general problem of the probability of a statement, and this in turn is regarded as nothing but the problem of the probability of an event, expressed in a particular terminology. Thus we read in Reichenbach, for example, whether we ascribe probability to statements or to events is only a matter of terminology. So far we have regarded it as a case of the probability of events that the probability of / has been assigned to the turning up of a certain face of a die. But we might just as well say that it is the statement the face showing the eye will turn up which has been assigned the probability of / This identification of the probability of events with the probability of statements may be better understood if we recall what was said in section. There the concept event was deemed as a class of singular statements. It must therefore also be permissible to speak of the probability of statements in place of the probability of events. So we can regard this as being merely a change of terminology. The reference sequences are interpreted as sequences of statements. If we think of an alternative, or rather of its elements, as represented by statements, then we can describe the turning up of heads by the statement K is heads, and its failure to turn up by the negation of this statement. In this way we obtain a sequence of statements of the form Pj, Pk, Pl, Pm, Pn, in which a statement pi is sometimes characterized as true, and sometimes, by placing a bar over its name, as false. Probability within an alternative can thus be interpreted as the relative truth frequency of statements within a sequence of statements, rather than as the relative frequency of a property. If we like, we can call the concept of probability, so transformed, the probability of statements or the probability of propositions. And we can show a very close connection between this concept and the concept of truth. For if the sequence of statements becomes shorter and shorter and in the end contains only one element, i.e. only one single statement, then the probability, or truth frequency, of the sequence can assume only one of the two values and 0, according to whether the single statement is true or false. The truth or falsity of a statement can thus be looked upon as a limiting case of probability, and conversely, probability can be regarded as a generalization of the concept of truth, insofar as it includes the latter as a limiting case. Finally, it is possible to deal operations with truth frequencies in such a way that the usual truth operations of classical logic become limiting cases of these operations. And the calculus of these operations can be called probability logic. But can we really identify the probability of hypotheses with the probability of statements, deemed in this manner, and thus indirectly with the probability of events? I believe that this identification is the result of a confusion. The idea is that the probability of a hypothesis, since it is obviously a kind of probability of a statement, must come under the head of probability of statements in the sense just deemed. But this conclusion turns out to be unwarranted, and the terminology is thus highly unsuitable. Perhaps after all it would be better never to use the expression probability of statements if we have the probability of events in mind. However this may be, I assert that the issues arising from the concept of a probability of hypotheses are not even touched by considerations based on probability logic. I assert that if one says of a hypothesis that it is not true but probable, then this statement can under no circumstances be translated into a statement about the probability of events. For if one attempts to reduce the idea of a probability of hypotheses to that of a truth frequency which uses the concept of a sequence of statements, then one is at once confronted with the question, with reference to what sequence of statements can a probability value be assigned? To a hypothesis? Reichenbach identifies an assertion of natural science by which he means a scientific hypothesis itself with a reference sequence of statements. He says, the assertions of natural science, which are never singular statements, are in fact sequences of statements to which, strictly speaking, we must assign not the degree of probability I but a smaller probability value. It is therefore only probability logic which provides the logical form capable of strictly representing the concept of knowledge proper to natural science. Let us now try to follow up the suggestion that the hypotheses themselves are sequences of statements. One way of interpreting it would be to take, as the elements of such a sequence, the various singular statements which can contradict, or agree with, the hypothesis. The probability of this hypothesis would then be determined by the truth frequency of those among these statements which agree with it. But this would give the hypothesis a probability of if, on the average, it is refuted by every second singular statement of the sequence. In order to escape from this devastating conclusion, we might try two more expedients. One would be to ascribe to the hypothesis a certain probability, perhaps not a very precise one, on the basis of an estimate of the ratio of all the tests passed by it to all the tests which have not yet been attempted. But this way too leads nowhere. For this estimate can, as it happens, be computed with precision, and the result is always that the probability is zero. And nally, we could try to base our estimate upon the ratio of those tests which led to a favorable result to those which led to an indifferent result, i.e. one which did not produce a clear decision. In this way one might indeed obtain something resembling a measure of the subjective feeling of condensation with which the experimenter views his results. But this last expedient will not do either, even if we disregard the fact that with this kind of estimate we have strayed a long way from the concept of a truth frequency, and that of a probability of events. These concepts are based upon the ratio of the true statements to those which are false. And we must not, of course, equate an indifferent statement with one that is objectively false. The reason why this last attempt fails too is that the suggested definition would make the probability of a hypothesis hopelessly subjective. The probability of a hypothesis would depend upon the training and skill of the experimenter rather than upon objectively reproducible and testable results. But I think it is altogether impossible to accept the suggestion that a hypothesis can be taken to be a sequence of statements. It would be possible if universal statements had the form, for every value hfk it is true that at the place k so and so occurs. If universal statements had this form, then we could regard basic statements, those that contradict, or agree with, the universal statement, as elements of a sequence of statements, the sequence to be taken for the universal statement. But as we have seen, cf sections and, universal statements do not have this form. Basic statements are never derivable from universal statements alone. The latter cannot therefore be regarded as sequences of basic statements. If, however, we try to take into consideration the sequence of those negations of basic statements which are derivable from universal statements, then the estimate for every self-consistent hypothesis will lead to the same probability, namely I. For we should then have to consider the ratio of the non-falsied negated basic statements which can be derived, or other derivable statements, to the falsied ones. This means that instead of considering a truth frequency we should have to consider the complementary value of a falsity frequency. This value however would be equal to, for the class of derivable statements, and even the class of the derivable negations of basic statements, are both inite. On the other hand, there cannot be more than at most a finite number of accepted falsifying basic statements. Thus even if we disregard the fact that universal statements are never sequences of statements, and even if we try to interpret them as something of the kind and to correlate with them sequences of completely decidable singular statements, even then we do not reach an acceptable result. We have yet to examine another, quite different, possibility of explaining the probability of a hypothesis in terms of sequences of statements. It may be remembered that we have called a given singular occurrence probable, in the sense of a formally singular probability statement, if it is an element of a sequence of occurrences with a certain probability. Similarly, one might try to call a hypothesis probable if it is an element of a sequence of hypotheses with a finite truth frequency. But this attempt again fails quite apart from the difficulty of determining the reference sequence. It can be chosen in many ways, cf. section. For we cannot speak of a truth frequency within a sequence of hypotheses, simply because we can never know of a hypothesis whether it is true. If we could know this, then we should hardly need the concept of the probability of a hypothesis at all. Now we might try, as above, to take the complement of the falsity frequency within a sequence of hypotheses as our starting point. But if, say, we deem the probability of a hypothesis with the help of the ratio of the non-falsied to the falsied hypotheses of the sequence, then, as before, the probability of every hypothesis within every inite reference sequence will be equal to. And even if a inite reference sequence were chosen, we should be in no better position. For let us assume that we can ascribe to the elements of some inite sequence of hypotheses a degree of probability between 0 and, in accordance with this procedure, say, the value /. This can be done if we obtain the information that this or that hypothesis belonging to the sequence has been falsied. Insofar as these falsied hypotheses are elements of the sequence, we thus would have to ascribe to them, just because of this information, not the value O, but /. And in general, the probability of a hypothesis would decrease by /n in consequence of the information that it is false, where n is the number Burr of hypothesis in the reference sequence. All this glaringly contradicts the program of expressing, in terms of a probability of hypotheses, the degree of reliability which we have to ascribe to a hypothesis in view of supporting or undermining evidence. This seems to me to exhaust the possibilities of basing the concept of the probability of a hypothesis on that of the frequency of true statements, or the frequency of false ones, and thereby on the frequency theory of the probability of events. I think we have to regard the attempt to identify the probability of a hypothesis with the probability of events as a complete failure. This conclusion is quite independent of whether we accept the claim, it is Reichenbach's, that all hypotheses of physics are in reality, or on closer examination nothing but probability statements, about some average frequencies within sequences of observations which always show deviations from some mean value, or whether we are inclined to make a distinction between two different types of natural laws, between the deterministic or precision laws on the one hand, and the probability laws or hypotheses of frequency on the other. For both of these types are hypothetical assumptions which in their turn can never become probable, they can only be corroborated, in the sense that they can prove their mettle under the re of our tests. How are we to explain the fact that the believers in probability logic have reached an opposite view? Wherein lies the error made by Jeans when he writes at RST, in a sense with which I can fully agree, that we can know nothing for certain, but then goes on to say, at best we can only deal in probabilities. And the predictions of the new quantum theory agree so well with the observations that the odds in favor of the scheme having some correspondence with reality are enormous. Indeed, we may say the scheme is almost certain to be quantitatively true. Undoubtedly the commonest error consists in believing that hypothetical estimates of frequencies, that is to say, hypotheses regarding probabilities, can in their turn be only probable, or in other words, in ascribing to hypotheses of probability some degree of an alleged probability of hypotheses. We may be able to produce a persuasive argument in favor of this erroneous conclusion if we remember that hypotheses regarding probabilities are, as far as their logical form is concerned, and without reference to our methodological requirement of falsiability, neither variable nor falsiable. Cf. sections 2. They are not variable because they are universal statements, and they are not strictly falsiable because they can never be logically contradicted by any basic statements. They are thus, as Reichenbach puts it, completely undecidable. Now they can, as I have tried to show, be better, or less well, confirmed, which is to say that they may agree more, or less, with accepted basic statements. This is the point where, it may appear, probability logic comes in. The symmetry between variability and falsiability accepted by classical inductivist logic suggests the belief that it must be possible to correlate with these undecidable probability statements some scale of degrees of validity, something like continuous degrees of probability whose unattainable upper and lower limits are truth and falsity, to quote Reichenbach again. According to my view, however, probability statements, just because they are completely undecidable, are metaphysical unless we decide to make them falsiable by accepting a methodological rule. Thus the simple result of their non-falsiability is not that they can be better, or less well corroborated, but that they cannot be empirically corroborated at all. For otherwise, seeing that they rule out nothing, and are therefore compatible with every basic statement, they could be said to be corroborated by every arbitrarily chosen basic statement, of any degree of composition, provided it describes the occurrence of some relevant instance. I believe that physics uses probability statements only in the way which I have discussed at length in connection with the theory of probability, and more particularly that it uses probability assumptions, just like other hypotheses, as falsiable statements. But I should decline to join in any dispute about how physicists in fact proceed, since this must remain largely a matter of interpretation. We have here quite a nice illustration of the contrast between my view and what I called, in section 0, the naturalistic view. What can be shown is, RST, the internal logical consistency of my view, and secondly, that it is free from those difficulties which beset other views. Admittedly, it is impossible to prove that my view is correct, and a controversy with upholders of another logic of science may well be futile. All that can be shown is that my approach to this particular problem is a consequence of the conception of science for which I have been arguing. 81. Inductive logic and probability logic. The probability of hypotheses cannot be reduced to the probability of events. This is the conclusion which emerges from the examination carried out in the previous section. But might not a diarrhent approach lead to a satisfactory definition of the idea of a probability of hypotheses? I do not believe that it is possible to construct a concept of the probability of hypotheses which may be interpreted as expressing a degree of validity of the hypothesis, in analogy to the concepts true and false, and which, in addition, is sufficiently closely related to the concept objective probability, i.e. to relative frequency, to justify the use of the word probability. Nevertheless, I will now, for the sake of argument, adopt the supposition that such a concept has in fact been successfully constructed, in order to raise the question, how would this eat the problem of induction? Let us suppose that a certain hypothesis, say Schrödinger's theory, is recognized as probable in some finite sense, either as probable to this or that numerical degree, or merely as probable, without specification of a degree. The statement that describes Schrödinger's theory as probable we may call its appraisal. An appraisal must, of course, be a synthetic statement and assertion about reality in the same way as would be the statement Schrödinger's theory is true or Schrödinger's theory is false. All such statements obviously say something about the adequacy of the theory, and are thus certainly not tautological. They say that a theory is adequate or inadequate, or that it is adequate in some degree. Further, an appraisal of Schrödinger's theory must be a non-variable synthetic statement, just like the theory itself. For the probability of a theory, that is, the probability that the theory will remain acceptable, cannot, it appears, be deduced from basic statements with nullity. Therefore we are forced to ask, how can the appraisal be just EED? How can it be tested? Thus the problem of induction arises again, see section. As to the appraisal itself, this may either be asserted to be true, or it may, in its turn, be said to be probable. If it is regarded as true, then it must be a true synthetic statement which has not been empirically varied, a synthetic statement which is a priori true. If it is regarded as probable, then we need a new appraisal, an appraisal of the appraisal, as it were, and therefore an appraisal on a higher level. But this means that we are caught up in an innate regress. The appeal to the probability of the hypothesis is unable to improve the precarious logical situation of inductive logic. Most of those who believe in probability logic uphold the view that the appraisal is arrived at by means of a principle of induction which ascribes probabilities to the induced hypotheses. But if they ascribe a probability to this principle of induction in its turn, then the innate regress continues. If on the other hand they ascribe truth to it, then they are left with the choice between innate regress and a priorism. Once and for all, says Hymans, the theory of probability is incapable of explaining inductive arguments, for precisely the same problem which lurks in the one also lurks in the other, in the empirical application of probability theory. In both cases the conclusion goes beyond what is given in the premises. Thus nothing is gained by replacing the word true by the word probable, and the word false by the word improbable. Only if the asymmetry between verification and falsification is taken into account, that asymmetry which results from the logical relation between theories and basic statements, is it possible to avoid the pitfalls of the problem of induction. Believers in probability logic may try to meet my criticism by asserting that it springs from a mentality which is tied to the framework of classical logic, and which is therefore incapable of following the methods of reasoning employed by probability logic. I freely admit that I am incapable of following these methods of reasoning. 82. The positive theory of corroboration, how a hypothesis may prove its mettle. Cannot the objections I have just been advancing against the probability theory of induction be turned, perhaps, against my own view? It might well seem that they can, for these objections are based on the idea of an appraisal. And clearly, I have to use this idea too. I speak of the corroboration of a theory, and corroboration can only be expressed as an appraisal. In this respect there is no difference between corroboration and probability. Moreover, I too hold that hypotheses cannot be asserted to be true statements, but that they are provisional conjectures, or something of the sort, and this view, too, can only be expressed by way of an appraisal of these hypotheses. The second part of this objection can easily be answered. The appraisal of hypotheses, which indeed I am compelled to make use of, and which describes them as provisional conjectures, or something of the sort, has the status of a tautology. Thus it does not give rise to difficulties of the type to which inductive logic gives rise. For this description only paraphrases or interprets the assertion, to which it is equivalent by definition, that strictly universal statements, i.e. theories, cannot be derived from singular statements. The position is similar as regards the RST part of the objection, which concerns appraisals stating that a theory is corroborated. The appraisal of the corroboration is not a hypothesis, but can be derived if we are given the theory as well as the accepted basic statements. It asserts the fact that these basic statements do not contradict the theory, and it does this with due regard to the degree of testability of the theory, and to the severity of the tests to which the theory has been subjected, up to a stated period of time. We say that a theory is corroborated so long as it stands up to these tests. The appraisal which asserts corroboration, the corroborative appraisal, establishes certain fundamental relations, viz. compatibility and incompatibility. We regard incompatibility as falsification of the theory. But compatibility alone must not make us attribute to the theory a positive degree of corroboration. The mere fact that a theory has not yet been falsified can obviously not be regarded as sufficient. For nothing is easier than to construct any number of theoretical systems, which are compatible with any given system of accepted basic statements. This remark applies also to all metaphysical systems. It might perhaps be suggested that a theory should be accorded some positive degree of corroboration if it is compatible with the system of accepted basic statements, and if, in addition, part of this system can be derived from the theory. Or, considering that basic statements are not derivable from a purely theoretical system, though their negations may be so derivable, one might suggest that the following rule should be adopted: a theory is to be accorded a positive degree of corroboration if it is compatible with the accepted basic statements and if, in addition, a non-empty subclass of these basic statements is derivable from the theory in conjunction with the other accepted basic statements. I have no serious objections to this last formulation, except that it seems to me insufficient for an adequate characterization of the positive degree of corroboration of a theory. For we wish to speak of theories as being better, or less well, corroborated. But the degree of corroboration of a theory can surely not be established simply by counting the number of the corroborating instances, i.e. the accepted basic statements which are derivable in the way indicated. For it may happen that one theory appears to be far less well corroborated than another one, even though we have derived very many basic statements with its help, and only a few with the help of the second. As an example, we might compare the hypothesis all crows are black with the hypothesis, mentioned in section, the electronic charge has the value determined by Millikan. Although in the case of a hypothesis of the former kind, we have presumably encountered many more corroborative basic statements, we shall nevertheless judge Millikan's hypothesis to be the better corroborated of the two. This shows that it is not so much the number of corroborating instances which determines the degree of corroboration as the severity of the various tests to which the hypothesis in question can be, and has been, subjected. But the severity of the tests, in its turn, depends upon the degree of testability, and thus upon the simplicity of the hypothesis which is falsifiable in a higher degree, or the simpler hypothesis, is also the one which is corroborable in a higher degree. Of course, the degree of corroboration actually attained does not depend only on the degree of falsifiability. A statement may be falsifiable to a high degree yet it may be only slightly corroborated, or it may in fact be falsified. And it may perhaps, without being falsified, be superseded by a better testable theory from which it or a sufficiently close approximation to it can be deduced. In this case too its degree of corroboration is lowered. The degree of corroboration of two statements may not be comparable in all cases, any more than the degree of falsifiability. We cannot deem a numerically calculable degree of corroboration, but can speak only roughly in terms of positive degree of corroboration, negative degrees of corroboration, and so forth. Yet we can lay down various rules. For instance, the rule that we shall not continue to accord a positive degree of corroboration to a theory which has been falsified by an intersubjectively testable experiment based upon a falsifying hypothesis, cf. sections, and we may, however, under certain circumstances accord a positive degree of corroboration to another theory, even though it follows a kindred line of thought. An example is Einstein's photon theory, with its kinship to Newton's corpuscular theory of light. In general, we regard an intersubjectively testable falsification as null, provided it is well tested. This is the way in which the asymmetry between verification and falsification of the IES makes itself felt. Each of these methodological points contributes in its own peculiar way to the historical development of science as a process of step-by-step approximations. A corroborative appraisal made at a later date, that is, an appraisal made after new basic statements have been added to those already accepted, can replace a positive degree of corroboration by a negative one, but not vice versa. And although I believe that in the history of science it is always the theory and not the experiment, always the idea and not the observation, which opens up the way to new knowledge, I also believe that it is always the experiment which saves us from following a track that leads nowhere, which helps us out of the rut, and which challenges us to enter a new way. Thus the degree of falsifiability or of simplicity of a theory enters into the appraisal of its corroboration. And this appraisal may be regarded as one of the logical relations between the theory and the accepted basic statements, as an appraisal that takes into consideration the severity of the tests to which the theory has been subjected. 83. Corroborability, testability, and logical probability. In appraising the degree of corroboration of a theory, we take into account its degree of falsifiability. A theory can be the better corroborated the better testable it is. Testability, however, is converse to the concept of logical probability, so that we can also say that an appraisal of corroboration takes into account the logical probability of the statement in question. And this, in turn, as was shown in section, is related to the concept of objective probability, the probability of events. Thus, by taking logical probability into account, the concept of corroboration is linked, even if perhaps only indirectly and loosely, with that of the probability of events. The idea may occur to us that there is perhaps a connection here with the doctrine of the probability of hypotheses criticized above. When trying to appraise the degree of corroboration of a theory, we may reason somewhat as follows. Its degree of corroboration will increase with the number of its corroborating instances. Here we usually accord to the RST corroborating instances far greater importance than to later ones. Once a theory is well corroborated, further instances raise its degree of corroboration only very little. This rule, however, does not hold good if these new instances are very different from the earlier ones, that is, if they corroborate the theory in a new field of application. In this case, they may increase the degree of corroboration very considerably. The degree of corroboration of a theory which has a higher degree of universality can thus be greater than that of a theory which has a lower degree of universality, and therefore a lower degree of falsifiability. In a similar way, theories of a higher degree of precision can be better corroborated than less precise ones. One of the reasons why we do not accord a positive degree of corroboration to the typical prophecies of palmists and soothsayers is that their predictions are so cautious and imprecise that the logical probability of their being correct is extremely high. And if we are told that more precise and thus logically less probable predictions of this kind have been successful, then it is not, as a rule, their success that we are inclined to doubt so much as their alleged logical improbability. Since we tend to believe that such prophecies are non-corroborable, we also tend to argue in such cases from their low degree of corroborability to their low degree of testability. If we compare these views of mine with what is implicit in inductive probability logic, we get a truly remarkable result. According to my view, the corroborability of a theory and also the degree of corroboration of a theory which has in fact passed severe tests, stand both, as it were, in inverse ratio to its logical probability, for they both increase with its degree of testability and simplicity. But the view implied by probability logic is the precise opposite of this. Its upholders let the probability of a hypothesis increase in direct proportion to its logical probability, although there is no doubt that they intend their probability of a hypothesis to stand for much the same thing that I try to indicate by degree of corroboration. Among those who argue in this way is Keynes, who uses the expression a priori probability for what I call logical probability. See note to section. He makes the following perfectly accurate remark regarding a generalization G, i.e. a hypothesis, with the condition or antecedent or protasis phi and the conclusion or consequent or apodosis F. The more comprehensive the condition phi and the less comprehensive the conclusion F, the greater a priori probability do we attribute to the generalization G. With every increase in phi this probability increases, and with every increase in F it will diminish. This, as I said, is perfectly accurate, even though Keynes does not draw a sharp distinction between what he calls the probability of a generalization corresponding to what is here called the probability of a hypothesis and its a priori probability. Thus, in contrast to my degree of corroboration, Keynes's probability of a hypothesis increases with its a priori logical probability. That Keynes nevertheless intends by his probability the same as I do by my corroboration may be seen from the fact that his probability rises with the number of corroborating instances, and also, most important, with the increase of diversity among them. But Keynes overlooks the fact that theories whose corroborating instances belong to widely different fields of application will usually have a correspondingly high degree of universality. Hence his two requirements for obtaining a high probability: the least possible universality and the greatest possible diversity of instances will as a rule be incompatible. Expressed in my terminology, Keynes's theory implies that corroboration, or the probability of hypotheses, decreases with testability. He is led to this view by his belief in inductive logic. For it is the tendency of inductive logic to make scientific hypotheses as certain as possible. Scientific significance is assigned to the various hypotheses only to the extent to which they can be justified by experience. A theory is regarded as scientifically valuable only because of the close logical proximity, cf. Note to section and text, between the theory and empirical statements. But this means nothing else than that the content of the theory must go as little as possible beyond what is empirically established. This view is closely connected with a tendency to deny the value of prediction. The peculiar virtue of prediction, Keynes writes, is altogether imaginary. The number of instances examined and the analogy between them are the essential points, and the question as to whether a particular hypothesis happens to be propounded before or after their examination is quite irrelevant. In reference to hypotheses which have been a priori proposed, that is, proposed before we had sufficient support for them on inductive grounds, Keynes writes, if it is a mere guess, the lucky fact of its preceding some or all of the cases which verify it adds nothing whatever to its value. This view of prediction is certainly consistent. But it makes one wonder why we should ever have to generalize at all. What possible reason can there be for constructing all these theories and hypotheses? The standpoint of inductive logic makes these activities quite incomprehensible. If what we value most is the securest knowledge available, and if predictions as such contribute nothing towards corroboration, why then may we not rest content with our basic statements? Another view which gives rise to very similar questions is that of Karl. Whilst I believe that it is the simple theories, and those which make little use of auxiliary hypotheses, cf. section, which can be well corroborated, just because of their logical improbability, Karl interprets the situation in precisely the opposite way, on grounds similar to Keynes's. He too sees that we usually ascribe a high probability, in our terminology, a high probability of hypotheses, to simple theories, and especially to those needing few auxiliary hypotheses. But his reasons are the opposite of mine. He does not, as I do, ascribe a high probability to such theories because they are severely testable, or logically improbable, that is to say because they have, a priori as it were, many opportunities of clashing with basic statements. On the contrary, he ascribes this high probability to simple theories with few auxiliary hypotheses because he believes that a system consisting of few hypotheses will, a priori, have fewer opportunities of clashing with reality than a system consisting of many hypotheses. Here again one wonders why we should ever bother to construct these adventurous theories. If we shrink from contact with reality, why invite it by making assertions? The safest course is to adopt a system without any hypotheses. Speech is silver, silence is golden. My own rule, which requires that auxiliary hypotheses shall be used as sparingly as possible, the principle of parsimony in the use of hypotheses, has nothing whatever in common with considerations such as Karl's. I am not interested in merely keeping down the number of our statements, I am interested in their simplicity in the sense of high testability. It is this interest which leads, on the one hand, to my rule that auxiliary hypotheses should be used as sparingly as possible, and on the other hand, to my demand that the number of our axioms of our most fundamental hypotheses should be kept down. For this latter point arises out of the demand that statements of a high level of universality should be chosen, and that a system consisting of many axioms should, if possible, be deduced from, and thus explained by, one with fewer axioms, and with axioms of a higher level of universality. 84 Remarks concerning the use of the concepts true and corroborated. In the logic of science here outlined, it is possible to avoid using the concepts true and false. Their place may be taken by logical Considerations about derivability relations. Thus we need not say, the prediction P is true provided the theory T and the basic statement B are true. We may say, instead, that the statement P follows from the non-contradictory conjunction of T and B.